So hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing amazing, all of you are doing great. So quickly, let me know in the chats with some fire emojis if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats. Quickly, my dear students. Quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Quickly. Yes? So people, as you all must be knowing, today it's going to be our day 33 of our Game of NEET preparation, right? So what does that mean? That means we are done with 32 chapters till now, right? So almost 40% syllabus we have completed in 32 days, right? Now, the remaining 60% will be also completing in the upcoming days, yeah? So quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Yes, because today it's going to be a mega marathon, my dear students. A mega marathon it's going to be. Because the chapter which we are going to do today, that is considered to be one of the difficult chapters of chemistry when it comes to the NEET preparation, basically. But since you know, I always start every chapter with the basics, with the scratch, right? From the scratch itself, I start every chapter. So this particular chapter also, I'll be starting from the basics, from the scratch. So whether you have studied the chapter before or not, no worries at all. Yeah? No worries at all. I'll be exactly starting from the basics. Slowly we'll scale up all the things. And at the same time, let me tell you, this particular year, from the chapter Thermodynamics, there will be minimum 4 questions asked. Minimum 4 questions, right? And the problem patterns which I'll be giving you in the today's session, remember, nothing will be asked apart from those problem patterns which I'll be showing you in the today's session. So are you guys ready for the mega marathon? Are you guys ready for the mega marathon, people? Let me know quickly in the chats if all of you are ready for the marathon. And a lot of students are asking, how long will it take? I have no idea how long it's going to take. It might take 9 hours, it might take 10 hours, 11 hours, whatever, right? Till we complete this chapter, I'll be standing here with all of you. And I would want all of you to be with me till the end. Yeah? Because it's one huge chapter, guys. It's one huge chapter. So it deserves 9 to 10 hours for sure. Even more than that. Even more than that. Because I'll be going into the details of every single topic here. Right? It's not just I'll be showing you the problem patterns or only the theory. Every single thing I'll be discussing from the basics. That's why this particular chapter is going to take almost 9, 10, 11 hours. I don't know. Yeah? So you have to be with me till, I believe, 2, 3 in the morning. Right? Yeah? Perfect. So should we start the session then? Are you guys ready with your pen and paper? Are you all ready with your pen and paper? Let me know in the chats quickly. Yes, atomic structure will be also done. Just wait. Right? Are you all ready with your pen and paper? Quickly. And I can see not everyone has liked the session yet. Yeah? Is it really difficult to like the session? Huh? So the ones who have not liked the session yet, do like this particular session. Do share this particular session with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for everyone. Everyone means everyone. Yeah? Perfect. So people, before starting this particular session, let me just quickly give you the flow of the topics, right? Let me give you the session flow, which I'll be following here in this particular thermodynamics. Okay, let me exactly show you from where we are going to start and what exactly is going to be the session flow. The first topic which we are going to cover in the today's session, first topic which we are going to cover in the today's session, just a second. All right. First of all, we shall be talking about the basic terminologies. The basic terminologies which are involved in the chapter thermodynamics. This thermodynamics chapter, it has got a different language basically. Okay? It has got a separate language and we'll be understanding that language first. So that is why I'm going to start with the basic terminologies, and from these basic terminologies, questions are asked. I'll let you know what all different types of questions. Number one, after covering the basic terminologies, we shall be discussing about heat and work. This is again one very important topic which we are going to discuss, heat and work. After covering the topic heat and work, we shall be talking about heat capacities. We shall be discussing about heat capacity. After covering the heat capacity, we shall be talking about the thermodynamic processes. Introduction to thermodynamic processes. Introduction to thermodynamic processes. Once we are done with the introduction of the thermodynamic processes, we shall be talking about something called as internal energy, which is again a very important topic. Internal energy and different problem patterns. After covering internal energy, we shall be doing the first law of thermodynamics. First law of thermodynamics, right? And after covering the first law of thermodynamics, we shall be going into the topic, which is again one very important one, that is enthalpy, right? After covering the enthalpy, it's going to be delta U and delta H relation, which is again carrying high weightage in this particular chapter. Delta U and delta H relation and different types of questions based on delta U and delta H. Then we shall be talking about the different types of thermodynamic processes in detail, right? So processes in detail. And these processes will include isochoric process in detail, isobaric process in detail, isothermal process in detail, adiabatic process in detail, cyclic process in detail. Cyclic process, then we'll be talking about the polytropic process. Polytropic processes in detail. And then we shall be talking about the free expansion. Free expansion. This is again one important topic. After discussing the free expansion, we shall be discussing about the calculation of molar heat capacity for a process. Calculation of molar heat capacity for a process, right? Once we are done with this particular topic, then we shall be covering entropy and its application. Once we are done with entropy, we are going to do the Gibbs free energy in detail. And once we are done with the Gibbs free energy, we shall be discussing the enthalpies of the reactions as well. Enthalpy of reaction. So basically, this is going to be the session flow which we shall be following in this particular session. Yeah? So people, this is your complete thermodynamics basically. This is your complete thermodynamics. This is your complete thermodynamics. And again, I'm repeating the same thing. You can expect 4 to 5 questions from this particular chapter in your NEET 2024. In your NEET 2024. 4 to 5 questions you shall be expecting from this particular chapter. Okay? So should we start the session? Should we start the session? Should we start the session? Yeah? Already? Thermochemistry is this one. You call this as thermochemistry, enthalpy of reactions. You call this as thermochemistry, by the way. Right? Zahran, let's keep it confidential for now. Okay, people. Absolutely. MCQ solving will happen in the today's session only. I told you every single pattern I'll be discussing. Every single pattern. Perfect. So let's start then. But before starting, let me have some water first. Yeah, and then we shall start. Just a second, people. All right. So let's start. The first topic of the session, which are going to be the basic terminologies in thermodynamics. The basic terminologies in the chapter Thermodynamics. My dear students, the first terminology which we shall be discussing today, that is going to be system. After system, I'll be talking about something called as surroundings. And then I shall be talking about something called as boundary, which is what you call as wall as well. Now, first of all, how do you exactly define these three terminologies? How do you define these three terminologies? What is system basically? Let me tell you, system, it is defined as that part of the universe, which is under thermodynamic investigation. I want you guys to write all these things with me. That part of the universe which is under thermodynamic investigation. What does it mean exactly? You'll get the idea in some time. But before, you need to write all these things. Number one, surrounding. How do you exactly define the term surrounding? The part of the universe except system. The part of the universe except system is something which you call a surrounding. Boundary. Anything that separates system from the surroundings. Anything that separates system from the surroundings is something which you call as boundary. Now, how exactly we are going to understand these three terminologies? These are very simple terminologies, people. Try to understand carefully what exactly I'm going to say. For example, imagine that I have taken a container over here, which is closed on all the sides. In this particular container, imagine that I am keeping water. I am keeping water inside this particular container. So inside this particular container, what do we have? We have got water in liquid state in this particular container, right? Now, people, imagine I have to increase the temperature of this water. Imagine that I have to increase the temperature of this particular water. Well, in order to increase the temperature of this water in the container, what do I have to do? I have to supply some heat. Imagine I'm supplying some heat to this particular water. Why am I supplying heat to this water? Because I want to increase the temperature of this particular water, right? For example, I have to do one thermodynamic investigation. Let's assume that I have to do one thermodynamic investigation related to this particular water which is there in the container. And what is that thermodynamic investigation? For example, I have to do an investigation in which I have to check one simple thing. What is that thing? Let's say I have to check in order to increase the temperature. In order to increase the temperature of this water by 1 degree. In order to increase the temperature of this water by 1 degree, I need to check how much heat is required. This is one investigation which I need to do. I have taken water in this particular container. And for this particular water which is there in the container, I have to do one investigation. I have to check how much heat I need to supply to this particular water such that its temperature raises by 1 degree. Yeah? Can I say this particular water in the container right now is under thermodynamic investigation? Absolutely. This water in the container right now is under thermodynamic investigation. And that part of the universe which will be under thermodynamic investigation, what do you call that as? You call that as the system. So this water in the container right now is under investigation. So I'll be calling this water right now as my system, right? Point number 1. Point number 2. Whatever is there in the universe except this system. Whatever is there in the universe except the system. Whatever is there in the universe except the system. That is something which you'll be calling as surrounding. So anything which is there in the universe, everything which is there in the universe except this water right now, that is something which I'll be calling as surrounding, right? And at the same time, do you see these walls of the container? Do you see these walls of the container are basically separating your system from the surroundings? Absolutely. And anything that separates system from the surrounding, that is what you should be calling as the boundary. That's what you should be calling as the boundary. So 3 terminologies which you will be remembering from now onwards. Point number 1, system. That part of the universe which will be under thermodynamic investigation, that is something which you should be calling as system from now onwards. Point number 2, all the other things in the universe except the system, that are your surroundings. Anything that separates your system from the surroundings, that is something which you should be calling as the boundary, right? So these are the 3 basic terminologies from which we start this particular chapter, which is thermodynamics. I believe this is clear to everyone. If this is clear, let me know in the chats with some fire emojis quickly. Let me know in the chats with some fire emojis if it is clear. Quickly, people. Everyone, quickly in the chats. If all the things are clear, let me know in the chats with some fire emojis. I believe every single thing is clear, yeah? Perfect. Now, people, what are the different types of the boundaries? What are the different types of the boundaries? How do you classify these boundaries? Number 1, the first type of the boundary is your real boundary. The second type is what you call as imaginary boundary. Imaginary. Then in this chapter, there is one more boundary which you'll see. That's what you call as adiabatic boundary. Or let's just do one thing, or let's write it here only. Adiabatic boundary. And the fourth one, which I shall be discussing with you, what do you call that as? Diathermic boundary. So what are these different boundaries which we are going to discuss here? Number one, real boundary, imaginary boundary, diathermic boundary, adiabatic boundary, right? Now, how do you exactly define them? How do you exactly define them? Have a look, people. What exactly these boundaries are all about. First of all, any boundary which can be seen by the eyes. Any boundary which can be seen by the eyes is something which you call as a real boundary. For example, if you look at the walls of the container, right? These walls of the container, they are separating your system from the surroundings. You call it as the boundary. Now, this is the boundary which you can exactly see from by your eyes, right? This is the boundary which you can exactly see by your eyes, that it is separating system from the surrounding. And any such boundary which can be seen by the eyes, right? Any such boundary which can be seen by the eyes, you call that as the real boundary. Point number one. Point number two. How do you define the imaginary boundary then? Imaginary boundary cannot be seen by the eyes. Cannot be seen. Now, how you are going to justify this particular imaginary boundary here? How you guys are going to justify this imaginary boundary here? See, guys, what exactly you need to do. For example, imagine that this is one container which I have. Imagine that this is one container which we have. And in this particular container, I'm keeping water in liquid state. This is water here. This is your H2O liquid here. Correct? This is your H2O liquid here. This water, imagine it is under investigation. So this water is my system. So this water in the container, it is my system right now. It is my system right now. Now imagine that you're supplying some heat to this water. Imagine that you're supplying some heat to this water in the container. Now, when you supply heat to this water, what will happen? Water will start undergoing evaporation. Water will start getting converted into its vapors. Water will start getting converted into its vapors. And those vapors will go into the atmosphere because I have kept the container open on one side. I have kept the container open on one side. So these vapors will start going into the atmosphere. Perfect. Now, my dear students, try to understand one simple thing. See, if you look at this part of the container, I can categorically say that this part of the container is separating system from the surroundings, right? This part of the container is separating system from the surroundings. And this part of the container is something which I can see by my eyes, that it's separating system from the surroundings. So I should be calling this part as the real boundary. It is my real boundary here, right? Which I can see. This particular part of the container, again, you can see it by your eyes, separating system from the surroundings. So again, it's a real boundary. Look at this part of the container. Again, it's going to be a real boundary. Here. Now comes the point. First of all, if you look at the top layer of water here, can I say top layer of water and the vapors, they are basically in direct contact with each other? Absolutely, the top layer of the water and its vapors, they are in direct contact with each other. Can I say between the top layer of the water and the vapors above it, can I say a fine layer will be existing, which we cannot see by the eyes, but that fine layer will be separating system from the surroundings? That will be separating system from the surroundings? Yes. So what do you call that layer as? What do you call that particular layer as? Quickly, what do you call that particular layer as? Quickly, people. You'll be calling that as the imaginary layer, imaginary boundary, right? Imaginary boundary. So between the top layer of water and the vapors, a fine line will exist, which we cannot see by the eyes, but that fine layer is separating your system from the surroundings, and you'll be calling that as the imaginary boundary. I believe this imaginary boundary is clear, right? Now, how do you define the diathermic boundary? It is pretty much simple. Diathermic boundary is the one. Diathermic boundary is the one which allows the exchange, of heat between system and surroundings. Between system and surroundings. If you look at this particular boundary over here, right? This particular boundary, which I've shaded, right? Which I've shaded. It is allowing the exchange of heat between system and surroundings, right? I was sending heat from surrounding to the system. I was sending heat from surrounding to the system, right? Any such boundary which allows the exchange of heat between system and surroundings. Either heat can go from surrounding to system or from system to surroundings. That particular boundary which allows the exchange of heat between system and surroundings, you call that as the diathermic boundary, right? Now, what do you think will be the adiabatic boundary? Adiabatic boundary, it does not allow the passage of heat. It does not allow the passage of heat either from system to surroundings or from surrounding to system. Adiabatic boundary is the one. Adiabatic boundary is the one which does not allow the passage of heat either from system to surroundings or from surrounding to system. And let me tell you, there is no boundary as such. There is no boundary as such which can block 100% heat transfer between system and surroundings. There is no boundary as such which can block 100% heat transfer between system and surroundings. So this adiabatic boundary, it is a hypothetical concept. It is an imaginary concept. It is an imaginary concept. I believe all these types of boundaries are clear to you. If they are clear, let me know once in the chats with some fire emojis quickly. Everyone. Everyone, people. Everyone. So any boundary which can be seen by the eyes, that's called your real boundary. Which you cannot see by your eyes, that's imaginary. Which allows the passage of heat either from system to surroundings or from surrounding to system, that's what you call as diathermic. Which does not allow the passage of heat either from system to surroundings or from surrounding to system, that is something which you call as the adiabatic boundary, right? Now, what are the different types of system which we have? What are the different types of system which we have? The first type of system is what you call as open system. Then you have got the closed system. And then you have got the isolated system. Then you have got the isolated system. So how do you exactly classify them? How do you differentiate them? My dear students, my dear students, any system that allows the exchange of energy as well as matter. Energy as well as matter with the surroundings. With the surroundings is something which you call as open system. What is meant by it, you'll get the idea in some time. But before that, how do you define closed system? Closed system is the one which allows the exchange of energy, but not the matter. Isolated system, it neither allows the exchange of energy nor the matter with the surroundings. Now, what is meant by these three terminologies? These are again some basic terminologies which we have. Open system, people. What is an open system? Have a look. Let me take the same example which I took in the beginning. Or let me make it once again so that it becomes properly clear to you. Imagine this is the container, which is open on one side. And in this particular container, what exactly I'm keeping? I'm keeping water in this particular container. This water is in liquid state. And this water in the container, it is under investigation. So this water, I should be calling my system here. Perfect. Apart from this water, whatever is there in the universe, that's something which you call as surroundings. Right? That is something which you call as surroundings. Perfect. Now, my dear students, just to make you understand, imagine the walls of the container here. Imagine the walls of the container here are diathermic. Just to make you understand. Imagine the walls of the container here are diathermic. If the walls are diathermic, they'll be allowing the passage of heat either from system to surroundings or from surrounding to system. Right? Imagine that I'm supplying some heat to the system. Imagine that I'm supplying some heat to the system. Correct? So can I say between the system and the surroundings, exchange of energy is taking place? Right? Right now, absolutely you can see exchange of energy taking place between system and surroundings. And right now I'm showing this exchange in terms of heat. Okay? Number one. Number two, due to the supply of heat, what will happen? This water will start getting converted into vapors, and those vapors will enter into the atmosphere. Those vapors will enter into the atmosphere. Can I say this particular system is exchanging energy as well as matter with the surroundings? Absolutely. This particular system, it's exchanging energy as well as matter with the surroundings. And whenever you see such kind of the system, which will be exchanging energy as well as matter with the surroundings, that is something which you call as open system. That's what you call as open system. Number one. Number two, if I close this container from the top, now tell me, will this particular system be exchanging matter with the surroundings? No, it won't exchange matter with the surroundings because I'll close this container from the top. And any such system which allows the exchange of energy only, not the matter with the surroundings, you call that particular system as the closed system. You call that as a closed system. And any such system which neither allows the exchange of energy nor the matter, what do you call that as? You call that as the isolated system. Can you give me the perfect example of isolated system? Can you give me the perfect example of the isolated system quickly? Quickly, people. Can you give me the perfect example of the isolated system? I'm talking about perfect example. Perfect example. The only perfect example of the isolated system is when you take entire universe. When you take entire universe as under the thermodynamic investigation. If you take entire universe under the thermodynamic investigation, imagine this is my universe. Imagine this is my universe, right? Perfect. Imagine this is the universe. And I am taking entire universe under thermodynamic investigation, right? Now tell me one thing. There is nothing apart from this universe which we have. This is the entire thing, right? Will it exchange energy or matter with some other thing? Because there is nothing apart from this universe which we have, right? Perfect. So when you take the entire universe under thermodynamic investigation, when you consider entire universe as your system, this becomes your example of the perfectly isolated system. This becomes your example of the perfectly isolated system. So universe is the only example of the perfectly isolated system. I believe all these things are absolutely clear to you. Yeah? Let me know in the chats quickly. Everyone. Everyone, people, everyone. Quickly in the chats. Quickly in the chats. Quickly in the chats. Yeah, quickly in the chats. Quickly in the chats. These are the basic terminologies. We have to make sure that these basic terminologies are clear to us. Then we can enter into the chapter basically. I have not entered in the chapter yet. But from this particular topic, extensive properties, question is asked. I'll let you know. I'll let you know. I'll let you know about that. So I believe every single thing is clear till now. Okay, what are your extensive properties? How do you define your extensive properties? Let me tell you that. Those properties of the system, whose value, does not change. Those properties of the system whose value changes on changing the size of the system or the amount of substance present in the system. Or what we call as extensive properties, otherwise intensive. Let me make you understand what these extensive and intensive properties are exactly all about. Then I'll give you some examples which are much needed in this particular extensive intensive properties, right? From those examples, you will be getting a question, and I'll let you know what kind of question. Understand properly what exactly I'm going to do. Just to make you understand, imagine that this is a solid block. Over here. I'm assuming that this particular solid block is under investigation right now. It is under thermodynamic investigation right now. So this complete solid block which I've taken over here, it is my system right now. This is my system right now. For example, the mass of this particular solid block I'm representing with M. Volume of this particular solid block is represented by V. Temperature of this particular solid block is represented by T, for example. Now people, what exactly am I going to do? I am going to divide this solid block into two equal parts. I divided this solid block into two equal parts. And what am I exactly doing? I'm only taking this part of the block. And this part of the block I'm representing over here. Perfect. I've represented this particular part of the block over here. Now you tell me one thing. What did I do? I divided this block into two equal parts, and later on I took one small part of it, right? Now you tell me, if I ask you what will be the mass of this smaller block, is it going to be same M or it's going to be M by 2? It's going to be M by 2. Volume of this particular block is going to be V by 2, but temperature of this particular part, it is not going to be T by 2. It is still going to remain the same. It's going to be T. It's evident. If this is the marker, right? If this marker has got the temperature of 25 degrees centigrade, I'm dividing this marker into two equal parts. Then I'm taking one smaller part. That one smaller part will have the temperature of 25 degrees centigrade as well. Yeah? Now people, if you try to understand carefully, how many properties of the system I defined? I defined three properties of the system: mass, volume, temperature. When I changed the size of the system, the value of mass changed from M to M by 2. Volume changed from V to V by 2. But temperature did not change from T to T by 2. It remained the same. So can I say, I defined three properties of the system, and among these three properties, there are two properties. One is your mass, one is volume. These two properties are the ones whose value changes on changing the size of the system. And those properties of the system whose value changes on changing the size of the system or amount of substance present in the system. Those are what you call as extensive properties. So can I say your mass and volume are the extensive properties? Absolutely, people. I would say your mass and volume here are extensive properties. Now try to understand what exactly I'm going to say. Okay, try to understand what exactly I'm going to say. So, what you have to do over here, you have to remember the examples of extensive and intensive properties. Do remember them directly. Examples of extensive and intensive properties, right? You are asked in the examination. I'll show you the questions in some time. What are the examples of extensive properties? What are the examples of intensive properties? So you have to remember them one by one. So first example, which you already know now, that is mass, volume, right? Mass, volume. There is something called as heat capacity, which we shall be discussing afterwards. Just remember them for now. Heat capacity, right? Heat capacity. There is something called as internal energy, which we shall be discussing afterwards. Internal energy. You might have heard something called as enthalpy as well. You might have heard about something called as entropy as well. You might have heard about something called as Gibbs free energy as well. Gibbs free energy. These are the common examples of the extensive properties. These are the common examples of the extensive properties. Now, what are the common examples of the intensive properties? The first thing which you already know, that is temperature. Temperature. Pressure. By the way, one thing I forgot to write over here, number of moles. Number of moles. That's again one example of extensive property, right? Okay. Temperature. Pressure. Density. 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 Specific heat capacity. Specific heat capacity. What is that? You'll get the idea after some time when I'll be teaching you, right? Temperature, pressure, density, specific heat capacity. Specific heat capacity. Molar heat capacity. Molar heat capacity. Concentration. Concentration. pH. pH. Boiling point. Boiling point. EMF of the cell. EMF of the cell, etc. These are all the examples of the intensive properties. These are all the examples of the intensive properties. Fahim is asking, how come cell potential? How come cell potential is the example of intensive? Fahim, our next chapter is going to be electrochemistry. There in detail, you'll get the answer of your questions. Right now, I don't want to deviate, okay? I don't want to deviate from the actual topic. The next chapter which we are going to do, that's electrochemistry. In that electrochemistry, you'll get to know why this is so, okay? Perfect. Now, guys, there are some special features. There are some special features which are related to these extensive and intensive properties, which I would want every one of you to remember. So I'm writing the heading over here as important features of extensive and intensive properties. Important features of extensive and intensive properties, which you will remember, which are very, very, very important and logical at the same time. See, guys, first and the most important one. Extensive properties. Extensive properties are additive in nature. Extensive properties are additive in nature, whereas intensive properties are non-additive. Point number one. What is meant by this? You'll get the idea in some time. Just take a note of these things first. Point number two. Division of, by the way, from this particular first statement, you get one very, very, very important question in electrochemistry. From this particular question, from this particular statement, you get one amazing question in electrochemistry, right? Okay, so do remember this. Extensive properties, these are additive, whereas intensive properties are non-additive. What it means? Wait for that. Division of extensive properties makes the new property as intensive. makes the new property intensive in nature. Makes the new property intensive. This is point number 2. Point number 3. Point number 3. An extensive property when expressed per unit mass or per unit moles or per unit volume becomes intensive. What exactly is meant by these 3 statements which I'm writing over here? And again, I'm telling you, these are 3 very, very, very important statements. Why is that? Try to understand. Try to understand why exactly am I telling you all this. The first statement which I told you, the first statement is extensive properties are additive in nature, whereas intensive properties are non-additive in nature. It's one very simple statement. See, imagine I have got these 2 containers over here, identical in nature. Imagine you have got water in this container as well as water in this container, right? The mass of the water in the container is m, its volume is v, its temperature is T. The mass of this water in the container is m, its volume is v, its temperature is T. Now people, I'm adding these waters into the final container. This is my final container wherein I'm adding them up. When I'm adding them up, this is the final container which is filled with water. If I ask you what is the mass of this particular water, you will say it's going to be 2 times m. Volume occupied by this water is going to be 2 times v, but temperature is still going to remain the same. That is T. That is T. Right? That is T. Now, how many properties of the system I defined here? I defined 3 properties of the system. And out of these 3 properties, how many are extensive? Mass is extensive, volume is extensive, right? Mass is extensive, volume is extensive. Now people, do you see one thing? This m plus m finally made 2m. V plus v finally made 2 times v, right? So these 2 properties, this mass and volume, they were your extensive properties. And as you can see, you are adding the extensive properties directly. M plus m makes it 2m. V plus v makes it 2v. So you are adding the extensive properties directly. But can you add the intensive properties directly? As you can see over here, if intensive properties were also additive in nature, then the final temperature of this water should have been 2 times T. But that's not the case, right? That's not the case here. Okay? So do remember, your extensive properties, they are additive in nature. You can add or subtract extensive properties directly, but you cannot add or subtract the intensive properties directly. This is one very important point, people, which you have to remember. Okay? Jeff, batch access for JE Energized has been extended. You check it out. Okay, this was at point number 1. Point number 2. As I told you already, division of extensive properties makes the new property as intensive. What exactly it means? Try to understand. For example, this M represents mass of the substance. V represents volume of the substance, right? M represents mass of the substance, V represents volume of the substance, right? Now tell me one thing. Was mass extensive or intensive? This was extensive. Volume. This was extensive. When you are dividing them up, mass of the substance divided by volume of the substance, the new property becomes your density. But is this density the example of extensive or intensive? It is the example of intensive property. You know it, right? So people, when we divided 2 extensive properties, the new property which came into existence, that became intensive. Remember, when you divide 2 extensive properties, the new property which comes into existence, what do we call that as? That is going to be always intensive in nature, right? For example, number of moles, and here it's volume. Number of moles is extensive. Volume is also extensive, right? You are dividing them up. Moles per unit volume is something which you call as concentration, right? This was extensive. This was extensive. When you divided these two extensive properties, the new property which came into existence, it is going to be your intensive one. It's going to be your intensive one. So I believe your second statement is clear. Division of extensive properties makes the new property as intensive. The third one. People, there's a term which we shall be discussing in some time. That's called as heat capacity, which is represented by C. Heat capacity. Heat capacity is the example of extensive property. It is the example of extensive property. Whenever you express extensive property per unit mass, per unit moles, or per unit volume, the new property which comes into existence, that's always going to be your intensive. For example, the C, it is the heat capacity, right? If I write C divided by N, heat capacity per unit mole, this is something which you call as molar heat capacity. There's something which you call as molar heat capacity. And afterwards, you'll get to know that molar heat capacity, it is intensive in nature. Once we study the molar heat capacity in detail, there you'll understand this molar heat capacity is intensive. When I express this heat capacity per unit mass, it becomes specific heat capacity. We call this as specific heat capacity. Extensive property expressed per unit mass, per unit moles, or per unit volume. The new property which comes into existence, that's intensive, right? Extensive property per unit volume, the new property becomes intensive, right? For example, S represents your entropy. Understand, S represents entropy. Entropy is the example of extensive property, right? Now, entropy per unit moles, this is called as molar entropy. This is what you call as molar entropy. So let me know in the chats what will be the nature of this molar entropy. This was extensive expressed per unit moles. The new property which comes into existence, that's going to be intensive, right? Right, people? Enthalpy, enthalpy, it is an extensive property. Per unit mole, it becomes your molar enthalpy, right? This is going to be your intensive property. Perfect. So do remember, whenever an extensive property is expressed either per unit mass, per unit moles, or per unit volume, the new property that comes into existence, that is always going to be the intensive. Sir, are you joining Sky classes? Just wait and watch. Is it clear, people? Is every single thing clear till here? So let's see if there were some questions asked from the concepts which I discussed till now. I believe yes, there were some questions which were asked. Just a second. Okay. This is one asked question. Tell me, what do you think is going to be the answer of this particular question? It is an asked question, people. Out of internal energy, boiling point, pH, and EMF of the cell, intensive properties are. This is the asked question, and you have to answer this one. You have to answer this one, people. Quickly. Internal energy is extensive. Boiling point is intensive. pH is intensive. EMF is intensive. So it's going to be second, third, and fourth. That's going to be intensive. So second, third, and fourth. So it has to be option number 2. I believe it's clear to everyone. It has to be option number 2. This is one more question, which is the asked question in your competitive examination. Molar entropy and temperature. Are temperature is intensive, and molar entropy, which is entropy per unit mole, that's also intensive. You know it. A few minutes back only we have discussed, right? So these are the examples of your intensive properties. Perfect. So option 1 is the correct answer of this particular question, right? Okay, I believe whenever these sort of questions are asked, you should be in a position to answer these questions. Yeah? You should be in a position to answer these particular questions, people. You should be in a position to answer these sort of questions. Okay? Now, let's move on to a few more things. Before moving on to a few more things, let me know in the chats if all the things are clear. Let me know in the chats if all the things are clear. Boiling point. How come boiling point will be extensive? It is intensive. Right? Boiling point of 100 ml of water is 100 degree. Boiling point of 1000 liters of water is also 100 degree, right? So it is mass independent, sorry. Perfect? Perfect, guys. Quickly in the chats. Quickly in the chats. Everyone. Everyone, quickly. Are you guys sleeping or what? I want everyone to let me know in the chats if all the things which we have discussed till now are clear. Perfect. Then let's move on to something called as one more basic terminology. State parameters. Or you call them as the state variables. You can call them as the state variables as well. State parameters or state variables. Now, what are these state parameters? How do we exactly define them? Try to remember a few things about state parameters, which will be used later on. State parameters are the ones. These are the parameters, or I can say these are the variables which defines the state of the system. These are the variables which define the state of the system. Point number one. Point number one. Point number two. On changing the value of state parameters. On changing the value of state parameters, the state of the system automatically changes. The state of the system automatically changes. What is meant by these two important parameters here? Try to understand. Try to understand, people. State parameters. As I told you, these are the parameters which exactly define the state of the system. For example, imagine that this is the container, and this particular container contains an ideal gas. This is an ideal gas in the container. And this ideal gas, imagine this is under investigation. So this ideal gas is my system right now. It is my system right now, right? Now, people, imagine that you are calculating the pressure of this ideal gas. For example, that is P1. Let's say volume of this ideal gas is V1. Moles of this ideal gas, N1. Temperature of this ideal gas, T1. Imagine I took the ideal gas in the container and I'm measuring its pressure, its volume, moles, and temperature. Now, after measuring these parameters, I am telling you that this ideal gas is present at its initial state. Right? When the pressure of the ideal gas is P1, volume is V1, temperature is T1, moles are N1. I'm telling you that this ideal gas is present at its initial state. So I would say these are basically the parameters. These are basically the parameters which are defining the state of the system. These are the parameters which are letting you know whether the system is present at its initial state, whether the system is present at its final state, whether the system is present at its intermediate state, or whatever. Yes? Someone is saying, sir, voice is not clear. Let me just quickly check it. If the voice was clear and you are just playing around, you are going to get blocked forever from this channel. This was clear and you are just playing around and get blocked. It's clear, right? It's clear. Do you want me to block you now? Yeah? Should I be blocking you? Should I be blocking you right now? Look here now. Sir is very kind, yeah? All right, so what I was talking about, I was telling you that these are the parameters, these are the variables of the system which exactly define the state of the system. By knowing the value of these parameters, you get the idea whether the system is present at its initial state, final state, intermediate state. So in short, I would say something like this, that these are the parameters which are defining the state of the system, and any such parameter which define the state of the system, you call that parameters as the state parameters, right? And people at the same time, whenever you would want to remember this particular thing as well, whenever you would want to change the state of the system, whenever you would want to change the state of the system, for example, you want to take the system from initial state to final state. You want to take the system from initial state to final state. Whenever the state of the system needs to be changed, we are supposed to change the value of state parameters. So when you change the value of these state parameters, the state of the system automatically changes, right? And do remember, minimum, if you change one of these state parameters, if you change the value of one of these state parameters, the state of the system automatically changes. For example, I'm changing the pressure from P1 to P2, volume from V1 to V2, temperature from T1 to T2, moles from N1 to N2. What did I do? I changed the value of all the state parameters. And when you change the values of state parameters, the state of system automatically gets changed. Again, I'm repeating, if you change the value of even one state parameter, the state of the system automatically gets changed. So what are state parameters? State parameters are the ones which define the state of the system. Number one, if we change the value of state parameters, the state of the system automatically changes. Minimum, if you change one state parameter, the state of the system will change. Do remember this. Yeah? Perfect. Now, people, there is one more basic terminology. What is that? This is something important. State functions and path functions. State functions and path functions. What are your state functions? What are your path functions? I'm not going to go into much of details of this particular topic. There are a few things which you need to remember. That is enough when it comes to your NEET, right? State functions. State functions are the ones whose value depends on the initial state and the final state of the system. Point number one. Point number two, state functions are path independent. State functions are path independent. State functions are path independent. We always calculate change in the value of a state function, and that change is represented by delta. We always calculate change in the value of state function. And change in the value of state function is always equal to final value of state function minus initial value of state function. Final value of state function minus initial value of state function. What are the examples of the state functions? Your internal energy. In the books, you would have always seen internal energy like this, delta U, right? Enthalpy as delta H. Gibbs free energy as delta G, right? So if I ask you, what are the examples of your state functions? I would say your internal energy, enthalpy, Gibbs free energy, right? Entropy, pressure, volume, temperature. These are all your examples of the state functions. So do remember these 7 state functions. 1, 2, 3, 4, 5, 6, 7. So internal energy, enthalpy, entropy, Gibbs free energy, pressure, volume, temperature. These are the examples of your state functions. These are the examples of your state functions. Do remember them. Do remember them. Right? Do remember them. These are important. These are the examples of your state functions. Their value only depends on initial and final state of the system. They're path independent. They're path independent. They're path independent. Yeah? They're path independent. Here only, there is one more theoretical topic. What is that? That is path function. That is path function. How do you define the path functions? First of all, path functions, they also depend on the initial state and final state of the system. They also depend on initial and final state of the system. But apart from that, they are path dependent. They are path dependent. And the examples are heat and work. These are the examples of the path functions. Now guys, here, 2 things which you have to remember. First of all, they're examples of state functions, path functions, which can be asked in your exam. And number 2, which I'm telling you right now. Take a note of this particular thing which I'm telling you right now. For example, A is a state function. Let's say A is a state function. B is a path function. Imagine your A, it is a state function, and B is a path function. B is a path function. Now people, if I multiply this A by D, that means I'm writing dA here, and here I'm multiplying with D as well. I'm writing dB here, dB here, dA, dB. I multiplied state function with D. I multiplied path function with D as well. Now, what is meant by this dA? dA I'll be calling as small change in A. But this dB, I'll be calling it as small amount of B. I won't be calling it as change. This is going to give you the small amount of B. Whenever state function is multiplied by D, it gives you the value of small change in state function. This gives you small amount of path function. Point number 1. Point number 2. If I integrate this dA over here and if I integrate this dB over here, what do I get? Integral of small change, it gives me the large change. And that large change I'm representing by delta A. That large change I'm representing by delta A. So it gives you the value of large change in A. But here, integral of small amount gives me the total amount. And total amount I'm not representing with delta. I'll be representing it with capital B, right? It gives me the total amount of B. It gives me the total amount of B. Now you are going to let me know the answers of few things. Get activated in the chats. Get activated in the chats. People, I'm writing U here. U is basically the internal energy, which is a state function. And here, W, which represents work. Work is the example of path function. Work is the example of path function. Now tell me, du represents what? And dw represents what? Quickly in the chats. What should I be calling this du as? Should I be calling it as small amount of internal energy or small change? Quickly. I will be calling it as the small change in internal energy. Right? This I will be calling as, I won't be calling it as small change in work because there is nothing called a small change in work. Right? This is small amount of work. This is small amount of work. Right? Now, if I integrate this du and if I integrate this dw, what do I get? Integral of small change in internal energy gives me what? Gives me what? It gives me total change in internal energy or large change in internal energy. It gives me total change in internal energy. And here, integral of small amount of work, it gives me total amount of work. Total amount of work. That is the reason why in thermodynamics, you do not see delta W written anywhere, right? You do not see delta Q written anywhere. It is always either W or Q, right? It is always either W or Q. Similarly, when it comes to your internal energy, enthalpies, in your books, you always see something delta U written, delta H written, delta G written, delta S written, right? You do not see your U, H, G or something written, right? I believe it's clear. I believe it's clear to you. Right, people? All clear? All clear quickly in the chats? All clear quickly in the chats? Perfect. I hope you all are following everything with me. I hope you all are following every single thing with me. Perfect, people. Perfect. Now, let's talk about something called as introduction. Introduction to thermodynamic processes. Introduction to thermodynamic process. I'm not going to go into the details of thermodynamic processes now. I'll be going into the details of thermodynamic processes afterwards in some time. But right now, I'll just give you the overview of what a thermodynamic process is all about and what are the different types of these processes. Rest, in detail, we are going to discuss them after some time, after 2-3 hours maybe. After 2-3 hours maybe. So first of all, how do you exactly define a thermodynamic process? How do you exactly define a thermodynamic process? Try to understand carefully what this thermodynamic process exactly is all about. See guys, thermodynamic process is defined as the path followed. It is defined as the path followed to change. The path followed to change the state of the system. The path followed to change the state of the system. What does it mean? What does it mean? Try to understand it very carefully. Before making you understand all these things, do remember one more thing. Do remember one more thing. In our syllabus, we have to discuss the thermodynamic of ideal gases, basically. Basically, in our syllabus, we have to discuss the thermodynamics of ideal gases. So from now onwards, whenever I'll be using the term system, understand and imagine that you have taken ideal gas into the container, which is under thermodynamic investigation. Right? Do remember this particular thing, which is very important here. Whenever I'll be using the term system, imagine I have taken the ideal gas in the container, which is under investigation. Okay? Perfect. So, dear students, imagine this is the container. And in this particular container, I have taken the ideal gas. And this ideal gas is under thermodynamic investigation. So, this ideal gas is my system right now. Now, assume that the pressure of the ideal gas is P1, volume is V1, temperature is T1, moles are N1. Right? And I'm assuming this particular ideal gas, whose pressure is P1, volume is V1, temperature T1, moles N1. I'm telling you that this ideal gas is present at its initial state. This ideal gas is present at its initial state. Now, as I told you already, if you want to change the state of the system, what do we have to do? We have to change the values of the state parameters. And if by chance we change the value of minimum one state parameter, the state of the system automatically will change. For example, I'm changing the value of moles from N1 to N2. I'm changing the temperature from T1 to T2. I'm changing the volume from V1 to V2. But, for example, I'm not changing the pressure. Pressure I'm keeping P1 only. Tell me in the chats whether the state of the system has changed or not. Minimum, if one parameter is changed, the state of the system automatically changes. So I'll say this is, for example, the final state of the system. Did I change the state of the system? Yes. Did I change the state of the system? Yes. But if you analyze one thing, when I changed the state of the system, I did not let the pressure of the system to change. When I changed the state of the system, I did not let the pressure of the system to change. No doubt, I changed the state of the system, but I kept pressure of the system constant. Similarly, I could have changed the state of the system by keeping its volume constant. I could have changed the state of the system by keeping its temperature constant. Right? I could have changed the state of the system by keeping its pressure constant, by keeping its volume constant, even by keeping its temperature constant. So can I say I have got different paths available? I have got different paths available in order to change the state of the system. I can change the state of the system by keeping its pressure constant. This is one of the paths which I can follow. This is one more path which I can follow. This is one more path I can follow, right? I have got a lot of paths available by means of which I can change the state of the system. Now, among those paths which are available with us, that particular path which we follow to change the state of the system, that is something which you call as thermodynamic process. So basically, one of the process will be, I'll be changing the state of the system by keeping its pressure constant. That is one of the path. That is one of the thermodynamic process. I can change the state of the system by keeping its temperature constant. That is one more path. It's one more thermodynamic process. So basically, we have got a lot of thermodynamic processes which we have to discuss in detail. But the detailed discussion is not going to happen now. Detailed discussion is going to happen afterwards. Right now, I'm only giving you the overview of the things. Right? Right now, I'm only giving you the overview of the things. Yeah? Now, people, the different types of thermodynamic process. The first one is what you call as isochoric process. Isochoric process. Can you let me know what this isochoric process will be all about? So first of all, in case of isochoric processes, what happens? Tell me what happens. You will be changing the state of the system by keeping its volume constant. So whenever from now onwards, I'll say that the ideal gas is undergoing isochoric process. That means you are changing the state of that ideal gas, but at the same time, while changing the state of the ideal gas, you are making sure that volume of the gas does not change. Okay? Number one. In isochoric processes, volume of the system remains constant. If volume is constant, volume does not change. So delta V, change in volume has to be 0. Change in volume has to be 0, right? Change in volume has to be 0, absolutely. Perfect. Now people, understand one more thing here. If you remember, have you studied gaseous state ever? Tell me. Have you studied gaseous state ever? Have you studied the gas laws ever in your life? Boyle's law, Charles' law, Gay-Lussac's law, etc., etc. You would have, right? Tell me, whenever you have the ideal gas, whose moles and volume are kept constant, which law the gas follows? Which law the gas follows? Tell me just that. Whenever you will be having the ideal gas, whose moles and volume are kept constant, which law, which gas law it follows? Is it Boyle's law? Is it Charles' law? Is it Gay-Lussac's law? It follows the Gay-Lussac's law. And as per your Gay-Lussac's law is concerned, pressure of the gas is directly proportional to temperature of the gas in Kelvin, provided the moles and volume of the system is kept constant, right? Perfect. So the ideal gas which is undergoing isochoric process, it will be following this particular law. Or I can write it like this. P1 divided by T1 has to be equal to P2 divided by T2. This is the equation which the gas is going to follow currently, right? And at the same time, if I would want to draw a graph, between pressure and temperature, temperature of the gas in Kelvin, how the graph will look like. This is P is equal to KT. P is equal to KT. Y is equal to mx. Y is equal to mx is a straight line. Y is equal to mx is a straight line. So you'll draw the graph like this. It's a straight line like this. Okay. What do you call this particular curve as? This is called as isochore. This is called as isochore. Right? This is called as isochore. At the same time, if you want to plot a graph, between pressure and volume, since you have to represent that volume is constant, so the graph will be like this. You'll be calling this isochore because you are keeping the volume constant. You are not letting the volume of the gas to change, right? Correct? Imagine you have to draw a graph between volume and temperature in Kelvin. How will you represent isochore here? In isochore, volume has to be constant. So volume has to be constant. It has to be a straight line like this. So this graph over here represents isochore. I hope all these things are clear. So this was just the introduction of the isochoric process. All the other things we have to discuss in detail, right? All the other things we'll be discussing in detail. Perfect. This is just the overview of the things. So this was your isochoric process. Number two, if I talk about isobaric process, tell me what happens in isobaric processes. In the similar way, whatever we discussed about isochoric, same things we are going to discuss for isobaric as well. In case of isobaric, what happens? You will be changing the state of the system. You'll be changing the state of the gas, but you will make sure that pressure of the gas does not change. So pressure is kept constant. Change in pressure, delta P, has to be 0 here. Has to be 0. Now, which gas law is valid at constant pressure? That is Charles' law. And as per Charles' law is concerned, volume of the gas is directly proportional to temperature of the gas in Kelvin. Perfect. Provided moles and pressure are kept constant. Yeah. So the gas which is undergoing, the ideal gas which is undergoing isobaric process, it will be following this equation. V1 by T1 is equal to V2 divided by T2. It will be following this particular equation. Now, what kind of graphs can we plot? The first type of the graph which we can plot over here, that's for example going to be between pressure and volume. Since I have to show that pressure is constant, pressure is not changing. Pressure is not changing means a straight line like this. Pressure is not changing at all. I'll be calling this isobar. For example, I have to represent isobar on this particular curve. Volume versus temperature in Kelvin. You know, volume is directly proportional to temperature in Kelvin. So V will be equal to K into T. So Y is equal to mx format. Y is equal to mx means straight line passing through origin. So it has to be a straight line like this. Perfect. You'll be calling this as isobar as well. Right, people? Now, similarly, if you need to plot the isobar, on pressure versus temperature curve, if you want to plot the isobar on pressure versus temperature curve, you just have to represent one thing, that you are keeping the pressure constant, right? So this is your isobar here. This represents your isobar. Correct? Correct, people? Yeah? Yes, Insha, you can do that. I hope these basic things are clear to you. Now, similarly, the third process which we have to define, what is that? That is isothermal process. What is isothermal process all about? What is isothermal process all about? Quickly. When do we say that the system is undergoing isothermal process? People, whenever you change the state of the gas, whenever you change the state of the system, By keeping its temperature constant. By keeping its temperature constant. You'll be calling it as, you'll be saying that the system is undergoing isothermal process. So I would say delta T, change in temperature has to be 0, right? In isothermal processes, delta T will be 0. Now, can you let me know which gas law is applicable? Which gas law is applicable when the ideal gas is kept at constant temperature? If you remember, Boyle's law. And Boyle's law states that, pressure of the gas is inversely proportional to what? Volume of the gas, right? So the gas, the ideal gas, which is undergoing isothermal process, that has to follow this particular equation. Okay. And similarly, from this particular statement, I can write P1V1 has to be equal to P2V2. Perfect. This is the equation which will be used, right? If I want to plot a graph, if I want to plot some graph, the first graph, pressure versus volume, pressure versus volume. Let me know in the chats. Is pressure and volume directly proportional or inversely proportional? Pressure and volume here are inversely proportional. Whenever you want to plot a graph between two variables which are inversely proportional to each other, the nature of the curve is rectangular hyperbola. So it is the hyperbola like this, right? You call it as the isotherm, if you remember. You call it as the isotherm, correct? You call it as the isotherm. If you want to represent isotherm on volume versus temperature curve, how do you represent isotherm on volume versus temperature curve? It is just, you have to show that temperature is not changing. Temperature is not changing, matlab temperature is constant. So it has to be a straight line like this. So I would say this particular line represents your isotherm. For example, you are representing isotherm here, right? On pressure versus temperature curve. How do you represent the isotherm here? It is just, you have to show temperature is constant, right? So this particular line will be representing your isotherm. Perfect. Yeah. Right, people? Similarly, this is just the quick introduction of the processes. All the other things we have to discuss in detail, right? I am not teaching you these things in detail yet. Afterwards, we'll see that. All right. Then we have got the fourth process which we have to discuss in detail. What is that? That is adiabatic process. Adiabatic process. What do you know about adiabatic processes? Tell me that. What do you know about adiabatic processes? My dear students, whenever the system undergoes a change in state, but during the change in the system, if there is no heat exchange, if there is no heat exchange between the system and surroundings, you will say that the system is undergoing adiabatic process. So I'll categorically say, in case of adiabatic processes, dq has to be 0. dq has to be 0, right? Perfect. Point number 1. Point number 2. I'm writing one equation over here, that is PV raised power gamma is equal to constant. PV raised power gamma is equal to constant. And this equation I'll be calling as equation of state. You call this equation as the equation of state for a reversible it's called as equation of state for reversible adiabatic processes. What are reversible, irreversible? Again, you'll get the idea in some time, right? Just take a note of these things for now. Okay. Well, people, you can write this equation like this as well. P is equal to K divided by V raised power gamma, right? Okay. And for example, you have to plot a curve between pressure and volume in this particular case. Again, I'll say pressure and volume, they are inversely proportional. And whenever you have to plot a curve between two variables which are inversely proportional to each other, the nature of the curve is hyperbola. It's again a hyperbola, right? And I'll be calling this particular hyperbola as adiabat. Now, if you look carefully, this is hyperbola, even this is hyperbola. This represents isothermal process. This represents your adiabatic process. The point is, how do you differentiate them? Let me tell you one quick trick which you are going to remember. Let me tell you one quick trick which you'll be remembering here. For example, this is pressure on one side, volume on another side. Correct? Pressure on one side, volume on another side. I'm starting from here. I'm making two hyperbolas like this. These are the two hyperbolas which I made. And people, I'm keeping arrows towards right. I'm keeping arrows towards right. Okay? Both are hyperbolas. I have to identify which one is for isothermal, which one is for adiabatic. What do I do in this particular case? First thing, tell me whether the arrows are towards the right or left. Arrows are towards right. And towards right, volume is increasing. So both these graphs, they represent what? Both these graphs represent expansion. They represent expansion. Okay? Now, what you need to do, place your thumb at the common point. Place your thumb at the common point. Curl your fingers in the clockwise direction. Curl your fingers in the clockwise direction. That curve which touches your fingers first, that's always your isothermal. So this one is always your isothermal. The other one is going to be adiabatic. The other one is going to be adiabatic. I believe it's clear. I believe it's clear. I believe it's clear. Now, for example, the case can be different as well. The case can be different as well. Have a look over here. Let's say I'm plotting a graph between pressure and volume. The graphs which I'm plotting, imagine the graphs are starting from here. And these are your hyperbolas like this. These are your, for example, hyperbolas like this. First of all, look at the arrows. Look at the arrows. The arrows are towards left, and towards left, volume is decreasing. Decrease in the volume is something which you call as compression. So both these graphs, they represent compression here. Now, one of the hyperbolas will be isothermal and one will be adiabatic. Again, the similar thing. Place your thumb at the common point. Curl your fingers in the clockwise direction. That curve which touches your fingers first, that has to be isothermal. So this is your isothermal. This is your isothermal curve. And this is your adiabatic curve. I believe it's clear. I believe it's clear to everyone. I believe it's clear to everyone. Yes? Right, people? You can use the slope concept as well. Right? You can use the slope concept as well. You know, your slope of your adiabatic curves at a particular point is always greater than, right? Is gamma times basically slope of your isothermal one. I'm not going into that yet. We'll be discussing about that after some time. This is one quick rule which you'll be remembering. That's what I need here, nothing else. Now, the fifth process which we have to discuss in detail in the today's session, that's what you call a cyclic process. Right now, I'm just giving you the introduction of the things. I did not discuss them yet in detail. Again, I'm telling you the same thing. How do you define the cyclic process? What is a cyclic process? What is the cyclic process? Quickly. Cyclic process is the one in which system returns to its initial state. Cyclic process is the one in which system returns to its initial state after going through a lot of steps. After going through a lot of steps. For example, I'm making a graph like this. Let's say I'm plotting the graph between pressure and volume. For example, let's say I'm starting from this point A. Let's say I'm going from A towards B. I moved from A towards B. For example, I'm going from B towards C. Then from C, I'm again coming towards A. Can I say system is returning to its initial state after going through a lot of steps? 3 steps basically. But after 3 steps, the system is returning to its initial state. Whenever you see such kind of the case in which system returns to its initial state after going through a lot of steps, you say at that point of time, your system is undergoing a cyclic process. Now, if the system is returning to its initial state, I can say the initial state and final state of the system is same. This is the initial state as well as final state of the system. This is the initial state as well as final state of the system. Now you already know state function depends only on initial and final state. State function, be it any state function, internal energy, enthalpy or whatever, state function depends only on initial and final state. If the initial and final state is same, can I say the initial value of state function as well as final value of state function, that will be same, right? The initial value of state function and final value of state function will be the same, correct? So if I ask you, what is going to be the change in the value of state function for the system which undergoes cyclic process? Change means final minus initial. Final minus initial has to be 0. So do remember this particular point, which is very important. Change in the value of a state function for any cyclic process. Change in the value of a state function for any cyclic process, that's always 0. For example, delta U for this cyclic process, it will be 0. Delta H for this cyclic process will be 0, right? Delta G for this cyclic process will be 0. So do remember one simple statement from now onwards, people. Change in the value of a state function for any cyclic process is always 0. This is one important point which you have to remember. Okay, is this clear? Is this clear to everyone? Quickly in the chats. Quickly in the chats with the fire emojis, people. Everyone. And you know everyone means? And you know everyone means? Yeah. Everyone means what? Yeah, everyone means everyone, yeah? And the ones who have not liked the session yet, what are they supposed to do? Correct. All right, guys. Now let's talk about a term called as heat. Heat is represented by Q. You can represent it either with capital Q or small q. What is heat? What is heat? Just a second, guys. I saw something. Okay. All right. So have you discussed heat yet? I mean, have you discussed heat till now? Yeah? Have you discussed heat ever? So try to understand what this heat exactly is all about. Number one, how do we exactly define heat? How do you exactly define heat? Heat is basically defined as a mode of transfer of energy. The mode of transfer of energy between the system and surroundings. Heat is defined as the mode of transfer of energy between system and surroundings. What it means, you'll get the idea in some time. Point number one. Point number two, heat always flows. Heat always flows due to temperature difference. Due to temperature difference. Heat always flows from higher temperature to lower temperature. Higher temperature to lower temperature. Higher temperature to lower temperature. And already we have discussed heat. It is the example of path function. Heat is the example of path function. Try to understand these things, people. These are basic things. These are basic things here. See, first of all, whenever energy has to be exchanged between system and surroundings, whenever energy has to be exchanged between system and surroundings, what does that mean? That means if energy has to go out of the system, or if the energy has to enter into the system. That is something which you call as exchange of energy between system and surroundings. Whenever energy has to be exchanged between system and surroundings, there are many ways by means of which system and surrounding can exchange the energy. And one of the mode through which energy can be exchanged between system and surroundings, that is heat. Heat is the mode of transfer of energy, the mode of exchange of energy between system and surroundings. Right? So do remember, the exchange of energy between system and surroundings can happen via heat. So heat is just the mode of transfer of energy between system and surroundings. Yeah? Is it clear? Is it clear to everyone? Heat is just the mode of transfer of energy. Whenever energy has to go out of the system, or whenever energy has to come inside the system, it can happen via heat. So heat is just the mode of transfer of energy between system and surroundings. And you already know, heat always flows from higher temperature to lower temperature. Heat flows due to temperature difference. It is evident. For example, you have got this object. You have got one more object. This is at 100 Kelvin. This is at 1000 Kelvin. This is at 1000 Kelvin. So is there temperature difference between these objects? Yes. If you bring them in contact, automatically, spontaneously, you will see heat flowing from higher temperature to lower temperature. Right? So what is heat? Heat is the mode of transfer of energy. Heat flows due to the temperature difference. It flows from the body at higher temperature to lower temperature. Now, there are two things which you have to remember that is really very important, right? And I'll be using it everywhere. Imagine you have got ideal gas in the container, and this ideal gas I'm calling a system, right? So this particular system will be at certain temperature. This particular system will be at certain temperature, okay? Even surroundings will be also at certain temperature. Surrounding will be also at certain temperature. Now, first thing, if temperature of surrounding is more than that of temperature of system, if temperature of surrounding is more than that of temperature of system, can I say there is temperature difference between system and surroundings? Yes, there is a temperature difference between system and surroundings. And whenever there is temperature difference, heat will always flow from higher temperature to lower temperature. So higher to lower. Right now, surrounding is at higher. So it is higher to lower. It is higher to lower. So heat will flow from surrounding to system. If heat is flowing from surrounding to system, what does that mean? That means system absorbs heat. That means system absorbs heat. And at the same time, do remember, whenever system absorbs heat, as per sign conventions, the value of Q is taken to be positive. This is one very important statement which I would want every one of you to remember from now onwards. Point number one. Point number two. If by chance temperature of system is more than that of temperature of surroundings, if system is at higher temperature, surrounding is at lower temperature, again there is a temperature difference. If there is temperature difference, heat flows from higher temperature to lower. So heat will go from system to surroundings. If heat is moving from system to surroundings, what does that mean? That means system releases. That means system right now will be releasing heat. System releases heat. And whenever system releases heat, as per sign conventions, Q value is taken to be negative. So whenever system releases heat, Q value is taken to be negative. These are the two things which I would want every one of you to remember from now onwards. Whenever heat is absorbed by the system, Q value is taken to be positive. Whenever heat is released by the system, Q value is taken to be negative. As simple as that. Nothing else you have to remember for now. Okay? Perfect, people? Perfect? I believe it's clear to everyone. Now, there is something called as work. Have you discussed this term work ever, which is represented by W? So first thing, how do you define the term work? How do you define work? Work is again defined as, it is again defined as the mode of transfer of energy. Work is again defined as the mode of transfer of energy between system and surroundings. Whenever energy has to move from system to surroundings or from surrounding to system, this exchange of energy between system and surroundings can happen via work as well. So work is nothing but the mode of transfer of energy between system and surroundings. Okay? Perfect. Number 2, work. It is again the example of what? It is again the example of path function. Now let's try to understand it a bit more in detail. I'm not going to derive any expression here. I'll be letting you only those points which are used when it comes to our preparation NEET, right? Not into the details, not into the derivations, etc., etc. No, I'll give you the expressions and I'll show you how to utilize those expressions in the questions. Try to understand. Few important things I'm going to tell you. Few very important things I'm going to tell you. My dear students, imagine that this is one container which we have. This is the piston right here. This piston, it can move outwards as well as inwards. The piston can move outwards as well as inwards. Imagine you have taken an ideal gas in this particular container. This is the ideal gas in the container. Now, people, if I ask you, how many pressures will be experienced by this piston over here? You will say, these gas molecules which are inside the container, they are colliding with the piston. So in this particular direction, what you'll observe? You'll observe pressure of gas. You'll observe pressure of gas. Now, from outside you have atmosphere, and those atmospheric gases will be also colliding from outside. So from here, I'll be calling that pressure as P external. So on the piston, 2 pressures are exerted. One by the inside gas, one from the atmospheric side, right? My dear students, when the piston is at this particular point A, I'm assuming the volume of the container is V. I'm assuming the volume of the container is, for example, V1. Okay? And do remember, ideal gas always occupies the volume of container in which it is kept. This is the ideal gas, right? It occupies the volume of container in which it is kept. If the volume of container right now is V1, that means I would say that the volume of the gas right now is V1. As simple as that. Okay? Now, here we have got certain cases which are going to arise. Case number 1. Case number 1. If by chance P gas will be greater than P external. If by chance P gas is greater than P external. If P gas is more, what will happen? The piston will start going outwards. The piston will start going outwards. Right? And will stop finally at some position. Imagine the piston has stopped here at point B. When the piston has stopped at point B, the volume of the container has increased, and I would say volume of the gas has increased. Let's say the final volume of the gas is V2. Okay. So if P gas is greater than P external, can I say V2 is greater than V1? V2 is greater than V1. Can I say increase in the volume of the system is happening? Can I say right now increase in the volume of the system is happening? And whenever you see increase in the volume of the system happening, you call that as expansion. And whenever there is expansion, we always say that work is done by the system. Work is done by the system. Work is done by the system. And whenever work is done by the system, as per sign conventions, the value of W, the sign of W in chemistry is taken to be negative. In physics, you take it positive. In physics, you take it positive. Okay? If P gas is greater than P external, volume of the container will increase. Volume of the gas is increasing. Increase in the volume of the gas is something which you call as expansion. Whenever there is expansion, work is done by the system. And whenever work is done by the system, the value of W is taken to be negative. Okay? Right? Perfect. Point number one. Point number two. Point number two. Imagine if P external was greater than P gas. Imagine if P external was greater than P gas, what would have happened? The piston would have gone inwards. And if the piston would have gone inwards, I would have said V2 is less than V1. And decrease in the volume of the system. Decrease in the volume of the system is what you call as compression. Decrease in the volume of the system is what you call as compression. Whenever there is compression, we always say work is done on the system. We always say work is done on the system. And whenever work is done on the system, the value of W is taken to be positive in chemistry. The value of W is taken to be positive in chemistry. Point number two. Point number three. Imagine if P external was equal to P gas. Imagine if P external was equal to P gas, there would have been no change in volume. There would have been no change in volume. That means volume of the system was constant, right? Volume of the system was constant. If the piston was not moving at all, that means there was no exchange of energy between system and surroundings in the form of work, right? So in short, whenever you see piston moving either outwards or inwards, except in case of free expansion, which I'll tell you afterwards, leave that aside. Right now, remember it like this. Whenever you see piston moving either outwards or inwards, remember, there is exchange of energy happening between system and surroundings in the form of work, except in case of free expansion. I believe this is clear. Now the point is, how do we calculate this work? One general expression I'm giving you, I'm not deriving it. I want you guys to remember it directly. How do you calculate work in general? Work is equal to minus integral P external dV under the limits initial volume to final volume. This is the general expression by means of which you can calculate work. Point number one. Point number two. In some time, I'll let you know that we have got two types of processes. Right now, just remember the things which I'm telling you. You'll get their explanation in some time. In general, we have got two types of processes. One is called as a reversible process. One is called as irreversible process. In case of your reversible processes, P gas is almost equal to P external. And in case of irreversible processes, P external is constant. This is something which I'll discuss with you in some time. But for now, remember it. We have got two types of processes, reversible, irreversible. In reversible process, P gas, P external are almost equal. If P gas and P external are almost equal in reversible processes, then how do we calculate work done in reversible process? It's going to be minus integral V1 to V2. Instead of P external, I'll write P gas multiplied by dV. This is the expression which we shall be using to calculate work done in case of reversible processes. What are reversible processes? Wait for that. Okay. In case of irreversible processes, P external is constant. If P external is constant, take it out of the integral. If P external goes out of the integral, integral of dV is V, upper limit, lower limit, V2 minus V1. So I would get the expression like this. Work done in case of irreversible processes will be directly minus P external, V2 minus V1. That will be written as delta V. So these are the two general expressions by means of which we can calculate work. One in reversible processes and another one in irreversible processes. Is this clear to everyone? Let me know quickly in the chats if all these things are absolutely clear to you. Quickly, people, quickly. Quickly. What is this heat and work? These are modes of transfer of energy. So can I say the unit of heat and work, the units of heat and work are going to be same as the units of energy? Can I say the units of heat and work are going to be same as the units of energy? And what are the units of energy? SI unit of energy is joule. CGS unit of energy is erg. 1 joule is 10 raised power 7 erg. 1 joule is 10 raised power 7 erg. What are the other units of energy which we use? The other units are ATM liter. This is one of the unit of energy. Bar liter, one more unit of energy. Calories, one more unit of energy. And you just have to remember their conversion. You just have to remember their conversion. This is important. 1 ATM liter is equal to 101.3 joules. 1 bar liter is equal to 100 joules. 1 calorie is equal to 4.2 joules. 1 ATM liter is equal to 24.2 joules. These points are really important because I'll be using these points when I'll be doing the questions based on first law of thermodynamics. Say it with me. SI unit of energy is joule. CGS unit is erg. 1 joule is 10 raised power 7 erg. Right? 1 ATM liter is equal to 101.3 joules. 1 bar liter is equal to 100 joules. Right? And at the end, 1 calorie is equal to 4.2 joules and 1 ATM liter is equal to 24.2 calories. These are the things which I would want you guys to remember. Okay. Number 1. Number 2. Number 2. Number 2. I'll give you one simplest question. One simplest question. Calculate the one simplest question. Calculate the work done in joules. In joules. When an ideal gas is undergoing, when an ideal gas is undergoing, or let me write it, when an ideal gas undergoes, when the ideal gas undergoes the change in volume, the change in volume from 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure. Against a constant external pressure. Against a constant external pressure of 10 raised power 5 Newton per meter square. Can you give it a try? You should be able to solve this question, people. It's a very simple question. Quickly in the chats. Quickly in the chats, everyone. If you look at the question carefully, you have got an ideal gas in the container, which is undergoing a change in volume. What is the initial volume of the gas as per the question? Initial volume of the gas is 10 raised power minus 3 meter cube. What is the final volume of the gas? 10 raised power minus 1 meter cube. Now look at these two values. I'll say increase in the volume is happening. Increase in the volume of the gas is happening. Increase in the volume is something which you call as expansion. Whenever there is expansion, W value has to be negative. So your answer has to be negative basically. Right? Okay. Now people, expansion of the gas, expansion in volume is happening against a constant external pressure of how much? 10 raised power 5 Newton per meter square. Few minutes back, only I told you. We have got two types of processes, reversible, irreversible. In irreversible process, external pressure is constant. Here in this question, expansion is happening against constant external pressure. So, this particular process, is it reversible or irreversible? It is irreversible in nature. If it is irreversible in nature, how do we calculate work done in irreversible processes? It is simple. Minus P external delta V, which is final volume minus initial volume. So W irreversible has to be equal minus, what is P external? 10 raised per 5 Newton per meter square. What is V2? 10 raised per minus 1 meter cube. V1, 10 raised per minus 3 meter cube. So it has to be 10 raised per 5 as such. Just take any of these terms out. If I take 10 raised per minus 1 out, it has to be 1 minus 10 raised per minus 3 divided by 10 raised per minus 1. I can write it something like this. I'm just showing you the calculation here. I'm just showing you the calculation here. Now, W irreversible will be equal. This will be 10 raised per 4. 10 raised per 4. It's going to be 1 minus 10 raised per, just a second, what did I take common? I took 10 raised per minus 1 as common. This is 1 minus this divided by this. Okay. So this is 1 minus 10 raised per minus 2. Perfect. Or guys, wait, why am I doing this much of complications and all? Let's do one thing. Which one is the smaller term among the two? It is 10 raised per minus 3. Smaller term is 10 raised per minus 3. Take that smaller term common. This is going to be 10 raised per minus 3 divided by 10, divided by this, minus 1. Okay, I hope now it's clear. So, work done in this irreversible process will be equal. This multiplied by this will be 10 raised per 2. 10 raised per minus 3 will come up. It becomes 10 raised per 2, which is 100. 100 minus 1 is 99. So, the final answer is minus 99 multiplied by 10 raised per 2. Now, if I ask you what are going to be the units, what are going to be its units? See, you took all these parameters as per SI system. You used all the parameters as per SI system. So, the value of W will also come as per SI system. So, it has to be joules. It has to be joules. It has to be joules. Right? It has to be joules. Now, one more question I'm giving you, and you will let me know the answer. You will let me know the answer. Just a second, people. Just a second. Just a second. That's an asked question too, and I want you guys to give that question a try. Where is that? Where is that? Okay, here it is. Here it is. Can you give this question a try? Can you give this question a try? Can you give this question a try quickly? Quickly in the chats, people. Quickly in the chats. Look at the question very carefully. A gas expands against a variable pressure. In the question, they are mentioning the variable pressure. They are not mentioning the constant pressure. So if they are mentioning the variable pressure, so which process is it going to be? Is it going to be reversible or irreversible? Absolutely, it's going to be a reversible process. Correct? Yes. And in case of reversible processes, how do we calculate work? In case of reversible processes, how do we calculate work? In case of reversible processes, how do we calculate work? As I've told you already, work done in reversible process is equal to minus integral V1 to V2. It has to be P gas multiplied by dV. Now, as per the equation, there are few parameters which are given. Initial volume, final volume. During the expansion, the volume is changing from 1 liter to 10 liter. So initial volume is 1 liter, final volume is 10 liters. Right? What is P? As per the equation, P is nothing, that is 20 divided by V. 20 divided by V multiplied by dV. The question is done and dusted, right, people? So how you are going to solve it? This is going to be minus 20 and integral of 1 by V is minus 1 upon V square, right? It's going to be minus 1 upon V square. Now, upper limit, lower limit, you'll give here. You'll get the answer in ATM liter. You'll get the answer in ATM liter. Why is that? Because you have taken pressure in ATM, volume in liters. Pressure in ATM, volume in liters. So you'll get the value of W in ATM liter, right? Perfect. You'll get the value of W in ATM liter. The equation is still here only. The equation is still here only, right? I just want you to calculate work done. I just want you to calculate work done, nothing else. Right? Right, people? Tausif is telling a very nice thing. See, Tausif, I'll make you understand what you're talking about. So first of all, I hope this question you can do, right? You'll get the value of W in ATM liter. And once you get the value of W in ATM liter, then you can convert it in joules. Okay? Because 1 ATM liter is equal to 101.3 joules. Now see, there's a guy in the chats, namely Tausif. So see, guys, there are two things basically. I'm writing two statements. The first statement which I'm writing, well, I'm going to discuss it afterwards when I'll be doing the process in detail. But right now, just understand. See, I'm writing if delta T is equal to 0, the process must be isothermal. This is one of the statement which I'm writing. The process must be isothermal. The second statement which I'm writing. For an isothermal process, delta T is equal to 0. Which one is the appropriate statement among the two? What do you think? This one is the appropriate statement. This one can be or cannot be true. Can be or cannot be true. Why is that? For that, you'll have to wait till I start the isothermal process. Okay? Till I start the isothermal process. Perfect? Or maybe you can give it a thought till then. Similarly, I can write two more statements. Two more statements. Okay? First statement. If delta T is 0, the process must be isothermal. Second statement. If dt is equal to 0, the process must be isothermal. These are again two statements, out of which only one is correct. One is the most appropriate. Out of these two statements also, one is most appropriate. That is the second one. You can give it a thought till I start the isothermal processes. Right? Okay? You can give it a thought till I start the isothermal process. Perfect? All right, let's move on now. So we were basically talking about work, and we were discussing how do we calculate work in reversible and irreversible processes. Now, my dear students, look at this particular question. Rasik, just wait. Let me teach you reversible process, then your all these doubts, etc., they'll be clear. Okay? Right? Just wait for some time. Let me teach the reversible. In reversible, P gas and P external, they are not exactly equal. They are almost equal. There is some variation. That is very negligible, small variation. Just wait for some time. Solve this particular question. At STP, following reactions are given. Identify in which reactions work is done by the gas and in which reactions work is done on the gas. What do you think? In the first case, what do you think? See, if you look at the reaction number 1, it is 4 times NH3 gas plus 7 times O2 gas. It gives 4 times NO2 gas plus 6 times H2O gas. Right? As per the question is concerned, the reaction is carried out at STP. That means this particular process is carried out at constant pressure temperature. I believe you all would have studied ideal gas equation once in your life. PV is equal to nRT. If pressure and temperature is constant, R value is already constant. Can I say volume is directly proportional to moles? Absolutely. Volume is directly proportional to moles. Correct? So, if moles will be decreasing, volume will be decreasing. If moles will be increasing, volume will be increasing. Look at this particular reaction. Every reactant and product is in gaseous state. Every reactant and product is in gaseous state. Now tell me one thing. How many gaseous moles do we have on the reactant side? 4 plus 7. We have got 11 gaseous moles on the reactant side. How many gaseous moles are there on product side? 4 plus 6. 10 gaseous moles on the product side. So when this process is happening, are the moles increasing or decreasing? The moles are decreasing. The moles are decreasing. Moles are decreasing. If moles are decreasing, volume of the system will be decreasing. Decrease in the volume of the system is what you call as compression. Decrease in the volume of the system is what you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W value is taken to be positive in chemistry. So in the first case, work is done on the system and W value is positive. Okay, perfect. This is your first question. Second question. You are given with a reaction, carbon monoxide gas plus 2 times H2 gas. It gives what? It gives CH3OH liquid. This is the reaction which we have. Okay. Now, if you analyze carefully, all the reactants products, they are not in gaseous state. All the reactants products, they are not in gaseous state. Yeah. Your reactants are in gaseous state and the product is in liquid state. So basically, your gases are getting converted into liquid, right? Conversion of gas into liquid is happening. If conversion of gas into liquid is happening, what does that mean? Does that mean increase in the volume or decrease in the volume? Conversion of gas into liquid is happening. Does that mean increase in volume or decrease in volume? That's called as decrease in the volume. Decrease in the volume is something which you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W value in chemistry is taken to be positive. Clear? Look at the third case, people. Here you might do a mistake. And see what kind of mistake you might do. You have got H2O solid giving H2O liquid. Perfect. H2O solid basically means ice. This is your liquid water. So normally, if you think normally, ice is getting converted into liquid. And you know, when solid gets converted into liquid, expansion happens. Expansion of volume happens, right? When solid gets converted into liquid. In solid, molecules are packed closely. In liquid, molecules are comparatively far. In gases, molecules are far apart, right? But, if you think under those parameters in this particular case, you'll mark this question wrong. If you talk about ice, you would have studied in your chemical bonding, ice has got a cage-like structure, special structure. Cage-like structure due to hydrogen bonding, due to which volume of ice will be more here and volume of liquid will be less here. Volume of liquid water will be less here, right? So from more volume to less volume, decrease in the volume. Decrease in the volume is what you call as compression. Whenever there is compression, work is done on the system. And whenever work is done on the system, W is positive as per sign conventions in chemistry. Now, this is solid, this is gas. And you know, when solid gets converted into gas, there'll be expansion always, right? Expansion means work is done by the system. And whenever work is done by the system, W value as per sign convention will be taken as negative, right? I believe you can easily solve the questions based on work, right? Yes. Is it clear to everyone? Quickly, people. Quickly. I'll be giving you the break after 20 minutes. Okay? After 20 to 30 minutes, I'll be giving the break. We'll take a break after 30 minutes. So, let me know if all the things are clear till here. I hope you can easily do the questions based on work. Yeah? In reversible processes, W reversible is equal to minus integral V1 to V2, P gas multiplied by dV. Yeah? Right? And in case of irreversible processes, W Irreversible is equal to minus P external multiplied by delta V. V2 minus V1. Right, people? Okay. And few students were asking about these statements. These statements will be discussed in detail after some time when I'll be introducing your different types of processes in detail. Yeah? Perfect. Now let's move on to a few more things. I believe every one of you would have come across this particular term, heat capacity, which is represented by C. How do you exactly define the term heat capacity? How do you define it? How do you define it? How do you define it? If I first of all talk about the definition of heat capacity, it is defined as the amount of heat required to raise the temperature. The amount of heat required to raise the temperature. Of a given mass of substance. By 1 degree. The amount of heat which is required. The amount of heat which is required to raise the temperature of a given mass of the substance by 1 degree. Now, what does it mean exactly? Try to understand, people. Imagine that you have got a system. Imagine that this one object. This object is under investigation, for example. This object is under thermodynamic investigation. So this object is my system, for example. Okay. Now, my dear students, try to understand one simple thing. Imagine that I am supplying a small amount of heat to this system. Imagine that I'm supplying small amount of heat dQ to the system, due to which its temperature changes by dT units. I'm giving small amount of heat to the system, due to which its temperature is changing. And if I'm giving some heat, if I'm supplying the heat, that means its temperature will be increasing. Right? Now, guys, try to understand. Can I write the same thing in the form of a statement? Can I say, in order to increase the temperature by dT units, heat supplied was equal to dQ? Yes, heat supplied was equal to dQ. Can I say, in order to increase the temperature by 1 unit, or you can say 1 degree, can I say heat supplied will be equal to, use the unitary method, heat supplied will be equal to dQ upon dt? Yes. So can I say, this particular term, it is the amount of heat supplied to raise the temperature of the given mass of the substance by 1 degree, and the amount of heat which is required to raise the temperature of a given mass of the substance by 1 degree. What do you call that as? You call that as heat capacity. So you got the result by means of which you can calculate the heat capacity. Heat capacity of the system is always equal to dQ upon dt. It is equal to dQ upon dt. Point number 1. Point number 2. If I write the same expression like this, dQ is equal to C dt, does not make a difference. I just cross multiplied, nothing else. Okay, I just cross multiplied. Now, my dear students, imagine the object which you have taken over here. Imagine its heat capacity is C. Now, I want to change the temperature of this particular object from T1 to T2. I'm asking you, how much heat is exchanged between system and surroundings? Or let me make a little clear to you. Let me make it a bit easy for you. For example, I want to increase the temperature of this system from T1 to T2. For that purpose, how much heat I have to supply. How much heat I have to supply. That's what I want to calculate. How you approach those sort of questions. You'll be simply integrating here. And integration is done with respect to temperature. Temperature is changing from T1 to T2. And integral of dq is nothing that's q, right? If c is constant, comes out. Integral of dt is t, upper limit, lower limit. So it has to be T2 minus T1. It has to be T2 minus T1. So you got one very, very, very important result, which you will remember from now onwards. Q is equal to C, T2 minus T1 is delta T. What is meant by this particular equation, and when are we going to use it? When are we going to use it? Remember, people, whenever you will find a question in which a system is given to you, whose heat capacity will be given to you, and you would have to change its temperature from T1 to T2, and they are asking you to calculate the heat exchanged between system and surroundings. Heat exchange means heat absorbed or released by the system, right? Heat exchange means heat absorbed or released by the system. Whenever they'll ask you heat exchanged or heat absorbed by the system or heat released by the system, you'll be using this particular expression, right? I'll show you the questions based on this expression in some time. But before that, if I ask you what are going to be the units of heat capacity, what are going to be the units of heat capacity? C is equal to dq upon dt. In the numerator, it's heat. In the denominator, it's temperature. So it's one of the unit can be joules per Kelvin. It's one of the unit can be joules per degree centigrade. It's one of the unit can be calories per Kelvin, etc., etc. Right? These are the different units of it. Yeah? Right, people? I hope this is clear. And at the same time, if you remember, in the beginning only I've told you heat capacity. Is it going to be extensive or intensive? It is going to be extensive in nature. Right? Now you can relate it as well. It is going to be extensive in nature. Right? It is going to be extensive in nature. Perfect. Perfect, guys. Yeah. Guys, now if you want to relate it, if you don't want to remember this formula, if you want to relate it, if you want to use your common sense, you can do that as well. Now see how you'll understand it. For example, the heat capacity of this object is 5 joules per Kelvin. 5 joules per Kelvin, right? Or you can say 5 joules per degree centigrade, one of the same thing. Okay, let's say heat capacity of this object is 5 joules per Kelvin. I want to raise the temperature of this object. I want to raise the temperature of this object from 50 degrees centigrade to 100 degrees centigrade. Or let's say from 50 degrees centigrade to 60 degrees centigrade. I want to raise the temperature, and I'm asking you how much heat I have to supply. How much heat I have to supply. Forget this formula. Use the common sense. Heat capacity is 5 joules per degree centigrade. That means in order to increase the temperature by 1 degree, how much heat has to be supplied? 5 joules of heat has to be supplied. Now, as per the current scenario, do we have to increase the temperature by 1 degree? No. I have to increase the temperature from 50 to 60. That means I have to increase the temperature by 10 degree. When you were increasing the temperature by 1 degree, this much heat has to be supplied. So when you are increasing the temperature by 10 degree, how much heat is supplied? 5 multiplied by 10. The value comes out to 50 joules. So that means in order to raise the temperature from 50 degree to 60 degree, how much heat has to be supplied? 50 joules. Correct? Right? Right, people? You can use the same formula. I was supposed to get the value of Q. If you use the same formula, Q is equal to C. C is 5 delta T, change in temperature, final minus initial, multiplied by 10, the value would have come as 50 joules as well. The choice is all yours, whatever you want to use. And do that. Okay? This is just the common sense. I hope this particular concept is clear. Now, guys, there is something called as molar heat capacity. Or let me use the term specific heat capacity. There is something called as specific heat capacity. Specific heat capacity, I'm representing with small s. What is the specific heat capacity all about? What is the specific heat capacity all about? In simple terminologies, I'm writing. I'm not going into the details now. Specific heat capacity, it is defined as, specific heat capacity is defined as heat capacity per unit mass of the system. Per unit mass of the system, right? Now already we know C is equal to dq upon dt. So it becomes dq upon m dt, right? So your specific heat capacity S is equal to dq upon m dt. Perfect. You can make whatever units you want to make. It is just you have to remember one thing. In the numerator, it's heat, energy, for example, joules. In the denominator, it's mass and temperature, right? You can make whatever units you want to make. Perfect. Now people, here you can say dq is equal to ms dt. Now the same procedure, if you integrate under the limits t1 to t2, here you'll get q is equal to ms. Integral of dt is t, upper limit, lower limit, so it is t2 minus t1, which is delta t. Perfect. So q is equal to ms delta t. Q is equal to ms delta t. Q is equal to ms delta t, right? Perfect. When do we use this expression? Before making you understand when do we use this expression, something which I want to tell you further. Specific heat capacity. It is defined as heat capacity per unit mole. Remember I told you, extensive property when expressed per unit mole becomes what? Becomes intensive. So it is the example of which property? It is the intensive property. It is the example of intensive property. It is the example of intensive property. Yeah? Clear, people? Clear? Is it clear? Now, when do we use this particular expression? Imagine a system is given to us whose specific heat capacity is given to us. We want to increase the temperature of this system from T1 to T2. We want to change its temperature from T1 to T2. And they are asking us how much heat is supplied to increase the temperature of this object from T1 to T2. Which expression you'll use? You'll use this particular expression. Q is equal to mass of this object will be given. Specific heat capacity is given. T1, T2, you know. So use this expression, get the value of Q, nothing else. Yeah? Perfect. Similarly, there is one more. Similarly, there is one more term. That is molar heat capacity. That is molar heat capacity. And molar heat capacity is represented with what? Cm. How do you define the term molar heat capacity? How do you define it? How do you define it? In the similar way, molar heat capacity is nothing. It is just heat capacity per unit mole. And heat capacity already we know that is dq upon dt. So it becomes dq upon n dt. So you can make its units on your own. Okay. Now I can say dq is nothing, that is ncm dt. Right? I'll be integrating here also with under the limits t1 to t2. So it becomes q is equal to, if n is constant, cm is constant, so ncm comes out. Integral of dt is t, upper limit, lower limit. So it has to be t2 minus t1. So in short, you can represent it as q is equal to ncm delta t. ncm delta t. Now the point is cm. Cm. Is it going to be extensive or intensive? Cm is intensive property. Molar heat capacity is intensive. Yeah? It is intensive in nature. When do we use this particular expression? When do we use? I'm using the term when do we use. Imagine you have got n moles of ideal gas. Imagine you have got n moles of ideal gas whose molar heat capacity is given to us. Whose molar heat capacity is given to us. I want to increase the temperature of this gas, for example, from T1 to T2. How much heat has to be supplied to increase the temperature of this gas from T1 to T2? I'll be using this particular expression. I'll be using this particular expression. Okay. So in short, if I summarize all this, and if I write something like this, heat exchange. What is meant by heat exchange? Heat exchange means the amount of heat absorbed or released by the system. The amount of heat absorbed or released by the system. In some questions, they'll directly ask you, calculate the heat exchange between system surroundings. In some questions, they'll ask you, calculate the heat absorbed by the system. In some question, they'll ask you, calculate the heat released by the system. Whenever these questions are asked, whenever you are supposed to calculate the heat exchanged between system and surroundings, the amount of heat absorbed or released by the system, you have to use few expressions. Number one, if heat capacity of the system is given, then Q you will calculate like this. Q will be C delta T. Okay. If, for example, in the question they'll give you the value of specific heat capacity. If specific heat capacity of the system is given, then Q you will write as Ms delta T. Right? Now, at the same time, if in the question they give you the molar heat capacity, if they give you the molar heat capacity of the system, then Q has to be equal to NCM delta T. NCM delta T. Now, this can be further divided into two categories. If in the question they mention calculate the heat absorbed at constant volume, or calculate the heat absorbed or released by the system at constant pressure. They can ask you, calculate the heat absorbed or released by the system at constant volume or at constant pressure. Just one thing. Instead of CM, you'll write CV or CMV. Choice is all yours. Here, instead of CM, you'll write CP. And your equation becomes what? It becomes Q, but now I'll write QV is equal to N CV delta T. This is one of the finest equations in thermodynamics, right? Similarly, QP has to be equal to N, it has to be CP, and it has to be delta T. Now, people, what is the meaning of these two equations? What is the meaning of these two equations? These are really very important. This equation means heat absorbed or released. Heat absorbed or released by the system, which is kept at constant volume. This question is asked directly. Calculate the heat absorbed or released at constant volume. Or they can say, calculate the heat exchanged between system and surroundings at constant volume. Or in some questions, they might ask you, calculate the heat absorbed or released by the system, but this time at constant pressure. Is this clear? These are going to be two important questions, people. These are going to be two important questions. Heat absorbed, released by the system at constant pressure. Heat absorbed, released by the system at constant volume. These two. Okay? Remember these expressions. These are very important. Remember these expressions. These are very important. These are some ways by means of which we can calculate the amount of heat absorbed or released by the gas. Okay? If heat capacity is given or specific heat capacity is given, molar heat capacity at constant volume, constant pressure is given, accordingly, you'll have to use the results. Is it clear? Is it clear, people? Now, there are a few more results which I'm pretty much sure you already know. What are those? You must be knowing that for 1 mole of ideal gas. Tell me in the chats. Do you know this? For 1 mole of ideal gas, Cp minus Cv is R. For 1 mole of ideal gas, Cp minus Cv is R. Similarly, for n moles of ideal gas, Cp minus Cv is Nr. You must be knowing about these results. These results you would have studied in physics as well, right? Similarly, gamma, Poisson's ratio, that is the ratio of Cp and Cv, right? Perfect. Since Cp minus Cv is R, that means R is a positive number. Perfect. So Cp has to be greater than Cv. If Cp is greater than Cv, gamma value will be greater than 1. Gamma value will be greater than 1. Again, this result I believe you would have studied already, right? Gamma is equal to Cp divided by Cv. I hope you remember. Gamma is equal to Cp divided by Cv. Similarly, one more result, I'm not giving its derivation. Cv is equal to R divided by gamma minus 1. This you are going to remember directly. This you'll be remembering directly. Okay? This you'll be remembering directly. Similarly, guys, imagine that you have got a mixture. You have got a mixture containing two chemically non-reacting gases. This is gas 1 and gas 2. Imagine in the container you have got two chemically non-reacting gases, gas 1 and gas 2. I've got its N1 moles, N2 moles. Its molar heat capacity at constant volume is C1. Its molar heat capacity at constant volume is CV2. Similarly, molar heat capacity at constant pressure is CP1. Molar heat capacity at constant pressure is CP2 for these two gases. For these two gases. I've got two chemically non-reacting gases. Whose moles are given. Their molar heat capacities at constant pressures as well as constant volumes are given. Now, sometimes they'll ask you, how do we calculate the CV for the mixture of gas? How do you calculate CV for the mixture of gas? Which is going to be equal to N1 CV1 plus N2 CV2 divided by what? Divided by N1 plus N2. General result which you can remember to calculate CV for the mixture. Sometimes they'll ask you calculate CP for the mixture, and CP for the mixture is simple. N1 CP1 plus N2 CP2 divided by what? Divided by N1 plus N2. This is the result which you will remember directly to calculate CP for the mixture. Right? Right, people? So you have to remember them. Similarly, if by chance they ask you, calculate the gamma for the mixture. Gamma for the mixture will be simple. The division of CP mixture to that of CV mixture. Right? All these things I'll be utilizing in the questions in some time. All these things I'll be utilizing in the questions in some time. Okay? Right, people? Right. Now, one more table, and after that, I'm going to give you the break. And after the break, we'll shift towards problems, numericals, and important concepts. One table I'm giving you. And table is pretty much simple. Here I'm writing type of the gas. Here I'm writing type of the gas. Here I'm writing CV for the gas. Here I'm writing CP for the gas. And here I'm writing gamma for the gas. Okay? Now, if you remember, for the monoatomic gas, like helium is monoatomic, neon is monoatomic, argon is monoatomic. For monoatomic gas, what is the value of CV? This you should remember directly from now onwards. CV for a monoatomic gas is 3 by 2R. CP is 5 by 2R. Gamma is nothing, that is CP by CV, right? CP by CV. So this is this by this, 5 by 3. 5 by 3 comes out to be 1.66. So this is gamma for the monoatomic gas. Imagine you have a diatomic gas. Diatomic gas like O2. O2 is diatomic, correct? Or you have triatomic linear gas. What is the example of triatomic linear gas? That is your carbon dioxide. That is triatomic and linear at the same time, right? Its CV, remember 5 by 2R. Its CP is 7 by 2R. Its gamma is this by this. So it comes out to be 7 by 5. The value is going to be 1.4, right? Similarly, if you will be having a triatomic non-linear gas, triatomic non-linear, like SO2. No doubt SO2 is triatomic, but it's non-linear. Or by chance, they'll give you a polyatomic gas, right? Polyatomic. Its CV is going to be 3R, CP is going to be 4R, and its gamma is going to be this by this. So 4 by 3 is going to be 1.33. This table you have to remember before doing any sort of questions. And if you keenly look at this particular table, I started with monoatomic gas first, then diatomic, then triatomic. So from top to the bottom, is the atomicity of the gas increasing or decreasing? From top to the bottom. From top to the bottom, is atomicity increasing or decreasing? From top to bottom, atomicity of the gas is increasing. Value of gamma is decreasing. So take a note of one simple statement. I can summarize here as the atomicity of the gas increases, the value of gamma decreases. Perfect. Do remember this particular statement as well. Yeah. Clear, guys? Now, with this, we are complete. Start the first and the most important topic of the chapter, that is internal energy. But Before doing the internal energy, it is high time to take a break. But break I'll only give if you promise that you'll be back on time. Yes? Break I'll only give if you promise that you will be back on time. Yeah? The time right now is 7:50. So let's take the break till, I think 30 minutes are enough. Okay? Break till 8:20. Be back on time. Guys, this is a huge chapter. That's why. Be back on time, okay? So session resumes at 8:20 p.m. Okay? Thank you, everyone. I'll see you after the break, but I would want every one of you to be back because the way you are going to discuss the internal energy, that is going to be amazing. Yeah? That's going to be amazing. Chalo, I'll see you after the break. See you, people. Is everybody back? Yes. Is everybody back on time? Vijay, that has already been extended. You check it. You check it. That has been extended. So are you guys done with your dinner or something? Are you guys done with your dinner? All right, people. Not yet. Even I'm not done yet, okay? We'll have dinner at 10:30. Yeah? I think 10:30 is the perfect time. Cool? So I think everyone is refreshed. All right, so before starting the next topic, one of the most important topics of this particular chapter, before starting this one, let me know once in the chats if all the things which we discussed till now are absolutely clear to you. Say yes or no in the chats. Yeah? Let me know in the chats quickly. Yes, Shrujan, you can watch that. No issues. No, Sudhir, I still do not know that. Okay, so people, let's get going then. Let's get started with the topic that is internal energy. Okay. So first of all, internal energy, which is represented either with capital U or capital E. Represented with either capital U or capital E. Now, what is this exactly, this internal energy? What is this all about? So step by step, we'll talk about the internal energy, people, okay? First of all, internal energy, it is the sum total of the kinetic and potential energy present in the system. It is the sum total of the kinetic and potential energy present in the system. What does it mean? Have a look. My dear students, imagine that you have taken a container over here. And in this container, for example, you have got these real gas molecules. These real gas molecules are there in the container. I'm assuming this container is at rest. Container is at rest. Okay, I'm assuming the container is at rest. Perfect. Now, first of all, these real gas molecules, you already know these gas molecules will be in continuous random motion, right? These gas molecules will be in continuous random motion. Due to which I would say these gas molecules will be having different types of kinetic energies, right? Some of the gas molecules will be showing translational motion, some will be showing rotational motion, vibrational, etc., right? Not going into the details. In short, these gas molecules, they'll be in continuous random motion and they are in motion due to the kinetic energy present in the system. Okay? Number one. Number two, you know, between the real gas molecules, there will be force of interaction. And due to the force of interaction between these gas molecules, which energy comes into play? It is the potential energy which comes into play due to the force of interaction, right? If I take the sum of all the kinetic energies and potential energy present in the system. That means I am calculating basically the internal energy present in the system. So what is internal energy? Internal energy is the sum of all the possible kinds of energies present in the system. Okay? And this kinetic energy present in the system is due to the motion, right? I mean, motion arises due to kinetic energy, and due to the force of interaction between the real gas molecules, I would say there'll be potential energy as well. If you take the sum of them, what you'll get the internal energy of the system. Point number one. Point number two. Internal energy, if I write its definition now, I can write it as the sum total. I can write it like this: the sum total of all the possible kinds of energies, the sum total of all the possible kinds of energies present in the system. Present in the system. Whatever energies are present in the system, you take the sum total of all of them, what you'll get? You'll get the internal energy, right? Next point. This internal energy is a state function. It is a state function. If it is a state function, therefore, we will be calculating the change in its value, and the change in the value of state function is always equal to final value of state function minus initial value of state function, right? Next point. For any cyclic process, you already know this. For any cyclic process, I would say delta U has to be 0. We have already discussed this point as well. Change in the value of a state function for any cyclic process, that's always 0. Okay. Now, my dear students, as I told you, this internal energy is the sum of kinetic and potential energy. Okay. Perfect. It is valid for the real gas. But if I talk about the ideal gas, for an ideal gas, in the ideal gas, between the molecules, is there any interaction? If I talk about the ideal gas, between the molecules, there is no interaction. If there is no interaction, will there be any potential energy present in the ideal gas? There'll be no potential energy. So in case of the ideal gas, your internal energy is basically the total kinetic energy present in the system. It is the total kinetic energy, because the potential energy in case of ideal gas is going to be 0. Why is that? Because there is no interaction between the molecules. This is valid for ideal gas and this is valid for real gas. Okay. Now, if I talk about internal energy in particular, internal energy of a real gas, it depends on two parameters: volume and temperature. Internal energy of the real gas depends on volume, it depends on temperature. It is a function of two parameters, but for a real gas. If I talk about the ideal gas, for the ideal gas, internal energy only depends on temperature. For an ideal gas, internal energy only depends on temperature. That means when you change the temperature of the ideal gas, its internal energy will change. Okay? Its internal energy will change. Perfect. Now, people, few more things. Try to understand what exactly I'm going to say. This is something very important which you need to know. For example, I have got the function y is equal to f of x. What does it mean? It means that on changing x, y will change. Correct? If I want to calculate the change in the value of y due to change in x, that means I will have to get this value, dy upon dx. dy upon dx will give me the change in the value of y due to the change in the value of x. Correct? This is something which I assume you already know. Yeah? But people, if you have got a function like this, z is equal to f of x comma y. This z, it does not depend on one variable. It depends on two variables here. The z depends on two variables. Whenever you will have this sort of a scenario in which, for example, z depends on more than one variable, what do we do at that point of time? See guys, z depends on x, it depends on y as well. That means on changing x, z will change. On changing y, z will change. Now, how do we get that change in the value of z? How do we get that total change in the z? Try to understand. What I'll be doing, what I'll be doing? I'll be first of all doing one thing. I'll be doing one simple thing. I'll keep y constant. I'll keep y constant and I'll change the value of x. On changing the value of x, what is the change in z? That's what I'll measure. So, change in the value of z due to change in x. How do I represent it? Change in z due to change in x. Keeping what constant? Keeping y constant. First of all, I kept y constant. I kept one y constant, changed the value of x and got the change in z. This is my first step. Second step. In the second step, what do? I'll keep x constant and change the value of y and see what is the change in z. So change in z due to change in y. How will you represent it? Change in z due to change in y. But right now, what did we keep constant? We kept x constant. First, I kept y constant, changed the value of x and saw the change in the value of z. In the second step, what did I do? I kept x constant, changed the value of y and got the change in z. Okay. Now, my dear students, if you remove this dx over here, you can multiply it here. Correct? If you remove this dy over here, you can multiply it here. Perfect. This particular term is giving you change in the value of z due to change in x keeping y constant. This particular term is giving you change in z due to change in y keeping x constant. So what is the overall change in z then? Overall change in z will be this plus this. That will be the overall change in z. I hope you got it. That will be the overall change in z. Overall change in z will be this plus this. Okay. Why am I showing you this? Understand. Over here, if you look at this particular equation, as I told you, internal energy is the function of volume and temperature. It depends on two parameters. If it depends on two parameters, how do you get the overall change in internal energy? What you will do? Like this. What you will do? First of all, I'll write it like this. Change in the value of internal energy due to change in volume. Keeping what constant? Keeping temperature constant. Keeping temperature constant multiplied by dV. Multiplied by dV. Plus change in the value of internal energy due to change in temperature. Keeping what constant? Keeping volume constant multiplied by dt. Did you get this particular equation? Did you understand how this equation came? Right? What I showed you over here, same thing I did over here, nothing else. I did not do something different here. Perfect? So this particular equation will be giving you the overall change in internal energy. It is giving you the overall change in internal energy. Now people try to understand. If I particularly talk about the ideal gas, for an ideal gas, you know, internal energy only depends on what? Only depends on temperature. That means, if you have got ideal gas in the container, if you change its volume, keeping temperature constant, will there be any change in its internal energy? Can I say for an ideal gas, this particular term, change in internal energy due to change in volume, keeping temperature constant multiplied by dV, can I say this term has to be 0? Right? This term has to be 0 in case of ideal gas. If this term is 0, I'll say for an ideal gas, what will be the change in internal energy? For an ideal gas, change in internal energy is only this term, which is dou U upon dou T at constant volume multiplied by what? Multiplied by dt. And this particular equation, it is valid just for 1 mole of ideal gas. It is valid just for 1 mole of ideal gas. And my dear students, try to understand few more important things. Over here, you got a term, change in internal energy of the ideal gas due to change in temperature, keeping volume constant. This particular term is something which you call as CV. This particular term, something which you call as CV. So you got one final equation like this. I'll write du, change in internal energy, is equal to, it is going to be CV multiplied by dt. This is valid for 1 mole of ideal gas. So for 2 moles of ideal gas, it's going to be 2 times 3 moles, 3 times n moles of ideal gas. du is going to be NCV dt. This is one of the finest equation which you'll be remembering from now onwards, and it is only valid for what? It is valid for n moles of ideal gas. It is valid for n moles of ideal gas. Perfect. Right, guys? It is valid for n moles of ideal gas. Now, people try to understand carefully what I'm going to say. Imagine you have taken a container. Imagine this is your container. In this container, you have got the ideal gas. The internal energy of this ideal gas depends on only temperature. So if you change the temperature, its internal energy will change. Imagine I'm changing the temperature of the gas from T1 to T2, and I want to calculate the total change in internal energy. Total change in the internal energy of this ideal gas. How will I be doing it? I'll be just doing one thing. I'll be integrating this equation. I'll be integrating this equation with respect to temperature, which we are changing from T1 to T2. Perfect. So I'll be getting delta U, total change in internal energy, is equal to integral from T1 to T2. It's going to be N, it's going to be CV, it's going to be dt. This is the general equation which will always give you the change in internal energy of an ideal gas due to change in temperature. Okay. Now here, if by chance CV for the ideal gas is constant, N is already constant, so take both the terms out. So delta U will be equal to NCV. Integral of dt is t, upper limit, lower limit, so it's NCV T2 minus T1, which can be written like this, NCV delta T. Okay, this is the equation which we shall be frequently using in all the questions of internal energy. Whenever you'll be given an ideal gas, you'll be changing the temperature of the ideal gas, and you will have to calculate change in the internal energy of the ideal gas due to change in temperature. This is the equation which we shall be using. If CV was constant, if CV was temperature independent, and if CV was temperature dependent, then this particular equation. If CV was constant, temperature independent, then this equation. Okay? Right, people? I believe these two things are absolutely clear to you. Now, as I told you, delta U is equal to NCV delta T, which is T2 minus T1. This equation is valid for an ideal gas whose temperature will be changing from T1 to T2, and from this equation we'll get its change in internal energy. Yeah? Right, people? Someone is saying it's very dangerous to see. Yes, it's very dangerous to see, right? Yeah, it's very dangerous to see. Perfect. Now, guys, now a few more things. If I say for an ideal gas undergoing an isothermal process, if the ideal gas is undergoing isothermal process, what does that mean? That means we are changing the state of the ideal gas, but we are making sure its temperature does not change. We are keeping the temperature of the gas constant. If temperature is constant, that means delta T has to be 0. If delta T has to be 0, I'll say delta U for the gas has to be 0. It is pretty much clear also, since for ideal gas, you know, internal energy depends only on temperature. So if temperature only is not changing, there'll be no change in its internal energy, right? So delta U, change in internal energy, will be 0, nothing else. Okay? I believe this point is clear to everyone, right? And people, do remember one simple thing. From this particular equation, you can conclude that internal energy of the gas is directly proportional to temperature. If you increase the temperature of the ideal gas, its internal energy will increase. If you decrease the temperature, its internal energy will decrease. As simple as that. Okay? It is evident also, if you increase the temperature, kinetic energy of the molecules will increase. That means internal energy of the gas is increasing. Simple. Okay? Now, people, here, if I give you one question, let me see if you can solve that question or not. Here, if I'll give you one question, the question is like this. One simple question. Let's say I'm making a graph between internal energy versus temperature. And the graph which I'm making, imagine that is valid for 1 mole of ideal gas. Imagine that The curve is valid for 1 mole of ideal gas. Let's say it's like this, for example, right? Or just a second. Let's say it's like this. Okay, this is the graph. Over here, I'm marking 2 points. This is point A, this is point B. And I am asking you, where is the CV more? Is CV value at A more than that of CV value at B, less than or equal? What do you think about this? What do you think about this, people? What do you think about this particular question? Where is the CV more? Where is the CV more? Quickly. You can give it a try. It's not that difficult. Try to understand. Few minutes back, I gave you one equation. du is equal to n CV dt. If I write this equation for 1 mole of ideal gas, therefore n is 1. If n is 1, I can write CV is equal to du upon dt. What is du upon dt? Du upon dt means slope of the tangent at a point, on internal energy versus temperature curve, right? This is something which I can conclude from here. Correct, people? Now, what do you have to do? I have to check where is the CV more. Correct? So what I'll be doing, I'll be extending this line first of all. After the extension of this particular line, I'll be drawing a tangent here. And then I'll draw one tangent here. Tell me where is the angle more. Let's call this as theta A. Let's call this as theta B. Is theta A more than that of theta B? Absolutely. I can say theta A is more than that of theta B. If theta A is more than that of theta B, what does that mean? That means tan of theta A will be more than that of tan of theta B. What does that mean? That means slope of the tangent at A is greater than slope of tangent at B. And wherever slope is more, then only CV value is more. As simple as that. So I would say CV value at A is more than that of CV value at B. I believe this particular point is also clear to everyone. Yes? Is it clear, people? Let me know in the chats quickly. Yeah? Let me know in the chats quickly if all these things are clear. Perfect, guys. Perfect. Now, after doing the internal energy, let's try to talk about a few other things. What are those other things? Have a look. Just a second. There is something called as first law of thermodynamics. Once we do first law of thermodynamics, then we'll be doing some questions so that you can understand easily this internal energy problem patterns. Okay? What is first law of thermodynamics all about? See, guys, I'm going to write one statement. First law of thermodynamics. It is based on energy conservation principle. First law of thermodynamics is based on energy conservation principle. Now, what it states? Simple. When the state of the system changes, there will be change in its internal energy. When the state of the system changes, there will be change in its internal energy. And that change in internal energy, or let me simplify it a bit. Whenever the state of the system changes, there will be change in its internal energy, which can be brought about in two ways. Number one, when heat is absorbed or released by the system. Number two, when work is done by the system or on the system. Now you must be thinking, what is the meaning of the statements which I wrote over here? Try to understand very carefully what exactly I'm going to talk about here. Okay? Try to understand, people. Imagine that I'm taking a container. This is the container wherein a piston is fitted at the top. The piston is fitted at the top. Imagine you've got this is the gas inside this particular container. I'm assuming the system is right now present at its initial state. And when the system is at its initial state, its internal energy is, for example, U1. Internal energy of the system is U1 right now. Okay? Now, people, for example, I'm supplying some heat to the system. Let's say I'm supplying some heat to the system. I'm supplying Q amount of heat. When I'll be supplying Q amount of heat, to the system, what will happen? Try to understand. When I'll be supplying Q amount of heat to the system, what will happen? Can you let me know what will be the total energy in the system now? Initially, it was U1. Now you are supplying Q amount of heat. So the total energy of the system now will be U1 plus Q. Agreed? Okay. Now, people, for example, you are doing some W amount of work on the system. Let's say you are doing W amount of work on the system. For example, you are bringing this piston down. Bringing this piston down means decrease in volume, compression. Compression means work is done on the system. I'm assuming that W amount of work is done on the system. Whatever amount of work is done on the system, I'm assuming whatever amount of work is done on the system, I'm assuming that work is stored. That work is stored in the gas in the form of its internal energy. Whatever amount of work is done on the system, I'm assuming that that amount of work is stored in the gas in the form of its internal energy. Now you tell me. Over here, the total energy was U1 plus Q. Now W amount of work is done on the system. What will be the total energy of the system now? It's going to be U1 plus Q plus W. Assume that this is the final state of the system. This was the initial state of the system. Okay, assume this is the final state, right? Let's call this as the final internal energy of the system. Okay, let's call this as final internal energy of the system. So what could I conclude from here? I could say U2 is nothing. It is U1 plus Q plus W, right? Now, if you put U1 on this side, it's going to be U2 minus U1 will be equal to Q plus W. And U2 minus U1, final internal energy minus internal energy, give you change in the internal energy. So change in the internal energy as per first law of thermodynamics is equal to Q plus W. Just this thing you have to remember, nothing else. Delta U is equal to Q plus W. Delta U is equal to Q plus W. Where Q is the amount of heat absorbed or released by the system, where W is the amount of work done by the system or on the system. That's all. Now the point is, how do we use this equation? For that, we'll do few questions and you'll understand automatically how this first law, what kind of questions are asked from first law of thermodynamics. Look at this particular question, very common question. Very common question. A system means ideal gas, okay? A system expands from 5 liters to 10 liters, right? That means the gas is undergoing expansion. Initial volume of the gas is 5 liters. Final volume of the gas is 10 liters. The gas is undergoing expansion against a constant external pressure. The gas is undergoing expansion against a constant external pressure of 2 atm. And if the external pressure is constant, I'll be calling this expansion as irreversible expansion. You know it? Okay. And as per the question, when this expansion is happening, the gas is absorbing heat. How much heat is absorbed by the gas? During the expansion, the gas is absorbing this much of heat. And when the system absorbs heat, Q value is taken to be positive. So it's plus 800. What do we have to calculate? We have to calculate the value of delta U. And this delta U, for example, we have to calculate in joules. How do we get it? How do we get it? We'll use the first law of thermodynamics. You know, your delta U is nothing. It is Q plus W. Delta U is equal to Q plus W. Which W am I talking about? The process is irreversible. So this is W irreversible. Correct? Q value already we have. W value we do not have. So we'll be calculating W first of all. And how do we calculate W irreversible? I already gave you the expression if you remember, which is minus P external delta V, V2 minus V1, right? So what is P external? P external is 2 atm, V2 minus V1, final minus initial, that will come out to be 5 liters, right? So this value will be minus 10. Pressure is in atm, volume is in liters, so the units of W will be atm liter, right? Units of W will be atm liter. Units of W here will be atm liter. Now convert it into joules. I already told you 1 atm liter is 101.3 joules. So the value is minus 1013 joules. This is the value of W in joules. If you got the value of W in joules, Q is already given in joules. That means delta U has to be equal to Q. Q is how much? Q is 800 joules. 800 joules. W is how much? W is minus 1013 joules. When you solve this, the value will come out to be minus 213 joules. This is something which I was supposed to calculate as per the question. That's all. Yes? Is it clear to everyone? Quickly, people. Is it clear to everyone? I believe this sort of a question you can easily solve from now on. Similarly, there is one more type of question. I am pretty much sure that this particular question you can easily solve on your own. Look at the question. I'm not solving this, you have to solve this. Delta U is given. Delta is given. Q value is given. We have to calculate delta V. And P external is also given. Change in volume. Change in volume. Delta V we have to calculate. Yeah? Change in volume. Delta V we have to calculate. Can't we do it? Can't we do it, people? Yeah? Vijay, I'll check it again. I'll check it again. I got a call today from the backend team that the batch access for JE has extended. Now you are telling that it's not, so I'll have to check it afterwards. Perfect. Can you solve this particular question, people? Can you solve this particular question on your own? Yeah? All right. Have you heard about something called as enthalpy, which is again very important? Enthalpy, which is represented by H. Which is represented by H. First of all, if you ask me how this enthalpy function, how the enthalpy of the system was introduced, how this particular function, enthalpy, you call it as an enthalpy function or whatever, how this was introduced. See guys, how this particular function was introduced. See. As per first law of thermodynamics, delta U is equal to Q plus W. You know it, correct? Yes. If I write this equation at constant pressure, can I say delta U will be equal to, instead of Q, I'll write QP plus W, where QP will be heat absorbed or released by the system at constant pressure. Okay. So can I say delta U is nothing? It is QP. W will be minus P delta V. Delta V will be V2 minus V1. Delta U, change in internal energy, final minus initial, is equal to QP. This will be minus PV2. This will be plus PV1, right? If I reshuffle this equation, if I take these terms on the left side, I'll be getting something like this. U2 plus PV2 minus U1 plus PV1 is equal to QP, is equal to QP. Is equal to QP. Now, do you see two common things here? It is just U2 plus PV2. Here it is U1 plus PV1. It is just states are different. This particular equation is written at final state. This equation is written at initial state. This is U2 plus PV2. This is U1 plus PV1. So, in order to reduce the calculations, can I do one thing? This U plus PV, let me call this as H, right? Here you have got U plus PV, here you have got U plus PV. It is just this that final state of the system, this that initial state of the system. So instead of U plus PV I'm calling as H. So can I say this particular term here is basically H2? This particular term is H1, and which is equal to QP. So I got to know QP is nothing, it is but delta H. QP is delta H. What is meant by this QP is equal to delta H? It has got the significance. It has got the significance. Try to understand what is Its significance, my dear students, I'll say something like this. I'll say something like this. Delta H means enthalpy change of the system. So first I'm defining enthalpy change. What is enthalpy change? Enthalpy change of the system is nothing. It is heat absorbed or released by the system at constant pressure. Whatever heat is absorbed or released by the system at constant pressure. Whatever heat is absorbed or released by the system at constant pressure. That is something which you will be calling as enthalpy change. Nothing else. Right? So I'm writing a statement over here. Enthalpy change is defined as the heat absorbed or released by the system at constant pressure. Whatever heat will be absorbed or released by the system at constant pressure, that is something which you will be calling as enthalpy change, right? And eventually at the end you got to know QP is nothing, that is delta H. QP is nothing, that's delta H. Now people, this is something which is very important. You'll get its significance in some time. But before that, let's talk about some general features of enthalpy. Number one. If I talk about enthalpy of the system H, which is basically the sum of internal energy and the pressure volume work. This is something which we call as enthalpy. U plus PV is called as enthalpy, right? Now, understand properly. Internal energy is a state function. Pressure is a state function. Volume is a state function. That means your enthalpy automatically becomes your state function. So enthalpy is a state function. If enthalpy is a state function, therefore we'll be calculating its change. So change in enthalpy will be simply equal to H final minus H initial. H final minus H initial, right? H final minus H initial. Now, dear students, this enthalpy, as I told you, internal energy, it gives us the idea about the total energy present in the system. This enthalpy, it gives us the idea about the heat content present in the system. This enthalpy function, which is H, it is also an extensive property, like your internal energy, right? It's an extensive property. If you will find any cyclic process, do remember change in the value of enthalpy for any cyclic process, that will be 0. Because change in the value of state function for a cyclic process, that's always 0, right? So delta H for the cyclic process is equal to 0. Okay, this is one more point which you have to remember related to enthalpy. Similarly, as internal energy used to be the function of volume and temperature, right? Your enthalpy, it is a function of pressure and temperature. For what? For a real gas. For an ideal gas, enthalpy is again the function of temperature only. The enthalpy is again the function of temperature only for the ideal gas. Enthalpy is again the function of what? The function of temperature only for the ideal gas. Now guys, try to understand carefully what I'm going to say. Try to understand very carefully. I told you enthalpy, it is a function of pressure and temperature for the real gas, right? For the real gas. Now, again you have got H, which depends on two variables, pressure and temperature. If you change the pressure, enthalpy will change. If you change the temperature, enthalpy of the system will change. Now, how do we get the overall change in enthalpy? How do we get it? The overall change in enthalpy, which I'm representing with dH, that is equal. How do we do it? We'll be using the partial differentiation, the way we did for internal energy. I'll write change in internal energy due to change in pressure, keeping temperature constant, multiplied by dP, plus change in enthalpy due to change in temperature, keeping pressure constant, multiplied by dt. This particular equation gives me the overall change in enthalpy. Now, as I told you, for ideal gas, enthalpy only depends on temperature. For ideal gas, enthalpy only depends on temperature. Enthalpy only depends on temperature. So if you change the pressure of the ideal gas, enthalpy won't change. So I'll say for an ideal gas, change in enthalpy due to change in pressure, keeping temperature constant. What about this particular term? What will be its value? I'm talking about the ideal gas. For the ideal gas, enthalpy only depends on temperature, right? So you are keeping the temperature constant and changing the pressure of the ideal gas. What will happen to enthalpy? Nothing, right? Because enthalpy of the ideal gas, it only depends on temperature. So for an ideal gas, do remember, change in enthalpy due to change in pressure, keeping temperature constant multiplied by dP, it has to be 0, correct? So your dH has to be equal. It is simply going to be dou H upon dou T, keeping pressure constant multiplied by dt. This particular equation which we got over here, it is valid for only ideal gas. That too for 1 mole of ideal gas. Okay. Now guys, here I can say dH is equal to this particular term. This particular term is something which you call as Cp, molar heat capacity at constant pressure, multiplied by dt. And this equation is valid for 1 mole of ideal gas. It is valid for 1 mole of ideal gas. Imagine you have n moles of ideal gas, then dH has to be equal to nCp dt. dH has to be equal to nCp dt, right? dH has to be equal to nCp dt. Perfect. If you got dH equal to nCp dt, can I say this particular equation, it is valid for n moles of ideal gas. Okay, n moles of ideal gas. Now people, imagine that you have got a container which contains an ideal gas. There is ideal gas in this container, right? Enthalpy of the ideal gas just depends on temperature. If you are changing the temperature of this gas from T1 to T2, and I'm asking you, due to the change in temperature, what will be the total change in enthalpy? How do you do it? How do you calculate the total change in enthalpy due to the change in the temperature of this ideal gas? How you are going to do it? Understand? We got to know dH is equal to nCp dt, correct? I'll be integrating this equation under the limits. Under the limits, you're integrating with respect to temperature and you are changing the temperature from T1 to T2. Integral of dH is nothing, that's delta H. So delta H is equal to integral from T1 to T2. This is N, this is Cp, this is dt. This is the general equation with the help of which you will be calculating change in enthalpy of the ideal gas when you will be changing the temperature of the ideal gas from T1 to T2, right? And by chance, if Cp was temperature independent, that means if Cp was constant, N is already constant, I can say delta H is equal to N take out, Cp take out, integral of dt is T, upper limit, lower limit, so T2 minus T1. T2 minus T1 is nothing, that is your delta T, change in temperature. So this particular equation we are going to use in the questions. Whenever we'll be asked to calculate the enthalpy change of the ideal gas upon changing the temperature of the ideal gas from T1 to T2, this is the equation which we shall be using. If Cp for the ideal gas was temperature independent. If Cp was temperature dependent, then this equation. If Cp was temperature independent, then this equation. Okay? Right, people? Now understand few more things. Here. Based on, or let me tell you first of all, one more thing. If I write a statement for an ideal gas, if you'll be having an ideal gas undergoing isothermal process, for an ideal gas undergoing isothermal process. Isothermal process means, that means temperature of the gas is not changing, it's constant. If temperature is not changing, delta T, change in temperature is 0. If change in temperature is 0, that means automatically delta H for the ideal gas undergoing isothermal process, that will be 0, right? Delta H for the ideal gas undergoing isothermal process, that's always 0. Okay, but do remember it's valid only for ideal gas. It is not valid for real gas, right? Okay, perfect people. Is this point clear? Now, similarly, there is one more point. As I told you, delta H for the ideal gas is equal to NCP delta T, which is T2 minus T1. This is the equation. Now, people, based on the sign of delta H, we classify processes into two types. The sign of delta H can be negative or the sign of delta H can be positive. That process for which delta H value is negative, you call that process exothermic process. That process for which delta H value is positive, you call that as the endothermic process. And people, if delta H is negative, that means T2 minus T1 has to be negative. And when will be this term negative? That will be negative only when T2 is less than T1. Okay. So final temperature of the system will be less than initial temperature. So for the exothermic processes, in case of exothermic processes, final temperature of the system is less than initial. Over here, you can say T2 minus T1 has to be positive, which tells you that T2 will be greater than T1. Okay, do remember these two terms as well, right? And after remembering these two terms, if I give you a question like this, understand, give its answer in the chats, okay? For example, I'm plotting a graph. The graph is between enthalpy versus temperature. And the graph is again like this, okay? And imagine this graph is valid for 1 mole of ideal gas. What I'm exactly doing here, I'm marking 2 points, point A, point B. I'm asking you, where will be the CP value more? Is CP value more at A or CP value is more at B? What do you think? Quickly, guys. What do you think? Where will be the CP value more? I'm asking you. See, I already gave you one equation. Equation was dH is equal to NCP dt for 1 mole of ideal gas, where N is 1. If N is 1, you can say CP is equal to dH upon dt. What is dH upon dt? dH upon dt will give you nothing. It will give you the slope of the tangent. At a point. On enthalpy versus temperature curve. Correct? So can I say wherever slope is more, CP will be more? Now what you'll be doing? Just extend this particular line over here. After extension, draw the tangent at point A. Imagine it's making angle theta A with the positive x-axis in the anti-clockwise direction, right? Draw the tangent at point B. Imagine it's making an angle theta B with the positive temperature axis, right? In the anti-clockwise direction. So which theta is more? Can I say theta A is basically more than theta B? If theta is more than theta B, can I say tan of theta should be greater than that of the tan of theta B? So that means slope at A will be greater than slope at B, right? And wherever slope of the tangent at a point is more, CP value is more there only. So I would say CP value at A is greater than that of CP value at B. I believe this particular point is clear to everyone. This was the question on your screen, right? This was the question on your screen. I hope this is done and dusted. Yeah? I hope it's done. Is it clear, people? Will you be able to solve this sort of equation on your own from now onwards? Yes? Now, guys, understand. Two things which we got till now. Delta U for the ideal gas is equal to NCV delta T if CV is constant, and delta H for the ideal gas, which is equal to QP, right? Which is equal to NCP delta T. Do you remember when I gave you the heat capacities? When I gave you some expressions to calculate heat exchanged, there I gave you two things. One was QP, one was QV. QP was equal to NCP delta T, and QV was equal to NCV delta T. Here you have got NCV delta T, which is basically nothing. It is QV. Perfect. So basically, anything can be asked out of these equations. They can give you a question like this. They can give you a question like this. Calculate the heat absorbed or released by the system at constant volume. That means you have to calculate delta U, which for the ideal gas is nothing but NCV delta T. They can ask you, calculate the heat absorbed or released by the ideal gas at constant pressure. That means you have to calculate nothing delta H, and delta H for the ideal gas is NCP delta T. Well, this you can verify with the help of first law of thermodynamics as well. You can verify it. You can check it out whether this is correct or not. See guys, you can verify it as well. You know, as per first law of thermodynamics, delta U is equal to Q plus W. Correct? If I write the equation at constant volume, if I write the same equation at constant volume, if the volume of the gas is not changing, if the volume is constant, that means W has to be 0. If W is 0, I can simply say delta U is equal to Q, but here I won't be writing Q, I'll be writing QV, right? And in case of the ideal gas, already we know delta U is nothing, that is NCV delta T. Correct? You can verify it from here as well, right? You can verify it from here as well. Is it clear? Is it clear to you? Is it clear to you? Okay. Now see what kind of question can be asked from these equations here. See what kind of question can be asked from the equations here. Just a second. Look at the question carefully, guys. It's a very simple and basic question. Very simple and basic question. Try to understand. Calculate delta U and delta H when 10 decimeter cube. 1 decimeter cube is equal to 1 liter. That means when 10 liter of helium. So as per the question, we have got 10 liters of helium. We have got 10 liters of helium, right? And this helium is present at STP. This helium is present at STP. If helium is present at STP, that means its temperature right now will be 0 degrees centigrade and its pressure will be 1 atm. As per the question, we have got 10 liters of helium which is present at STP. Okay. Now, as per the question, you are heating this helium. You are heating this helium, right? You are heating this helium. Till what? Till 100 degree. Initial temperature was 0 degree. Now, you are heating this helium till 100 degrees centigrade. Tell me one thing. Tell me one thing. If helium is the ideal gas, here, we are changing the temperature of ideal gas. And you know, for an ideal gas, internal energy is the function of temperature only, and enthalpy is also the function of temperature only. So if we change the temperature, internal energy as well as enthalpy of the ideal gas will change. Okay. We have to calculate that change in internal energy and that change in enthalpy. Okay. How we are going to solve this question? First of all, if I ask you, we had 10 liters of helium at STP. So can you let me know how many moles of helium we had? Given volume of helium in liters divided by 22.4, right? So these are the moles of helium which we have. What do we have to calculate? Delta U and delta H. Delta U and delta H. Delta U and delta H. You know, delta U for the ideal gas, you already know that's equal to NCV delta T, T2 minus T1, if CV is constant. Okay. Similarly, delta H you can calculate. So first of all, delta U will be equal to N value. N value is 10 divided by 22.4. CV, helium. Helium is first of all a monoatomic gas. If it is a monoatomic gas, its CV will be equal to how much? T by 2R. T by 2R. Now, T2 minus T1. Final temperature minus initial temperature. The value comes out to be 100. Correct? Imagine we have to calculate delta U in joules. If delta U has to be calculated in joules, what you will be doing? This you will be writing 10 by 22.4 multiplied by 3 by 2. R value you will use as 8.314 joules per Kelvin per mole multiplied by 100. The final answer you will be getting in joules. So this equation will give you the value of delta U. This equation will give you the value of delta U. Right? Now similarly, in the equation they're asking you to calculate delta H. And you know delta H for the ideal gas is NCP_T2 minus T1. NCP_T2 minus T1. Right? Yeah. So N value, you already know. What is N? N is 10 divided by 22.4. What is CP? CP will be 7 divided by 2 R. Right? Wait, sorry, not 7 by 2, 5 by 2. Huh? CP for the monatomic gas is 5 by 2 and R value is 8.314. Change in temperature is 100. Final minus initial. Solve this. and get the answer in joules. These were the two questions which were asked. We were supposed to calculate delta U and delta H for the ideal gas. I hope this is clear. Now someone is asking, what if CV and CP was temperature dependent? For example, if in the same question, if it was mentioned that CV is equal to 5 times capital T, joules per Kelvin. Let's say in the question they had mentioned this. At that point of time, were we supposed to use this equation? No. Here, if CV was temperature dependent, then delta U was to be calculated like this. Integral from T1 to T1 and CV dt. Then you had to use the integration. You had to use the integration at that point of time, right? And T1 to T2, right? T1 is 273 Kelvin, T2 is 373 Kelvin, N is 10 divided by 22.4, CV is 5 times T multiplied by dt. So this particular term will come out of the integral. Integral of T dt will be T square by 2, upper limit, lower limit. At that point of time, you would have gotten the answer. So it depends basically. It depends. Like I have already mentioned it over here. Just a second. I've already mentioned it over here. If you see, I've already mentioned it over here. If CP was temperature independent, then this relation. If CP is temperature dependent, then this particular integral, right? Similarly, same goes for CV. If CV was temperature independent, then delta U is equal to NCV delta T. If CV was temperature dependent, then integral from T1 to T2 NCV dt. I hope you got it. Is that clear? Is that clear, people? So these are the two types of questions which can be asked from your delta U, delta H, delta U and delta H problems. Okay? By the way, they could have given the same question in a different format. They could have asked you, calculate the heat absorbed or heat released at constant volume. That means QV. QV is nothing, that's delta U. Delta U for ideal gas is nothing, that's NCV delta T. That's it. Right? Is it clear, people? If this is clear, then there is one more important topic. What is that? That is a relation between delta H and delta U. This is one very critical topic from which questions are frequently asked, and different types of questions are asked from this particular topic. So understand it properly. Okay? First of all, as you already know, H is equal to U plus PV. H is equal to U plus PV. This is something which we have defined. Enthalpy is defined as the sum of internal energy and the pressure volume work, right? Now, people, if I differentiate this equation, this becomes dH is equal to du plus d of PV. Correct? This can be further written as dH is equal to du plus P dV plus VdP, right? Plus VdP. Okay? Or let's not elaborate it so much. Let's do one simple procedure here. Let's integrate this one, and this one. Let's integrate this equation. Integral of dH will come out to be delta H. Integral of du will come out to be delta U. And this will be equal to delta of PV. This is one general result which connects enthalpy change and internal energy change. This is the general result which is valid everywhere. Okay? Right? This is the relation between delta H and delta U in general. Now, guys, what we shall be doing? For example, when you find a question where it's mentioned that pressure of the system is constant. If you find a question wherein it's mentioned that pressure of the system is constant, if pressure is constant, you'll write the same equation in this format. Delta H is equal to delta U. Pressure is constant, take it out, so it becomes P. And with this, you'll be writing delta V. This is the equation which I'll be using when pressure of the system is constant. If by chance volume of the system is constant, then take V out. So I would say delta H at that point of time will be equal to delta U. Take volume out, it becomes V delta P. Right? This is the equation which is valid. At constant volume. Right? Now, for example, if pressure and volume both are changing, if pressure and volume both will be changing, At that point of time, the equation will be written like this. Delta H is equal to delta U plus, it becomes simply P2V2 minus P1V1. Delta H is equal to delta U plus P2V2 minus P1V1. Minus P1V1. Correct? Okay. Look at all the cases. This is valid when pressure is constant, when volume is constant. When pressure and volume both will be changing, then this equation we have to use in the equations, right? And let me tell you, for a gaseous phase reaction, which is carried out at constant temperature, let's assume that I've got the reaction like this: N1A gas plus N2B gas. Oh my God. N1A gas plus N2B gas, it gives N3C gas plus N4D gas. This is a gaseous phase reaction, first of all, right? Imagine this reaction is carried out at constant temperature. If this reaction is carried out at constant temperature, if I ask you, what is the value of delta Ng for this reaction? If I ask you, what is the value of delta Ng for this particular reaction? You'll say delta Ng is equal to number of moles of gaseous products, which is N3 plus N4. Number of moles of gaseous products, which is N3 plus N4, minus number of moles of gaseous reactants, which is N1 plus N2. Which is N1 plus N2, right? This is how you calculate delta Ng. Now, which equation do we use here in case of gaseous phase reaction? Do remember delta H is equal to delta U plus delta Ng, and this is RT. This is the equation which I'll be using in case of gaseous phase reactions which are carried out at constant temperature. Perfect. So 1, 2, 3, and 4. 4 different types of questions can be asked from this particular example. Okay, from this particular topic. Now I know it's too dark, but electricity is gone, so we'll have to study in dark mode for some time. Okay, the electricity resumes back. All right. Okay. Perfect. Now guys, let's try to solve few questions so that you can understand how and where we use these sort of equations. See, the first type of the question which is on your screen. Look at the question carefully. 1 mole of ideal gas undergoes a change in state. 1 mole of ideal gas undergoes a change in state. When the gas was at initial state, as per the equation, its pressure was 2 atm and its volume was 3 liters, right? Now, the gas is undergoing a change in state. Now, as per the equation, the pressure of the gas is 2 atm and the volume is 7 liters, right? So, first of all, this is the initial pressure of the gas. This is the initial volume of the gas. This is the final pressure of the gas. This is the final volume of the gas. So, first of all, check. Volume of the gas is changing. We are changing the volume of the gas. We are changing one of the state parameters. You are changing one of the state parameters. And when one of the state parameters changed, the state of the system automatically changes. That means if this was the initial state of the system, this I'll be calling as the final state of the system. This I'll be calling as final state of the system. And as per the question, when the system undergoes the change in the state, its delta U is equal to 30 atm liter. What do we have to calculate? We have to calculate delta H for the process. Delta H we have to calculate. Now, how you are going to solve this? Understand carefully, people. You are changing the state of the gas. When you are changing the state of the gas, that means its internal energy will change, because internal energy is the state function. If state is changed, state function value is changed. Now calculate. Internal energy change is given. We have to calculate the enthalpy change. Now, first of all, if you observe, pressure initial was 2 atm, final is also 2 atm. That means the pressure of the system is given to us as constant. Pressure is constant. If pressure is constant, which equation do I need to use? Equation is delta H is equal to delta U plus P delta V, which is P V2 minus V1. This is the equation which I'll be using, right? Now, delta H is equal to, what is delta U? Delta U is 30 atm liter. I'm writing its units as well. Plus, what is P? P is 2 atm. V2 minus V1, 7 minus 3 is 4, right? So 2 multiplied by 4. Pressure is in atm, volume is in liters. So this term is also in atm liter. So the value comes out to be how much? 38 atm liter. 38 ATM liters. This is the value of delta H. This is the value of delta H for the process which we were supposed to calculate, right? And people at the same time, imagine you were not supposed to calculate the value of delta H in ATM liter. Imagine you are supposed to calculate it in joules. Then this has to be 38. Instead of ATM liter, you'll write 101.3. Then the answer will be in joules. I believe this is clear. This is one type of the question which can be asked. Look at the second type of the question. Look at the second type of the question. The question says, which of the following is correct for the following exothermic reaction carried out at constant pressure? So, as per the question, the reaction that is given to us, it is exothermic. It is exothermic. And it's carried out at constant pressure. And with constant pressure, it will be carried out at constant temperature as well. Because, I mean, all your reactions are basically carried out at constant temperature. And apart from that, pressure is also constant. Now, leave that part aside. It is mentioned that the reaction is exothermic. If reaction is exothermic, if the process is exothermic, during exothermic process, heat is absorbed or released. During exothermic process, heat is released by the system. And whenever heat is released by the system, as per sign convention, Q value has to be taken as negative. So Q for this process has to be negative. But over here, they are mentioning as Q is positive. So Q positive cannot be the answer. So D cannot be the answer. D cannot be the answer. Q is negative for the process. Number one. Number two. Since the reaction is carried out at constant pressure and temperature, and you know PV is equal to nRT, right? Since the reaction is carried out at constant pressure and temperature, R is already constant, so I can say volume is directly proportional to moles. If moles are increasing, volume will increase. If moles will decrease, volume will decrease. Now, try to understand. How many gaseous moles do we have on the reactant side? 3 plus 1, 4. How many gaseous moles do we have on the product side? 1 plus 1, 2. So when this process is happening, are the gaseous moles increasing or decreasing? 4 to 2, gaseous moles are decreasing. And when the gaseous moles will be decreasing, volume of the system will be decreasing. Volume of the system will be decreasing. And decrease in the volume of the system is what you call as compression. Decrease in the volume of the system is what you call as compression. And you know, whenever there is compression, work is on the system and W value is taken to be positive. But here, W value is given to us as negative, so this cannot be the answer. Okay? Now people, after doing all these things, let's try to understand a few more things. Now, only point is the relation between delta U and delta H. First of all, tell me one thing. What about delta Ng for this reaction? Number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactants, which is 3 plus 1, 4. The value comes out to be minus 2. Now, you know, delta H is equal to delta U plus delta NGRT, right? So I can say delta H has to be equal to delta U. Delta Ng is minus 2. This is RT. So from this particular equation, you can conclude a lot of things. Or let me write it so that you can properly interpret it. So delta U is equal to delta H plus 2 RT. Now, if you look at this particular equation, is this particular equation telling you that delta U is equal to delta H? No. Delta U, left hand side, right hand side are equal only if this term has been added on right hand side. So basically, we have to add this term towards delta H. Then only it will get equalized to delta U. Or I can categorically say here, delta U is greater than delta H. Delta U is greater than delta H. By how much of amount? By this much of amount, right? Or you can say in reverse, delta H is less than delta U. Perfect. Check the options. This cannot be the answer. Delta U is greater than delta H. So option B is the one which is correct among all. Right? Is this particular point clear? Is this particular point clear? Is this particular point clear, people? I hope yes. Yeah? Okay. Let's move on to one more question then. Let's move on to one more question. Even this sort of a question can be asked. Look at the question carefully. What is it? Calculate delta U. Calculate delta U when 2 moles of liquid water. When 2 moles of liquid water vaporizes at 100 degrees centigrade. The heat of vaporization is given. Okay. See guys, what this question exactly is all about. As per the question, you are vaporizing water That means H2O liquid, you're converting into H2O gas. That means H2O liquid, you're converting into H2O gas. Okay. As per the question, delta H for vaporization. Delta H during this process given 40.66 kilojoules per mole. What do we have to calculate? We have to calculate delta U. We have to calculate delta U. If you try to understand it carefully, delta U we have to calculate. Okay. Now, first of all, what about delta Ng for this reaction? Delta Ng will be equal to number of moles of gaseous product, which is 1, minus number of moles of gaseous reactant, that's 0. So the value comes out to be 1. Value comes out to be 1. So I'll reuse the equation. Delta H is equal to delta U plus delta Ng RT, right? So I can get delta U from here. Delta U will be equal to delta H minus delta Ng RT. Now tell me certain things. As per the question, delta U has to be calculated in kilojoules. For that purpose, delta H has to be in kilojoules, right? And this particular term, delta Ng RT, it has to be in kilojoules as well. Okay, it has to be in kilojoules as well. Now guys, how do you solve this? Try to understand very carefully. Delta U will be equal. Delta H for the process is 40.66 kilojoules minus delta Ng value is 1. R value is 8.314, but this is joules per Kelvin per mole. Joules per Kelvin per mole. Temperature is given to us as 100 degrees centigrade, which is 373 Kelvin. Now, since this term, R value 8.314 joules, this is joules per Kelvin per mole. But this term we do not need in joules, we need in kilojoules. So how do you convert joules into kilojoules? Divide by 1000, then only this term will come out to be in kilojoules. And when you solve this particular term, you'll be getting the value exactly as 37.5 kilojoules. Now there is the first option which says 37.5. If you mark this, you are gone. Why is that? Why is that? Because this is the value of delta U for the vaporization of 1 mole of liquid water. This is the value of delta U for the vaporization of 1 mole of liquid water. But as per the question, we are not vaporizing only 1 mole of liquid water. We are vaporizing 2 moles of liquid water, right? So this is the value of delta U for the vaporization of 1 mole of liquid water. So I would say for the vaporization of 2 moles of liquid water, delta U has to be 37.5 multiplied by 2. The value comes out to be 75.1 kilojoules. This is going to be the final answer of the question. Option B is the correct one. I hope this particular question you can solve. Yeah. Will you be able to solve this particular question? Absolutely, you should be. You should be. Okay. Now guys, look at this particular question as well. Understand the language of the question. For the combustion of benzoic acid, we are doing the combustion of benzoic acid at 300 Kelvin and 1 atm pressure. Heat released is, during the process, this much amount of heat is getting released. Calculate the heat released at constant volume for the same process. For the same process. For the same process. Can you solve it? Can you solve it? Yalini is saying, sir, you can take some difficult questions. Give me the answer of this question. If you could solve this question, then I'll give you advanced question. Okay? Promise. Solve this first. Quickly. Quickly, guys. See, guys, what this particular question exactly is all about. Try to understand what this particular question is all about. Have a look. As per this particular question, we are doing the combustion of benzoic acid. And when we do the combustion of benzoic acid, we are doing the combustion of benzoic acid at constant pressure. We are keeping pressure constant. The first thing which you have to identify here, this reaction is carried out at constant pressure. This reaction is carried out at constant pressure, right? As per the question, heat released during the process is 300 kilojoules. And we know heat released at constant pressure is nothing but QP. Heat absorbed or released at constant pressure is nothing but QP, correct? Which, as per the question, since the reaction is carried out at constant pressure, so it is basically the heat released at constant pressure, which is QP. And QP is nothing, that's delta H. So delta H is equal to 300 kilojoules. But since heat is released, so sign has to be negative. So this is something which is given to us as per the question, right? This is something which is given to us as per the question. What are we supposed to calculate? Calculate the heat released at constant volume. You know, heat absorbed or released at constant volume is basically QV, which is delta U. So basically you have to calculate delta U for the process, nothing else. As per the question, this process carried out at constant pressure. And heat released at constant pressure is nothing, that is QP. QP is already delta H, we know that. And delta H is given. Now people, calculate delta Ng for the reaction. Delta Ng is equal to number of moles of gaseous products, which is 7. This is liquid, nothing to do with this. Nothing to do with this. Minus 15 by 2. This is 15 by 2 here. The value comes out to be minus 1 by 2. So this is delta Ng value. If this is delta Ng, I can say delta H is equal to delta U plus delta NGRT. Okay? Delta H is equal to delta U plus delta NGRT. Now you need to tell me, what are we supposed to calculate? Delta U. So delta U has to be equal to delta H minus delta NGRT. Now you can do some calculations. Let's assume that delta U has to be calculated in kilojoules. That means delta H has to be in kilojoules as well. So it is minus 300 kilojoules. Correct? Minus delta Ng value, that's minus 1 by 2. So it becomes plus 1 by 2. R value I'm using 8.314 joules per Kelvin per mole. Temperature is given to us as how much? 300 Kelvin. Since I've used the value of R as in joules per Kelvin per mole. But this I'm using kilojoules, this kilojoules. So this term also has to be in kilojoules. So I'll be dividing here with 1000. Then only this particular term will be in kilojoules as well. Now it's a matter of calculation. And you'll be getting the value of delta U in kilojoules, which I was supposed to calculate. Right? Is it clear, people? Is it clear, people? Is it clear to everyone, people? I hope even this sort of a question you can solve from now on easily. Now comes one of the most important topics, and this is the topic in which majority of the students, they are confused. Okay? This is the topic in which majority of the students, they get confused. Yeah? So guys, how do we exactly explain this reversible, irreversible? By the way, can you see me? Am I visible to you? Am I visible to you? By somehow? Yeah? Okay, then it's perfect. All right, so let's try to understand what are reversible and irreversible processes. Before understanding the reversible and irreversible processes, we need to differentiate them. So I'm writing few things. You are going to write them with me. So on left side, I'm defining reversible process. On right side, I'm defining irreversible process. So what is reversible? What is irreversible? Few points, then we'll understand them one by one. Okay. First thing, reversible processes are the slow processes. Number one, the first point. Reversible processes are the slow processes. Driving force is greater than opposing force only by a small amount. Only by a small amount. What it means, you'll get the idea in some time. Driving force is, okay, P gas, P external are almost equal. System and surrounding are at equilibrium at every point of time. At every point of time. At every point of time. These are also called as imaginary processes. How do we calculate work done in reversible process? That is minus integral V1 to V2. And this is P gas multiplied by dV. I'm going to explain all these points one by one. First, I want you guys to write these. Okay? In case of irreversible processes, I'll say these are fast processes. Driving force is far greater than the opposing force. External pressure is constant here. System and surroundings are at equilibrium. Only at initial state and final state. Initial state and final state. These are what you call as the real processes. Real processes. Work done during irreversible process is nothing. It is minus the external multiplied by delta V. These are the differences between the two. These are the differences between the two. Now let's try to understand them one by one. Just give me a second, guys. Just give me a second. Just give me a second. Just people. Guys, did you take a note of this? Did you take the note of this? Did you take a note of all these things? All right, people, just a second and I'll explain these points one by one. Just a second. Okay. Let's try to understand now what are reversible and irreversible processes in detail. Perfect. Guys, first of all, as the first point is concerned over here, reversible processes, these are slow processes. Irreversible processes are fast processes. Let me give you an analogy first of all. This is the marker which you all can see, right? This is the marker. Just imagine I'm lifting this marker up. Tell me, when I'm lifting this marker up, how many forces are being experienced this marker up? Say, I'm lifting this marker up. How many forces are experienced by the marker? How many forces are experienced by the marker when I'm lifting it up? One force which I am giving in the upward direction, due to which the marker is going up, and one force that is due to gravity, which the gravity is pulling it towards itself. So basically, when I'm pulling the marker up, two forces are experienced by this marker. One which I am giving in the upward direction, due to which it's going up. Other, the gravity is pulling it towards itself, right? Downwards, I mean. That is one more force. That force by means of which the marker is going up, I'm calling that force as driving force, which I am giving. The downward force due to gravity is something I'm calling as opposing force. Correct? So when the marker is going up, two forces are experienced by the marker. One, which I'm giving up in the upward direction, by means of which it's going up, that's driving force. Second, due to gravity, which is opposing it, which is opposing its motion, I'm calling that as opposing force, right? Now tell me one thing. In order to lift this marker up, I've got two ways. Either I will lift this marker fastly, or I can lift this marker slowly. Imagine I am lifting this marker fastly. What does that mean? That means driving force is far, far, far greater than the opposing force. That is why I can lift this marker fastly. That is the reason why I'm lifting this marker fastly. See, in the upward direction, driving force, due to which it's going up. In the downward direction, opposing force. Now, I'm lifting this marker fastly. That means driving force is far, far, far greater than opposing force. And in case of irreversible processes, which are fast processes, wherein driving force is far, far, far greater than opposing force. Right? I'm just giving you the analogy. Now, tell me one thing. Imagine I'm lifting this marker up slowly. I'm lifting this marker up. Slowly. What does it mean? It means driving force is greater than opposing force. That's why the marker is going up. But the marker is going up slowly. What does that mean? That means driving force is greater than opposing force only by a small amount. And look at this process. Is it slow or fast? It's slow. Slow processes are called as reversible processes, in which driving force will be greater than the opposing force only by a small amount. This was the analogy to understand reversible, irreversible. Analogy. So basically, whenever from now onwards you hear the term reversible, one thing should strike into your mind. What is that? That is slow. Whenever you hear the term irreversible, one thing should strike into your mind. What is that? Fast. Irreversible fast, reversible slow. Irreversible fast, reversible slow. Okay? Irreversible fast, reversible slow. Right? Now, let's get into the details. Try to understand carefully, people, what exactly I'm going to say. Because something really, really amazing and interesting I'm going to give you. Something interesting which we are going to study. So here I'm writing reversible. Here I'm writing irreversible. Over here you have got a piston. Over here again you have got a frictionless massless piston. On both the sides you have got frictionless massless piston. Okay. Now people, imagine you have got a gas here in this container. Imagine an ideal gas. Here also you have got an ideal gas. Here also you have got an ideal gas. Okay. For example, you have got a lot of sand particles on the top. There are a lot of sand particles on the top. Over here you do not have sand particles. You have got a block. It is a block which is present at the top. Okay. Now people, first thing. I'm assuming this piston is right now at rest. First of all, tell me how many forces are experienced by this piston. Or in other way, I can say, how many pressures are experienced by this piston. I'll say these internal gas molecules will be colliding it. So there'll be internal pressure in this direction, which is what you call as P gas. So this is P gas. Okay. And then from the top, there will be P external. So two pressures are basically experienced by this piston. Similarly, over here, from the top, there is external pressure. And from this direction, it is pressure of the gas. So in both the ways, in both these cases, I can say two pressures are experienced by the piston. Okay. One due to the gas which is there in the container, one external. One pressure in upward direction due to the gas, one external. Okay. First of all, tell me one thing. What about the external pressure? What about the external pressure here in the first case? Can I say the external pressure in the first case is due to atmospheric pressure plus pressure due to sand? Yes. And here in the second case, I'll say the external pressure is due to atmospheric pressure plus pressure to block. This understood, I believe. This understood, right? Now guys, imagine that, just to make things clear, imagine that this piston is at rest. When can be the piston at rest? Piston will be at rest when P gas and P external will be equal. I'm assuming initially the external pressure was, for example, 5 atm. For example, the external pressure initially was 5 atm. If the piston is at rest, that means external and internal pressure, they are equal. That means at that point of time, internal pressure would have been also how much? Internal pressure would have been also 5 atm. That's why the piston was at rest. Okay. In the beginning, I'm assuming this piston is at rest, right? That means whatever is the external pressure, same will be the internal pressure. If the external pressure is 5 atm, that means internal pressure will be also 5 atm. At that point of time, I would say the piston is at rest. Okay, point number one. Point number two. I'm assuming initially, here in this case, P external is equal to what? Is equal to P gas, and both are equal to 5 atm. Correct? That means the piston is at rest. So I would say system and surrounding are at equilibrium right now. System and surrounding are at equilibrium. Now what exactly am I doing? Understand one thing, guys. This 5 atm, out of this 5 atm, imagine that 4 atm was due to sand and 1 atm is your atmospheric pressure, which is constant. The 5 atm external pressure is divided in two categories. One, pressure due to sand, and this is your atmospheric pressure. 4 plus 1 makes it 5. Okay. Now imagine that what you are doing, you are lifting the one sand particle up. If you are lifting one sand particle, that means pressure due to sand is decreasing slightly. Imagine now it is 3.99, and this again the same 1 atm. Right? What you have done? You have lifted one sand particle. Now the external pressure, initially it was 4 plus 1, 5. Now it is 4.99. This plus this. Now it is 4.99. Now the external pressure is 4.99. Initially, external pressure as well as P gas were 5, 5. Now, external pressure is decreased slightly. If external pressure is decreased slightly, can I say pressure difference got created between the system and surroundings? And I'll say if the pressure difference got created, since you have lifted one sand particle, initially the external pressure was 5 atm. Now you have lifted one sand particle. Now the external pressure is 4.99. And I say this piston will slightly go upwards, right? It will slightly go upwards and stop. It will go upwards slightly till the pressure of the gas also reaches 4.99, right? Initially, the internal external pressure both were 5 atm. Now you have lifted one sand particle. External pressure now is 4.99. Internal pressure is still 5. So pressure difference got created. So piston will slightly go up so that internal external pressure again becomes equal. And piston will go up until internal pressure becomes again 4.99 only. Correct? Right, people? So I would say one simple thing. Piston moved up slowly, right? Piston moved up and stopped. Okay? Now, if you take one more sand particle, now pressure due to sand is 3.98. Atmospheric pressure is still same. Now the external pressure, which was 4.99, now the external pressure will be 4.98. Internal pressure is still 4.99. Again, there is the pressure difference. Again, the piston will slightly go up and will stop till internal external pressure again becomes equal. If you take one more sand particle, right, this becomes 3.97, for example. This is still the same, 1 atm, right? Now the external pressure is 4.97. Piston will again go up till the external internal pressure becomes equal. So what is happening? The piston is slowly going upwards. And when the piston is going upwards, I'll say volume of the container is increasing. Increase in the volume is something which you call as expansion. So is this expansion here slow or fast? This is slow. Can I say at every point of time, your P gas and P external are almost equal? At every point of time, your P gas and P external are almost equal. At every point of time, they're almost equal, right? Can I say at every stage, your system and surroundings are at equilibrium? And you know, the general result to calculate work, it used to be minus integral V1 to V2. It used to be P external multiplied by dV. Now, if P external, P gas are almost equal. So here, instead of P gas, instead of P external, can't we write V1 to V2? This is P gas multiplied by dV, right? So work done in case of reversible processes is equal to minus integral V1 to V2, and here it is P gas multiplied by dV. I hope all these things are clear, right? So slowly, one by one, you are removing the sand particle. The piston is slowly going upwards. Piston, when you removed first sand particle, piston went upwards, stopped. Again one more, piston moved upwards, stopped. Again one more removed, piston moved upwards, stopped, right? Yes? Right, people? Is it clear? So this expansion which is happening here, tell me, is this expansion happening against constant external pressure or variable external pressure? Tell me that. Slowly you are removing one particle. So external pressure is slowly varying. So I would say over here in this particular case, expansion is happening against variable external pressure. Against variable external pressure, right? Okay. Now guys, in case of irreversible, here you do not have sand. There's a block. So your external pressure is basically pressure due to block. I mean your atmospheric pressure plus pressure due to block. I'm assuming initially this external pressure is, for example, 5 atm, out of which 4 atm is due to block and 1 atm is due to atmosphere, which is constant. Atmospheric pressure is constant. Okay. I'm assuming the piston is right now at rest. That means internal external pressure are equal, right? Okay. So initially, system and surroundings are at equilibrium. System and surroundings are initially at equilibrium. System and surroundings are initially at equilibrium. Okay. Now guys, imagine that suddenly you are lifting this block up. Suddenly you are lifting this block up. That means suddenly this pressure is removed. Suddenly you are lifting this block up. So suddenly this much pressure is removed, right? Initially, the internal, since the piston was at rest, so internal, external pressure both were equal to 5 atm. Now suddenly you removed a block. So suddenly you removed 4 atm from the top. Now from the top there is only 1 atm. But from the bottom there is still 5 atm. So there is a lot of pressure difference. Can I say when you remove the block, the piston will suddenly go upwards? And when the piston will be going upwards, it will be going upwards against what? Only against atmospheric pressure. There will be only atmospheric pressure acting upwards, right? Acting from this direction. So when you remove the block, the piston is going upwards. Expansion is happening. Expansion is happening against constant external pressure of 1 atm here, right? Right, people? Expansion is happening against constant external pressure of 1 atm. And when you remove the block, piston suddenly moved upwards, right? So can I say in this particular case, your driving force was far greater than the opposing force? Was the process slow or fast? It was fast. Perfect. And when you remove the block, sudden expansion happened. Piston suddenly went upwards. And piston went upwards till the internal external pressure again became equal. Till the pressure of the gas became equal to 1 atm. And when the pressure of the gas also became equal to 1 atm, right? When the pressure of the gas also became equal to 1 atm, the piston would have come at rest. So again, system and surroundings would have been at equilibrium at that point of time, at the final state. So at the final state, your system and surroundings again are at equilibrium. At final state, system and surroundings again are at equilibrium. So this expansion is happening against what? Against constant external pressure. Against constant external pressure. That's what I told you. In case of irreversible process, external pressure is constant. If external pressure is constant, take it outwards. So you get the formula to calculate work done, which is minus P external delta V, right? So are these two processes clear to you? Let me know in the chats quickly. Are these processes clear? So are all these points clear? Reversible means slow. P gas and P external almost equal. Right? Perfect. System surrounding always equilibrium because slowly it's going upwards. When I'm talking about fast expansion, at that time system surrounding, they are at equilibrium only at initial and final state. Okay? Perfect. So guys, let me quickly summarize it. Something which you have to remember, nothing apart from that. Something which you have to remember, nothing apart from that. Imagine I've taken a container. This is a container. Over here you have got a piston, right? There is a gas here. There is an ideal gas here. The piston is at point A. Okay? Let's assume volume of the container right now is 2 liters. That means volume of the gas is 2 liters because ideal gas occupies the volume of container. Now imagine the piston has to go from A to B. When the piston reaches B, volume of the container is increasing. That means volume of the gas is increasing. Assume that is 8 liters. So first of all, initial volume of the gas was 2 liters. Final volume has to be 8 liters. The piston has to move from A to B. So can you let me know how many liters of expansion do we have to do here? Can I say we are doing the expansion of 6 liters? Can I say I'm going to do the expansion of 6 liters? Now this 6 liters of expansion, it can be carried out in two ways. Reversibly or irreversibly. When the piston will be going outwards slowly, that means the expansion is irreversible. When the piston will be going outwards suddenly, that means the expansion is irreversible. Okay, expansion is irreversible. Guys, here I'm going to give you one statement which is very important. Okay, this is something which I believe you all know. Magnitude of work done is equal to area under PV curve. Do you know this? Area under PV curve gives you the magnitude of work done. You would have studied this in physics as well. Area under PV curve gives us the magnitude of work. I am going to represent the same scenario on a graph, which will make you understand some basic things. Say, initial volume of the gas was 2 liters. Final volume of the gas is 8 liters. So volume is increasing. So imagine the initial pressure of the gas was, for example, 8 atm. Final pressure of the gas is, for example, 2 atm. Okay, for example. At point A, the volume of the gas is 2 liters. Pressure of the gas is 8 atm. At point B, volume of the gas is 8 liters. Pressure is 2 atm. If I draw the things graphically here, how exactly? Understand. For example, this is pressure on one side. There is volume on another side. Let's say this point represents 2 atm. And this point represents 8 atm. Okay. This point represents 2 liters. And this point represents 8 liters. Correct? Initially, the piston was at point A, where the volume was 2 liters, pressure was 8 atm. Volume was 2 liters, pressure was 8 atm. That means this point I'm talking about. This is your point A. Now, finally, the piston is reaching at point B, where volume is 8 liters, pressure is 2 atm. Volume is 8 liters, pressure is 2 atm. Means this will be your point B. So basically, we are moving from A to B. We have to move from A to B. Now, I am moving from A to B first through a reversible path, then through an irreversible path. If I am moving from A to B through reversible path, that means the piston is slowly going outwards. If the piston is slowly going outwards, can I say pressure of the gas is slowly decreasing and volume of the gas is slowly increasing? Pressure of the gas is slowly decreasing from 8 atm to 2 atm and volume is increasing. This is the curve which represents that path, which is my reversible path. Right? Pressure is slowly decreasing, volume is slowly increasing. Now, if in order to go from A to B, in order to move from A to B, you are choosing the irreversible path. In irreversible, what happens? Piston will be suddenly going outwards. That means the pressure of the gas will be suddenly decreasing and at the same time, volume of the gas will be suddenly increasing. Pressure of the gas will be suddenly decreasing from 8 to 2 and volume will be suddenly increasing from 2 to 8. Pressure is suddenly decreasing from 8 to 2, from here to here, and volume is suddenly increasing from here to here, right? So this particular path, is it reversible or irreversible path? This is your irreversible path. This is your irreversible path here, okay? This is your irreversible path. So I moved from A to B by following two paths. One is reversible and one more is irreversible. Perfect. One more is irreversible. Now, as I told you, area under curve gives us the magnitude of work. What is the area under reversible curve? Area under reversible curve here is this much. This is the area under reversible curve. What is the area under irreversible curve? Nothing. This is the area under the reversible curve. Sorry, irreversible curve. So where do you see area under the curve more? Where do you see area under the curve more? Can I say area under reversible curve is more? Area under reversible curve is more, right? Yes. If area under a reversible curve is more, can I say magnitude of work done during reversible expansion is coming out to be greater than that of magnitude of work in irreversible expansion? Right? Right, people? So let me summarize it in the form of a statement. I'll say for the same amount of expansion, magnitude of work done in a reversible expansion is greater than that of magnitude of work done in case of irreversible expansion. Yes? Is this point clear to everyone? So I was doing the expansion. Now expansion can be done in two ways, either slowly or fastly. Slowly means reversibly, fastly means irreversibly, right? In both the cases, whether you want to do the expansion reversibly or irreversibly, in both the cases work is done by the system. But work done by the system during reversible expansion will be more than that of work done by the system during irreversible expansion. That is the point, right? Similarly, this is something which you can conclude on your own. For the same amount of compression, whenever there is compression, decrease in the volume. Compression can also be carried out in two ways, slowly and fastly. Slowly means reversibly, fastly means irreversibly. In both the cases, work is done on the system, right? But do remember, for the same amount of compression, magnitude of work done on the system in case of irreversible compression is greater than that of magnitude of work done on the system in case of reversible compression. These are two very important points which you will have to remember. Okay? And how do you remember it? For that, I'm asking you certain questions and you will have to answer the questions in the chats. Imagine I'm doing 5 liters of expansion. Now this particular expansion can be carried out in how many ways? 2 ways. Either I'll be doing this expansion reversibly or I'll be doing this expansion irreversibly, right? In either case, in both the cases, work is done by the system. Now tell me, where is the work done by the system more? Magnitude of work done by the system in reversible expansion will be more than that of magnitude of work done in irreversible expansion. Now imagine I'm doing 5 liters of compression. 5 liters of compression. This compression again can be done in 2 ways, either reversibly or irreversibly. But we already know whenever there is compression, work is done on the system. Whether you are doing the compression reversibly or irreversibly, work will be, in both the cases, work will be done on the system. But here in this particular case, magnitude of work done on the system in irreversible compression will be greater than that of magnitude of work done on the system in reversible compression. Is this particular point clear to you? Quickly in the chats. Is it clear, guys? Is it clear? Everyone in the chats. I believe it's clear. I believe it's clear. Okay. Now, this reversible, irreversible will be using everywhere. But please and please do remember these two statements. These are very important. These are very important, guys. Yeah? All clear? All clear, people? All clear, guys? Yeah? Let me do quickly. Break. Wait for the break, guys. Don't do this. Don't do this. Okay. Let's move on now to different types of thermodynamic processes, which we are going to deal one by one. Okay. I think the electricity has come. Now it's okay. All right. Now, guys, the first type of process which we have to discuss, that is your isochoric process. Isochoric process. First of all, tell me, when do we say that the ideal gas is undergoing isochoric process? When do we say that the ideal gas is undergoing isochoric process? Whenever you change the state of the gas, whenever you change the state of the system. And during the change in state, if volume of the system does not change, we say that the system is undergoing isochoric process. So first of all, volume will be constant. If volume is constant, delta V, change in volume has to be 0. What about the work done? Work is your basically minus P external delta V, right? If delta V is 0, that means W value is 0, right? If the piston is not moving at all, if the piston is not moving, neither going outwards nor inwards, there'll be no exchange of energy in the form of work. There'll be no exchange of energy in the form of work, right? So do remember, in case of your isochoric processes, your W value will be 0 always. Okay. Now, if you use the first law of thermodynamics, first law says delta U is equal to Q plus W. Right? First law says delta U is equal to Q plus W. Now, at constant volume, that means for isochoric processes, W value is 0. So delta U has to be equal to QV, right? Perfect. Delta U has to be equal to QV. Yeah. And this is something which we already discussed. And delta U for the ideal gas is nothing, that is NCV delta T. All these things are already discussed. Okay. All these things are already discussed. So I'm not going to waste any sort of time with isochoric processes. Directly we'll go into what? Directly we'll go into isobaric processes. You know its graph as well. We have discussed that. You know its graphs, etc., etc. Okay. If I ask you what is the significance of this equation, delta U is equal to QV, what does it mean? Look at the equation carefully. Look at the equation carefully. Guys, if I say Q is positive, that means delta U is positive. If I say Q is positive, that means delta U is positive. Q positive means heat absorbed. Delta U positive means internal energy is increasing. Q positive means heat is absorbed. Delta U positive means internal energy is increasing. What does that mean? It means whatever heat is absorbed by the system, entire amount of heat over here is used to increase the internal energy of the system, right? In case of isochoric processes, at constant volume, whatever heat you'll be supplying to the system, all that heat is utilized to increase the internal energy of the system, right? And if the internal energy is increased, that means temperature of the system will automatically increase. So indirectly, I can say, in case of isochoric processes, when the volume of the system is constant, at that point of time, whatever heat you are supplying to the system, that entire amount of heat is used, increase the temperature of the system. I hope this is clear. I hope this is clear. I'm writing it in the form of a statement. At constant volume, all the heat absorbed is used to increase the internal energy of the system. All the heat absorbed is used to increase the internal energy, or I'll say temperature of the system. Okay? Perfect, guys. This is one important statement. Do you remember this? Perfect. Do you remember this particular statement? It's important. It's important. Now, similarly, guys, understand it like this. Understand this equation like this. If Q is negative, that means delta U is negative. Delta U negative means internal energy is decreasing. Internal energy, if it is decreasing, that means temperature will be also decreasing, because internal energy is directly proportional to temperature, right? If Q is negative, that means heat is released. Heat is released by this system. That means at constant volume, if the system releases heat, that will directly impact your internal energy. If the system is releasing heat, right, due to which what is happening? Internal energy of the system is decreasing, and eventually temperature of the system is decreasing. Just the reverse of this statement. So whatever heat is released by the system at constant volume, that is directly impacting the internal energy of the system. Okay, and that is directly impacting the temperature of the system as well. Okay. Let me know once in the chats if this particular statement is clear. Everyone, guys. Everyone. Is it clear? All right. So let's move on to something called as isobaric process then. Isobaric process. What are your isobaric processes? When do we say that ideal gas is undergoing isobaric process? Tell me that. When do we say that ideal gas is undergoing isobaric process? During the change in the state of the gas, if pressure of the gas does not change, if pressure of the system does not change, we say the system is undergoing isobaric process. So if pressure is constant, what does that mean? That means change in pressure, delta P has to be zero. Now, how do we calculate work done here? It is simply going to be minus P external delta V. Right? Now, at the same time, as per your first law, delta U is equal to Q plus W. If I write this equation at constant pressure, what do I get? I get delta U is equal to QP plus W. Perfect. QP plus W. Or I can say delta U. W is minus P delta V, so this is plus P delta V is equal to QP. Do you remember delta U plus P delta V used to be called as delta H, which we already knew. So here is one more proof how your QP is equal to delta H. Already we have discussed this. And if you remember, in case of your ideal gas, delta H is nothing. That is NCP delta T. For the ideal gas. Correct? That is NCP delta T. Okay, that's NCP delta T. Now guys, if you look at this particular equation, look at its significance. I can say QP is equal to delta U plus W. What is the significance of this particular equation? Significance. Try to understand what it means. I can say at constant pressure, heat absorbed by the system heat absorbed by the system is utilized. Heat absorbed by the system is utilized in two ways. Is utilized in two things. Is utilized in two things. Some part of heat absorbed is going to increase the internal energy of the system, and some part of heat absorbed is going to be utilized in order to perform the work. Right? So whatever heat we are supplying to the system at constant pressure, whatever heat will be supplying to the system at constant pressure, that entire amount of heat, some part of that will be used to change the internal energy of the system, and some part of that heat will be used to perform work. Okay? Do remember it as such. People. And already we have discussed one thing. I mean, the graphs, etc. we have discussed. Here, one extra thing we'll be discussing, and I'll be showing you the questions. What is that? I'm writing here calculation of work done. Calculation of work done in an open container. Work done in an open container. This is again one important topic. And here, see what it's all about. Few things you'll remember here, you're done. Imagine that this is the container which we have, and this is open on one side. In this container, imagine the reaction is like this. We have got a reaction carried out in this container. N1A gas plus N2B gas. It gives, for example, N3C gas plus N4D gas. Imagine this is the reaction which is carried out here in this particular container. Whenever you see any sort of question wherein the process is carried out in an open container, whenever you see any type of this particular scenario, this is what we call as open vessel concept, by the way. Whenever you see any sort of process, taking place in an open container, consider the process to be isobaric. And how do we calculate work done here in this particular case? Minus delta NGRT. I'm not deriving these results, I'm just giving you the results. Whenever you see a process, a reaction happening in an open container, take it isobaric, right? And how do we calculate work done in this case? It's going to be minus delta NGRT. For example, let me give you certain questions so that you can understand it. This is the first question which is on your screen. What do you think about this? Give it a try. What do you think about this question? Quickly. What do you think about this question? Quickly, guys. What do you think about this particular question? 1 mole of aluminium is dropped in an aqueous solution in an open container. It's mentioned that whatever is happening, that's happening in an open container. If it is happening in the open container, so you will consider it to be isobaric in nature, right? Pressure you'll take as a constant, right? So people, as per the question, we have got 1 mole of aluminium which is dropped in an aqueous solution in an open container containing HCl. If 95 calories of heat is released during the process, calculate W, delta U and delta H, right? These are the 3 things which we have to calculate. First of all, say this particular process is happening in an open container. First of all, it is happening in the open container. If it is happening in the open container, how do I calculate work done? I gave you the result few minutes back. W is nothing. That is your minus delta NGRT, right? So first thing, calculate delta NG for the reaction. Delta NG has to be equal to number of moles of gaseous products, which is 3/2, minus number of moles of gaseous reactant, which is nothing. So it is 3/2 only. So delta NG is basically 3/2. Okay. Delta NG is 3/2. After getting the delta ng, calculate the work done. It is equal to minus delta ng is 3 by 2, right? Let's say we have to get all the things in calories. If all the things are to be calculated in calories, so our value in calories is 2 calories per Kelvin per mole. Temperature is given to me as how much? Temperature is given to me as 300 Kelvin. So this and this got cancelled. So W value came out to be minus 900 calories. This is the value of W which we calculated. This is the value of W which we calculated, right? Now, my dear students, since we calculated the W value, if you look at the question carefully, this process is happening in an open vessel, so constant pressure, right? Heat absorbed or released at constant pressure is represented by QP. As per the question, 95 calories of heat is released. So can I say this much amount of heat is released at constant pressure basically? And heat released at constant pressure or heat absorbed at constant pressure is represented by QP. Correct? So it will be equal to 95. But since heat is released, so sign has to be minus. So it's minus 95 calories. So QP is equal to minus 95 calories. Perfect. Now you already know QP is nothing, that's your delta H. So indirectly you calculate delta H here. Now you got Q, you got W. You can calculate delta U as well. Delta U is equal to Q plus W. Right? So I'll say delta U is equal to, this is minus 900, this is minus 95. The value is minus 995 calories. So delta U is nothing but minus 995 calories. Is it clear? Is it clear, people? Is it clear to everyone? Yes. So first of all, this particular process is happening in an open vessel. Open vessel means constant pressure. Calculate W minus delta ng RT. Heat is released. 95 calories of heat is released at constant pressure. That means QP is given. So Q, W, delta U can get easily. Right? Few more questions. Okay, look at this particular question. Can't you solve this one? Can't you solve this one? Calculate the work done in the complete decomposition of 5 moles of PCl5. Assume this is happening in an open container, okay? Assume it to be happening in open container. So this particular process is happening in an open container. So it is again an open vessel concept. Pressure is constant. How do I calculate work done? It is simple. Minus delta ng RT. How do I calculate delta ng? Number of moles of gaseous products, which is 1 plus 1, 2. Minus number of moles of gaseous reactant, which is 1. So delta ng is 1. If delta ng is 1, calculate the W value. W is minus delta ng is 1. R value is 2 calories per Kelvin per mole. Temperature is 300. The value is going to be minus 600 calories. But is this going to be the final answer? Is this going to be the final answer? No. This is the value of W for the decomposition of 1 mole of PCl5. But as per the question, we are not doing the decomposition of 1 mole of PCl5. We are doing the decomposition of 5 moles of PCl5. So this is the value of W for 1 mole of PCl5. So tell me, what will be the value of W for 5 moles of PCl5? It will be 600 multiplied by 5. The value will come out to be minus 3000 calories. This is the exact value of W for the decomposition of 5 moles. This sort of equation you will have to solve. Yeah. I mean, whenever this sort of a question comes, you should be able to solve this question as well. Okay. Look at the other one. Look at the other one. 5 moles of N2H4. 5 moles of N2H4 undergoes complete decomposition at 27 degrees centigrade in an open vessel. Okay, modify the equation. Write it as in an open vessel. In an open vessel. Calculate work done in calories. How are you going to solve this? Since it is mentioned that the process happening in an open vessel, so it is an open vessel concept, so pressure constant. If pressure is constant, you already know how to get the W. You already know how to get the W. W is simply going to be minus delta ng RT. Calculate delta ng for the process. Delta ng is equal to number of moles of gaseous products, which is 4 plus 1, 5, minus Number of moles of gaseous reactant, that is 0. Delta Ng value comes out to be 5. If delta Ng is 5, so W has to be minus 5. R value is 2 calories per Kelvin per mole. Temperature is how much? 27 degrees centigrade, that means 300 Kelvin. The value comes out to be minus 3000 calories. But is this the final answer? Is this the final answer? Look at it carefully. This is the value of W. This is the value of W for the decomposition of 3 moles of N2H4. As per the question, when we do the decomposition of 3 moles of N2H4, W value is coming out to be minus 3000 calories. Right? This is something which we got to know. If I use the unitary method, when we do the decomposition of 1 mole of N2H4, what will be the value of W? It will be minus 3000 divided by 3. It will be minus 1000 calories. Right? But as per the question, are we going to do the decomposition of 1 mole of N2H4? No. As per the question, we have to do the decomposition of 5 moles of N2H4. So I'll say when 5 moles of N2H4 undergoes decomposition, the value of W has to be multiplied by 5. So the final answer is going to be minus 5000 calories. Is it clear? So first of all, you have to look in the question for how many moles you are doing the decomposition. Is it clear? Is it clear, guys? Coming to your isothermal process, but before doing the isothermal process, I think we should have the dinner first, right? Let's have the dinner first and let's get back in some time. Okay? How much time do you need? It is, yeah, it's 10:30 already, but I want every one of you to be back. We have to complete this chapter, guys. Okay, we have to complete this chapter. And there are a lot of other things to be discussed as well. Dinner cannot be done in 10 minutes. Okay? I want you guys to be back. Then it's going to be fun. Otherwise, it was not going to be fun at all. Chalo, it is right now 20 to 33. That means 10:30. So break till dinner break. Okay. So session will resume at 11:10 sharp. Session will resume at 11:10 sharp. And I would want every one of you to be back on time. Okay. Go have dinner and come back fast. I'll also have my dinner and come back. Perfect. Chalo guys. See you after the dinner. Bye-bye. Is everybody back? Is everyone back, people? Yes? Done with the dinner? Done with the dinner? Okay, that's great. That's great, guys. That's great. Perfect. So, should we start then? Should we start? Should we start? Should we start? Yeah, I want some Josh in the chats, people. I want some Josh in the chats. That's great. Perfect. So let's start now with the isothermal process. This is the topic from which, like, I would say this is the short topic of the chapter thermodynamics. Okay. From this particular topic, questions are frequently asked. Isothermal processes, adiabatic processes, cyclic processes, right? These are the favorite topics of this particular thermodynamics chapter. So let's talk about them one by one. Okay. All right, people. So as the name speaks itself, isothermal process. First of all, when do we say that the system is undergoing isothermal process? When do we say? As I've told you already, when I gave you the introduction of the thermodynamic processes, I told you, when the state of the system changes, when the system undergoes a change in state, and during the change in the state, if the temperature of the system does not change, whenever during the change in the state of the system, temperature of the system does not change, we say system is undergoing isothermal process. So whenever a system undergoes isothermal process, I can say at that point of time, temperature of the system remains constant throughout the process. If temperature is constant, what does that mean? That means delta T, change in temperature has to be zero. Change in temperature has to be zero. As you all must be knowing, for an ideal gas, delta U is equal to NCV delta T. If delta T is zero, that means delta U for the ideal gas undergoing isothermal process, that will be zero as well. Similarly, delta H for the ideal gas, you know, that is NCP delta T. If delta T is zero, that means delta H has to be zero as well. Perfect. It has to be zero as well. Now, my dear students, as per your first law of thermodynamics, delta U is equal to Q plus W. Delta U is equal to Q plus W. And we know the ideal gas undergoing isothermal process, its delta U is zero. If delta U is zero, that means Q is equal to minus W. This particular result, it's not valid everywhere, but it is valid when the ideal gas undergoes isothermal process, right? So whenever you see an ideal gas undergoing isothermal process, its Q will be always equal to minus W. Okay. Now, people, few important parameters related to isothermal processes. Understand one by one. Understand one by one. As I told you, when the ideal gas undergoes isothermal process, its Q has to be equal to minus W. Perfect. Its Q has to be equal to minus W. Now, people, let's try to analyze this particular equation. First of all, the value of W over here, it can be negative, right? W value can be positive as well. And we already know, whenever W comes out be negative, that means system is undergoing expansion. System is undergoing expansion. And whenever W value is positive, we know that the system is undergoing compression. System is undergoing compression. Now you are going to tell me, If the value of W comes out to be negative, if W is negative, I'll say negative and negative makes it positive. So I would say Q value will come out to be positive. What is meant by Q positive? Q positive means heat is absorbed by the system. Heat is absorbed by the system. Heat is absorbed by the system. In the similar way, if W is positive, positive negative makes it negative. So Q value will come out to be negative from here. Q value will come out to be negative from here. And the meaning of Q negative means system releases heat, or I can say heat is released by the system. Now people, over here I can generalize two statements. Two important statements I can generalize. First of all, this particular equation is valid for the ideal gas undergoing isothermal process. Now, either there will be isothermal expansion of the gas or there will be isothermal compression of the gas. During isothermal expansion of an ideal gas, heat is always absorbed by the system. During isothermal compression of an ideal gas, heat is always released by the system. I'll tell you its physical significance as well. But before that, I would want you guys to write two statements. Statement number one. During isothermal expansion, of an ideal gas, heat is absorbed. Heat is absorbed by the gas. Statement number two. During isothermal compression, heat is released by the gas. Heat is released by the gas. These are two very important statements, my dear students, which directly from now onwards you are going to remember. Now the point is, how do we justify these statements? What is the physical significance of these two statements? Let's get to know about that as well. That is something which is very important. Try to analyze things carefully. For example, this is the container which I'm taking, and over here you've got a piston. And imagine this is the ideal gas in the container. Okay, imagine this is the ideal gas in the container. Assume that the piston was initially at point A, wherein volume of the container, for example, was 2 liters. Let's say when the piston was at point A, volume of the container was 2 liters. That means volume of the ideal gas was 2 liters, because ideal gas occupies the volume of container in which it is kept, right? Now imagine, my dear students, the piston has to go from point A to point B. Imagine the piston has to go from point A to point B. And when the piston reaches point B, that means the volume of container has increased. Let's assume volume of the container here is 10 liters. That means the volume of the gas here is 10 liters, correct? So guys, try to understand. Initially, the volume of the gas was 2 liters. Finally, the volume of the gas is 10 liters. That means the volume of the gas is increasing, right? So what are we doing exactly? We are doing expansion, right? Can I say we are doing the expansion of in total 8 liters? We are doing the 8 liters of expansion, correct? During the expansion, I am making sure that temperature of the gas remains constant. If during the expansion temperature of the gas does not change, then I'll be calling this expansion as isothermal expansion. If during the expansion temperature of the gas does not change, I'll be calling this expansion as isothermal expansion. Now people, what happens during isothermal expansion? Try to understand. What happens during isothermal expansion? As I told you already, during isothermal expansion of an ideal gas, heat is absorbed by the gas. Why is that? Try to analyze things. Try to understand things. When the piston was at point A, how many pressures were being experienced by the piston? I'll say 2 pressures. This was pressure of the gas. This was P external. This was P external. Correct? Now people, expansion is happening. Piston is going from A to B. Whenever there is expansion, work is done by the system. So when the piston is going from A to B, work is done by the system against this P external, right? Piston is going from A to B, but over here you have got opposing pressure, right? But still the piston is going. That means work is done by the system against what? Against this external pressure. Work is done by the gas against the external pressure. Now, if you use the common sense, during the expansion, if work is done by the system, if work is done by the gas during the expansion, normally what should we think? We should think like this. If during the expansion work is done by the gas, that means the gas will be using some of its energy during the expansion. This should be the first point which should strike our mind. During the expansion, work is done by the gas. If gas is performing work on the cost of what? I'll say gas will be performing work on the cost of its internal energy. Gas will be utilizing some part of its internal energy for the work. Right? Now, if the gas utilizes its internal energy for the work, if the gas during the expansion, if the gas utilizes its internal energy for the work, what will happen? Can I say during the expansion, internal energy of the gas will keep on decreasing because some part of internal energy gas is using for work? And if internal energy of the gas decreases with time, if internal energy of the gas decreases with time, that means temperature of the gas has to decrease with time, right? Temperature of the gas has to decrease with time during the expansion. But do we have to let the temperature of the gas to decrease? No, we do not have to let the temperature of the gas to decrease. We do not have to let the internal energy of the gas to decrease. For that purpose, we have to continuously supply heat to the gas such that its internal energy does not decrease, such that its temperature does not decrease, right? So can I say during the isothermal expansion of the ideal gas, heat is absorbed by the gas. Why? To keep the internal energy constant, to keep the internal energy maintained, and to keep the temperature maintained. Is this clear to everyone? Is this clear to everyone? If you do not supply heat to the gas, if the gas does not absorb heat during the expansion, its temperature will decrease, its internal energy will decrease, but we are not supposed to let the internal energy or temperature of the gas to decrease. So for that purpose, we'll be continuously supplying heat. Is it clear? Yes, I believe yes. Now, second point. Second point, people. Second point. Imagine this is the container, right? And the piston is right now at point A. The piston has to go from point A to point B. The piston has to go from point A to point B. So what is happening? Decrease in the volume. Compression is happening. Compression is happening, right? When should I call this compression as isothermal compression? When should I call it as the isothermal compression? Whenever, if during the compression, temperature of the gas does not change. If during the compression, temperature of the gas does not change, then only I should be calling this compression as isothermal compression. And as I told you already, during isothermal compression of an ideal gas, heat is released by the system. How can we justify this? Heat is released by the system. Try to understand. My dear students, when the piston will be going from A to B, that means decrease in the volume, compression. Compression is happening. Whenever compression is happening, whenever compression will be happening, is work done by the gas or work done on the gas? During the compression, work is done on the gas. Normally, I should think like this. Understand. During the compression, I'm telling you work is done on the gas. And whatever work is done on the gas, it should be stored in the gas in the form of its internal energy. Right? What is work? It is a mode of transfer of energy. During the compression, work is done on the gas. And whatever work is done on the gas, that work should be stored in the gas in the form of internal energy. Due to which, what should happen? During the compression, I would say internal energy of the gas should increase, right? During the compression, I should say internal energy of the gas should increase. And you know internal energy is directly proportional to temperature. If during the compression, internal energy of the gas should increase, that means temperature of the gas should increase, right? But do we have to let the temperature of the gas to increase? No. For that purpose, the gas should continuously release heat. Then only its internal energy and temperature will be maintained, right? Perfect. So can I say during isothermal compression, heat is released by the gas to maintain its internal energy and to maintain its temperature? I believe it's clear. Yes. So these two statements, I'm pretty much sure, are clear to you. Okay. So whenever ideal gas undergoes isothermal expansion, heat will be absorbed by the gas to maintain its internal energy and temperature. Similarly, whenever an ideal gas undergoes isothermal compression, heat will be released by the gas, right, to keep its temperature and internal energy constant. Yeah? Perfect? Perfect, people? All right. Now I'm going to give you one more statement. After that, we'll be using some mathematics, right? I'll be giving you one more statement. You have to tell me the answer. You have to tell me the answer. And over here, you will have to use your brain properly. You will have to use your brain properly, right? Be completely attentive in the class right now. Imagine I'm doing 5 liters of expansion. Let's say the expansion is isothermal. Imagine I'm doing the 5 liters of isothermal expansion. So that means heat will be absorbed by the system. During expansion, isothermal expansion, heat is absorbed. Now this isothermal expansion, the expansion can be done in 2 ways. You know it. Expansion can be done in 2 ways. Either the expansion will be happening reversibly or the expansion will be happening irreversibly. We know it. Either expansion will happen reversibly or irreversibly. Now we already know magnitude of work done by the system in reversible expansion is greater than magnitude of work done by the system in irreversible expansion. We know it already. During reversible expansion, the gas will be doing more work. If the gas will be doing more work, in reversible expansion, can I say gas should consume its internal energy more? If the gas should consume its internal energy more, can I say temperature of the gas should decrease more? But do we have to let the temperature of the gas to decrease? No. So can I say, no matter, in both these processes, heat will be absorbed by the gas. Can you let me know where will be the magnitude of heat absorbed more by the gas? Can you let me know where will be the magnitude of heat absorbed by the gas more? In reversible or irreversible? What do you think? You have to use your brain, people. Again, I'm repeating the same thing. Understand properly. Understand properly. I'm doing the expansion for 5 liters. And the expansion is isothermal in nature. This isothermal expansion can be done reversibly or irreversibly. These are the 2 paths which I have, right? But we know magnitude of work done in reversible expansion is more than that of magnitude of work done by the gas in irreversible expansion. We know it already. But we know during the isothermal expansion, heat is absorbed by the gas. So reversibly as well as irreversibly, right? Along both these paths, I would say heat will be absorbed by the gas. Now the point is, where will be the heat absorbed by the gas more? Wherever gas will be performing more work, there only heat absorbed by the gas will be more, right? So as to maintain its temperature. Is it clear? Is it clear? I'm going to write it in the form of a statement. I believe it's clear. Right? Statement will be simple like this. For the same amount of isothermal expansion, heat absorbed by the gas, for the same amount of isothermal expansion, heat absorbed by the gas in a reversible expansion will be more than that of heat absorbed by the gas in irreversible expansion. I believe this point is clear. I believe this particular point is clear, right? Similarly, I'm writing one more statement, and this will be reverse basically. For the same amount of compression, for the same amount of isothermal compression, for the same amount of isothermal compression, it will be magnitude of heat released by the gas in irreversible compression will be greater than that of magnitude of heat released by the gas in reversible compression. Do remember these two statements, people. And I believe you already know their logic now. Yeah? Perfect. Perfect, guys. Now, it is the time to see how to calculate work done in case of reversible isothermal and irreversible isothermal processes. So over here, I'm marking the heading as reversible isothermal process. And over here, I'm marking the heading as irreversible isothermal process. The point is pretty much simple. I have to calculate work done in case of reversible isothermal and irreversible isothermal processes. Okay. First of all, if I ask you, in reversible processes, how do we calculate work? You will say we use the integral minus integral V1 to V2. It is P gas multiplied by dV. This is the general expression which we know. Now, people, W has to be equal to minus integral V1 to V2. P gas will be nRT divided by V, and this is going to be dV. Perfect. So W will be equal to minus N constant, R constant, temperature constant, because it's isothermal, temperature out. Integral of dV by V is ln of V, upper limit, lower limit, so it's ln of V2 divided by V1. This is one of the expressions by means of which you can calculate work done in reversible isothermal processes. Okay. Similarly, people, you can write it like this, minus nRT ln of, instead of V2 by V1, you can write P1 divided by P2. Because you know, isothermal means temperature constant. That means Boyle's law you can apply. So P1 V1 has to be equal to P2 V2. If P1 V1 is equal to P2 V2, you can easily say V2 by V1 is equal to P1 by P2, nothing else. Right? Okay. Perfect, guys. Or you can just do one thing. You can remove the, here I have used ln, convert it into log. It is minus 2.303 nRT. Then it's going to be log of V2 by V1. Or you can say it is minus 2.303 nRT. It's going to be log of P1 by P2. Perfect. So these are the expressions which you have to remember to calculate work done in case of reversible isothermal processes. Reversible isothermal processes. Now, how do we calculate work done in irreversible isothermal processes? In case of irreversible process, generally we know it is minus P external delta V, which is V2 minus V1. Right? This is going to be the first expression, which you can use directly as such. Now, if you want to convert it into one more expression, you can write W irreversible. Work done in irreversible isothermal process will be equal to minus P external as such. This will be equal to, instead of V2, you can write nRT divided by P2. This is going to be nRT divided by P1. Perfect. You can take nRT common as well. No issues at all. So these are the two expressions which you guys are going to use in order to calculate the work done in case of irreversible isothermal process. This is for work done in reversible isothermal. This is work done in irreversible isothermal. Okay. Now, if I show you what kind of questions are asked, let's have a look. Let's have a look, people. This is the simplest among all. This is the simplest among all the questions. Calculate Q, W, delta U and delta H in calories when 2 moles of an ideal gas. So as per the question, we are given with 2 moles of ideal gas are expanded reversibly and isothermally. So gas is being expanded reversibly and isothermally from 10 atm to 5 atm. So initial pressure of the gas is 10 atm and final pressure of the gas is 5 atm. Correct? Temperature of the gas is 27 degrees centigrade. That means 300 Kelvin. And it's mentioned that the process is reversible and isothermal. The process is reversible and isothermal. What do we calculate? We need to calculate Q, W, delta U, delta H. Now, first of all, we know whenever an ideal gas undergoes isothermal process, be it reversible or irreversible, whenever an ideal gas undergoes isothermal process, delta U as well as delta H, both are equal to 0. We have discussed this if you remember. So these two are done. Now, since the ideal gas is undergoing isothermal process, so Q has to be equal to minus W. This is also discussed. So if I calculate W, that means I can easily get Q. How do I calculate W? The process is reversible. And how do you calculate work done in reversible isothermal? How do you calculate work done in reversible isothermal? Minus nRT, it's going to be ln of P2 divided by P1 or P1 by P2. Let me check what expression did we there. What was it? Was it P1 by P2? Yes, it was P1 by P2. It was ln of P1 divided by P2. Correct? Now, just a bit of calculations needed. Minus N value 2. R value in calories is 2. Temperature is 300. Ln of P1 by P2. P1 divided by P2. 10 by 5 is 2. Ln of 2 is given as 0.7. So this is 0.7. When you solve this, the value comes out to be minus 840 calories. This is the value of W. If you got the value of W, that means Q value will be just how much? Q value is minus W. So minus W means Q value will be plus 840 calories. And this is something which already you should know, that W value will come out to be negative. It is mentioned in the question that expansion is happening. And we know during isothermal expansion, heat is absorbed. So Q has to come as positive. Correct? It was understood. It was understood. Look at the other question. Look at this question, people. Look at this question. 2 liters of N2 gas at 0 degree and 5 atm are exploded isothermally against a constant external pressure. Against a constant external pressure. That means the process is irreversible, right? Until the pressure of the gas reaches 1. Calculate how much heat will be absorbed or released. Try to understand what the question says. As per the question, the process is irreversible and at the same time it's isothermal, right? So it is irreversible isothermal process. It is irreversible isothermal process, right? Which I've identified. As per the question, the initial volume of the gas is 2 liters, correct? Initial volume of the gas is 2 liters. The initial pressure of the gas is 5 atm. Now, the gas which you have in the container, it is undergoing irreversible isothermal process. It is undergoing the irreversible isothermal process. Now, as per the question, the final pressure of the gas will be equal to 1 atm. Initial pressure of the gas is 5 atm. Final pressure is 1 atm. Let's assume that final volume of the gas is V2. Right? This is the initial state of the gas. This is the final state. Right? P external is also given. P external. External pressure is also given how much? 1 atm. So expansion is happening against 1 atm external pressure. How much heat will be absorbed or released? Since the process is isothermal, so Q has to be equal to minus W. Right? So in order to calculate Q, I would need W. But is this W reversible or irreversible? This W is irreversible. So we have to calculate W irreversible here. And W irreversible in isothermal process minus P external, V2 minus V1. We know the value of V1. We know the value of P external, but we do not know the value of V2. How do we get the V2 value? If you use the normal Boyle's law, since it's isothermal, temperature constant, so you can use the Boyle's law, right? So I can say P1, V1 has to be equal to P2, V2 in this particular case. So P1 is 5, V1 is 2, P2 is 1, and V2 from here you can calculate. So V2 comes out to be 10 liters, right? If you got the V2 value, you can put it here, right? So it's going to be minus P external. P external is 1 atm. V2 minus V1. V2 minus V1. 10 minus 2 comes out to be 8. The value will be minus 8 atm liter. Minus 8 atm liter. If the value of W is minus 8, so the value of Q has to be minus, which is plus 8 atm liter. Plus 8 atm liter, right? This is the value of Q. If you are supposed to get the answer in joules, then you know what to do. Q is equal to 8, you are writing as such, 1 atm liter is nothing, that is 101.3, and the answer is going to be in joules, right? Depending on the question. depending on the question. Yes? Understood? Understood, people? All right. Now, can you solve this question on your own? I just want you guys to read the question. Because in this question, it is not mentioned whether the process is reversible or irreversible. It's not mentioned. You are just mentioned one thing. One thing is given, that the process is isothermal. But you do not know whether the process is reversible, isothermal, or irreversible. How do you check it? Tell me that. 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 It is a case of expansion. 1 liter to 10 liters. It is a case of expansion. We have to calculate maximum work during the same amount of expansion. Magnitude of work done by the gas in reversible is greater than that of irreversible. So since we have to calculate maximum work, and maximum work will be done when we consider this process to be reversible. So I will have to use which formula? Reversible isothermal formula. Minus nRT ln of either V2 by V1 or P1 by P2. Yeah? So I believe this particular question you can do on your own. It's a homework question. Okay? It is the homework question. Now guys, let's move on to something called as adiabatic processes. Right? Let's move on to adiabatic processes. So first of all, what are adiabatic processes exactly and what kind of questions can be asked? Okay? What are adiabatic processes? Let's try to understand. As I told you already, in adiabatic processes, there is no heat exchange. There is no heat exchange between what? Between the system and surroundings. There is no heat exchange between the system and surroundings. There is no heat exchange between the system and surroundings. What does it mean? That means whenever you'll have a gas, during the expansion or compression, if the gas neither absorbs heat nor releases heat, if the gas neither absorbs heat nor releases heat, we say the gas is undergoing adiabatic process, right? So I would say Q value over here will be equal to 0, right? Heat absorbed or released by the gas is 0. If Q is 0, if I use the first law for the gas undergoing adiabatic process, as per first law, delta U is equal to Q plus W, correct? Now Q has to be 0. If Q is 0, that means delta U is equal to W, right? This particular process is valid in case of what? Which process? In case of adiabatic processes, right? Q is equal to W. Now, if Q is equal to W, what can we conclude from here? Understand what all things can we conclude from here? See, we got to know delta U is equal to W. It's not valid everywhere, this result. This result is valid only when the system will be undergoing adiabatic process. Okay? Try to understand, people. Try to understand. Very carefully. Very carefully. See guys, here two things can arise. Either W value can be positive or the value of W can be negative. Only these two things can arise. Either the value of W can be positive or negative. If the value of W is negative, that means the gas is undergoing expansion. If the value of W is positive, that means the gas is undergoing compression. Right? Now, if the value of W is negative, that means delta U comes out to be negative. That means delta U comes out to be negative. Delta U negative means the internal energy of the gas is decreasing, right? Delta U negative means internal energy of the gas is decreasing. And you know, internal energy is directly proportional to temperature. If the internal energy of the gas decreases, that means temperature of the gas, it decreases too. Temperature of the system decreases. If temperature of the system decreases, I would say system undergoes cooling. I would say system undergoes cooling. From here, I'm going to make two statements after some time. Look at the top. W value positive. If W is positive, that means delta U is positive. If delta U is positive, that means internal energy of the gas is increasing. And if internal energy increases, temperature of the gas increases. Temperature of the gas increases. And if temperature of the gas increases, I'll say system undergoes heating. System undergoes heating. System undergoes heating. Now, two statements we can generalize over here. I can say, during adiabatic expansion of an ideal gas, during adiabatic expansion of an ideal gas, temperature of the gas decreases, due to which the gas undergoes cooling. During adiabatic compression of an ideal gas, temperature of the gas increases and gas undergoes heating. Let me write the two statements, then I'll give you their physical significance as well. See, the first statement. During adiabatic expansion, during adiabatic expansion of an ideal gas, during adiabatic expansion of an ideal gas, the gas undergoes cooling. That means temperature of the gas decreases. Temperature of the gas decreases. Second point. During adiabatic compression, of an ideal gas, the gas undergoes heating. Now, why this happens? You should be able to answer this, by the way, on your own. You should be able to answer this on your own, by the way. See, guys, why it happens. It's pretty much simple. This is the container. Imagine the piston is at point A and you have got ideal gas in this particular container. Now, imagine the piston has to move from A to B. So this is the case of expansion, basically. Increase in the volume. This is the case of expansion. I'm assuming during the expansion, there'll be no heat absorbed or released by the gas. Then only I'll be calling this expansion as adiabatic expansion. Right? Now, people, if you talk about the piston which was at point A, when the piston was at point A, two pressures were being experienced by the piston. This was pressure of the gas. This was P external. When the piston is going from A to B, that means expansion is happening. Work is done by the system. Against what? Against external pressure. If work is done by the system against external pressure, I'll say gas will be doing work against external pressure. For that purpose, gas will be utilizing its internal energy. So for the expansion to happen, the gas will have to utilize its internal energy for the expansion because the gas has to perform work, right? So during the expansion, internal energy of the gas will be decreasing and eventually temperature of the gas will be decreasing, right? Or I can categorically say the gas will be undergoing cooling. Is it clear? Is it clear, people? Is it clear? Right? Okay. So if I compare initial temperature and final temperature of the gas, can I say final temperature of the gas will be less than that of initial temperature? Final temperature of the gas in this particular case during adiabatic expansion, final temperature of the gas will be less than that of initial temperature. I can say something like this. Okay. Now similarly, people, when you talk about the compression, when you talk about adiabatic compression, imagine the piston initially was at point A. Now the piston has to go from A to B. That means this is the case of compression. And I'm assuming this compression to be adiabatic in nature. Right? First of all, whenever there is compression, work is done on the system. So whatever work will be done on the system, can I say the work which is done on the system during the compression, that work will be stored in the gas in the form of its internal energy, right? So during the compression, will the internal energy of the gas increase or decrease? It will increase. And if internal energy of the gas increases, I'll say temperature of the gas will increase. And if the temperature of the gas increases, I'll say the gas will undergo heating, right? So compare the temperatures here, initial temperature and final temperature. Tell me, during adiabatic compression, I told you temperature of the gas increases. So which temperature will be more? Final temperature of the gas will be more than that of initial temperature. Okay? Perfect, people? Is that clear? Is it clear? Let me know once in the chats. These are two very important statements which you have to remember. They can be asked directly. So, during adiabatic expansion of an ideal gas, temperature of the gas decreases. During adiabatic compression of an ideal gas, temperature of the gas increases. As simple as that. Okay? Perfect. Now, guys, understand something which I'm going to tell you, which you can only understand. The thing which I'm going to tell you, that you can only understand if you have your mind properly on the screen now. Okay? Because I'll be asking you the questions, you will have to answer me. Because this is something which is really, really important, and normally you won't get it. Normally you won't get it. Imagine that I have to do 5 liters of adiabatic expansion. Imagine that I have to do 5 liters of adiabatic expansion. For example, it can be 10 liters, 20, x liters, whatever, right? We know during the adiabatic expansion, temperature of the gas decreases. Final temperature will be less than that of initial temperature. We know that, right? Final temperature of the gas will be less than that of initial temperature. Now, this adiabatic expansion, it can be either carried out reversibly or it can be carried out irreversibly. I've got two paths. By means of which I can carry out this process, either reversibly or irreversibly. Now we know, since we are doing expansion, whenever there is expansion, work is done by the system, right? But here, magnitude of work done by the system in reversible process will be greater than that of magnitude of work done by the system in irreversible process. So, among these two paths, in which path the gas is doing more work? The gas is doing more work here. Wherever the gas will be doing more work, there only decrease in the temperature of the gas will happen more. Are you getting this? Are you getting this statement, what I'm saying? See, again, I'm repeating the same thing. Understand, this is important. I'm doing 5 liters of adiabatic expansion through reversible, irreversible path, right? Since there is expansion through both the paths, whenever there is expansion, work is done by the system, right? Work is done by the system. So first of all, magnitude of work done by the system in reversible will be more than that of irreversible. So here the gas is performing more work. Wherever the gas will be performing more work, there only the gas will be consuming its internal energy more. And wherever the gas will be consuming its internal energy more, there only temperature of the gas will decrease more. So decrease in the temperature will be more here. Decrease in the temperature will be more here. What does that mean? That means if the final temperature is TF here and final temperature is TF dash here, can you let me know the order of these final temperatures? I can say TF dash will be greater than that of TF. Is it clear? More work done by the system, more internal energy consumption, right? Lesser will be the final temperature. Yeah? Is this point clear? Is this point clear? I'm going to give you one more statement, right? Have your clear eye on the screen. Imagine I'm doing 5 liters of adiabatic compression. Imagine I'm doing 5 liters of adiabatic compression. Tell me one thing. Whenever there is compression, we always say work is done on the system. Work is done on the system, right? Now I've got two paths available with me. Reversible, irreversible. Okay? Whether you want to do this compression reversibly or irreversibly, in both the cases, work will be done on the system. But we know magnitude of work done on the system in irreversible will be greater than that of magnitude of work done on the system in reversible, right? wherever magnitude of work done, whatever work is done on the system, that work is stored in the gas in the form of internal energy, right? Now, where is the work done on the system more? Here is the work done on the system more, right? So more work here will be stored in the gas in the form of its internal energy. So where will be the increase in the internal energy more during the compression? I'll say increase in the internal energy will be more here, right? And wherever increase in the internal energy will be more, there only I would say temperature would have increased more. Okay? If the final temperature here is TF, here is TF dash. Can you give me the order of these final temperatures? Can you give me the order of these final temperatures? I'll say TF dash will be more than that of TF, right? Is it clear? Absolutely, guys. Absolutely. Wonderful. Absolutely. Absolutely. Perfect. Good job. Good job. I know this is a bit tricky, but you have to understand this. It can be asked. It can be asked. One question I'm giving you. If you were able to solve this question, then I'll believe that all the concepts you got. For example, I'm giving you a question. Imagine that I'm doing 10 liters of expansion. Imagine that I have to do 10 liters of expansion of an ideal gas. Okay? Now I'm using different paths. I'm using different paths for this expansion. Firstly, I'm doing this expansion reversible isothermally. Then I'm doing this expansion reversible adiabatically. Then I'm doing this expansion irreversible adiabatically. The order of the final temperatures. Final temperature of the gas over here is T1. Final temperature of the gas in this case is T2. In this case is T3. Can you let me know the order of these final temperatures? If you were able to let me know the answer of this question, that means your concepts are very strong. That means your concepts are very strong. Think over it once. I want you guys to think over it. Think over it once. Give me the order of these. Give me the order of these. Give me the order of these, people. And trust me, you can do it. Perfect. A lot of students gave the correct answer. Wonderful, yaar. Good. Good. See, first of all, you're doing the expansion, right? The first is isothermal. During isothermal expansion, temperature does not change. This adiabatic, this adiabatic. During adiabatic expansion, be it reversible or irreversible, temperature decreases, right? Perfect. So I would say these two temperatures will be less than that of T1 because temperature here does not decrease. Here in this case it will decrease, here in this case it will decrease. Now among these two, where will the decrease in temperature more? In reversible, right? In reversible. So how many of you gave this order? T1, T3, T2? This is the order of the final temperatures. Yes? Amazing. Amazing, guys. Good. That means you're getting the concepts. That's perfect. All right. Now, let's talk about some mathematical part now. And let's see what kind of questions can be asked. First of all, let's get to know how do we calculate work done. How do we calculate work done in reversible adiabatic process? How do we calculate work done in reversible adiabatic process? And similarly, how do we calculate work done in irreversible adiabatic process? Perfect. Let's see some results and then later on we'll be solving the questions. See guys, work done, calculation in case of reversible adiabatic. First of all, if the process is adiabatic, that means Q has to be 0. Q will be 0. As per first law of thermodynamics, delta U is equal to Q plus W. Or I can say W is equal to delta U. W right now is reversible adiabatic. And delta U for the ideal gas is nothing, that is N CVT2 minus T1. So this is one of the direct expressions. This is one of the direct expressions which you shall be using to calculate work done in case of reversible adiabatic process. This is one of the formulas by means of which you can calculate work done in case of reversible adiabatic processes. Point number one. Point number two. Work done in reversible adiabatic process is equal to N. CV is nothing, it is R divided by gamma minus 1. This will be T2. This will be T1. Right? Now it's going to be, or you can write it as NR delta T divided by what? Divided by gamma minus 1. You can remember this expression as well. This can be also used. Now similarly, NRT2 means, it means P2V2 minus NRT1 means P1V1 divided by gamma minus 1. This is one more expression by means of which you can calculate work done in reversible adiabatic processes, right? So these three expressions you have to remember, you are done. Okay. Now how do you calculate work done in irreversible adiabatic? How do we calculate work done in irreversible adiabatic process? Tell me that. First of all, in case of irreversible processes, how do we calculate work? Simple, minus P external V2 minus V1. So this expression can be used directly to calculate work done in case of irreversible adiabatic. Number one. Number two, you can convert the expression in different format as well. W irreversible is equal to minus P external. Instead of V2, you can write nRT2 divided by P2. Instead of V1, you can write nRT1 divided by P1. Perfect. This can be one more expression which you can remember to calculate work done in case of irreversible adiabatic processes. Perfect. So do remember these 3-4 expressions to calculate work done in reversible and irreversible adiabatic. Okay. Now similarly, guys, there is a question asked. Calculation of final temperature. Calculation of final temperature in reversible adiabatic and calculation of final temperature in irreversible adiabatic. Calculation of final temperature of the system in irreversible adiabatic. How do you solve this particular question? How do you solve this particular question? Calculation of final temperature in reversible adiabatic and calculation of final temperature in irreversible adiabatic, right? There are a few expressions which you can remember directly in order to calculate the final temperature of the gas. See, we already know whenever the ideal gas undergoes adiabatic expansion, its temperature decreases. How do we calculate its final temperature? There is a formula for that. Similarly, whenever the ideal gas undergoes irreversible adiabatic expansion, its final temperature will be decreasing. How do we calculate the final temperature there? So basically, we have got certain formulas which you have to remember over here. And you know why this final temperature decreases. Where is the decrease more? Where is the decrease less? Right? All those things we have discussed in detail. Correct? Now here, it's just going to be the formulas. The first formula is going to be T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. This is the first result. Or you can use T1 raised power 1 minus gamma. T1 raised power gamma is equal to T2 raised power 1 minus gamma and T2 raised power gamma. These are the two results which you can use, and by using these results, you can easily calculate the final temperature T2 of the gas. Final temperature T2 of the gas when the gas will be undergoing reversible adiabatic process. If the gas will be undergoing irreversible adiabatic process, how do we calculate its final temperature at that point of time? Say, it's adiabatic, Q is 0. If Q is 0, that means delta U is equal to W. Since I'm talking about irreversible adiabatic, so delta U is equal to W irreversible. Now people, delta U is nothing. It is NCV T2 minus T1. W irreversible will be simply minus P external V2 minus V1. So you can use directly this expression. You can use directly the first law and calculate the final temperature T2 of the gas. Point number one. Point number two. And you can write as such, instead of CV, it's going to be R divided by gamma minus 1. This is going to be T2 minus T1 is equal to minus P external. Instead of V2, you can write nRT2 divided by P2. This is going to be nRT1 divided by P1. So NR everywhere cancel. So you are getting one more result which we can use in the form, in the questions. T2 minus T1. T2 minus T1 divided by gamma minus 1 is equal to minus P external. This is going to be T2 divided by P2 minus T1 divided by P1. This can be one more expression which can be utilized to calculate the final temperature of the gas, which will be undergoing irreversible adiabatic process. Right? Perfect, guys. Are these expressions clear? Are these expressions clear to you? Now the point is, what kind of questions can be asked? See, guys, see what kind of questions can be asked. This is the first question, and this is the question which was asked long back in JEE mains as well. A simple question this is. 1 mole of a monoatomic ideal gas expands adiabatically at initial temperature capital T against a constant external pressure of 1 atm from 1 liter to 2 liters. Find the final temperature of the gas. First of all, as per this particular question is concerned, you are given with 1 mole of monoatomic gas. So N is equal to 1. The gas is monoatomic. That means its CV has to be equal to 3 by 2R. Now this 1 mole of gas, it expands adiabatically. From 1 liter to 2 liters. So initial volume of the gas is 1 liter. Final volume of the gas is 2 liters. Right? And this expansion is adiabatic in nature. Now, is it reversible or irreversible? Is it reversible or irreversible? As per the question, this expansion is happening against a constant external pressure. And constant external pressure means the process is irreversible. So I identified the process is irreversibly adiabatic. And what is the external pressure that's given to me? This expansion is happening against a constant external pressure of 1 atm. What do we have to calculate? We have to calculate the final temperature of the gas. Initial temperature of the gas is capital T. Final temperature we have to calculate. Just tell me one thing before solving this question. Tell me whether this T2 will be equal to T1 plus something or T1 minus something. Tell me that. By reading the question, if your concepts are clear, you should be able to answer this. Whether the final temperature T2 will be T1 plus something or T1 minus something. T1 plus something or T1 minus something. Quickly. T1 plus? Are you sure? Think logically. Adiabatic expansion is happening. Whenever there is adiabatic expansion, temperature of the gas decreases. So final temperature will be less than initial. So T2 will be T1 minus something, right? T2 will be less than T1, correct? T2 will be less than T1. Yeah? And since you identified the process irreversibly adiabatic, if the process is irreversibly adiabatic, how do we calculate the final temperature in this case? You know, the expression which I gave you right now, NCV T2 minus T1 is equal to minus P external V2 minus V1 using first law, right? N value is 1. CV is 3 by 2R. T2 we have to calculate. T1 is capital T minus P external is how much? 1 atm. V2 minus V1. V2 is 2 minus 1. That's 1. Correct? So T2 from here will be equal to capital T minus 2 divided by 3. And this is going to be R. This is going to be the final answer of the question. This is the final temperature of the gas. This is the final temperature of the gas. Now tell me one thing. This is the final temperature of the gas when the process is carried out irreversibly. If the process was carried out reversibly, would this have been the final temperature? If the process was carried out reversibly. See, right now the question is saying the process is irreversible. This is the final temperature when the process is carried out irreversibly adiabatically. Now, if the process was carried out reversibly adiabatically, how do you calculate the final temperature? This can be one more question. This can be one more question. This can be one more question. What plus? Arey yaar, what are you saying plus? See, it is expansion, adiabatic expansion. Whenever there is adiabatic expansion, temperature of the system decreases during the expansion, right? Temperature of the system, temperature of the gas decreases during the adiabatic expansion, be it reversible or irreversible, correct? These formulas are used if the process carried out irreversibly. When the process carried out reversibly, I gave you one more result if you remember. That is T1 V1 raised, T1 V1 raised power gamma minus 1 is equal to T2 V2 raised power gamma minus 1. This is the expression which we use to calculate final temperature when the gas is undergoing a reversible adiabatic process. Yeah? Right? So T1 is capital T, V1 is 1, 1 raised power anything is 1, correct? Is equal to T2 we have to calculate. What is V2? V2 is final volume which is 2 raised power gamma minus 1. Gamma value for monoatomic is going to be 5 by 3. So 5 by 3 minus 1 comes out to be 2 by 3. So final temperature of the gas T2 will be equal to capital 2 divided by 2 raised power 2 by 3. This is the final temperature of the gas when the gas undergoes what? A reversible adiabatic process. Okay? This is for reversible adiabatic. And this one was for irreversible adiabatic. Right? So don't confuse yourselves. I know your brain is not braining properly. I know that. I know that. It's okay. Happens. Okay. Can you give this question a try? Look at this particular question carefully. Look at this particular question carefully. Look at this particular question carefully. Can you solve this? Can you solve this, people? Hello, hello, hello. Mission is tapping hi. What's up? How are you? We have got some maskman in the chats. Yeah? Maskman must be the physics educator, I believe. I think you can solve this question by just looking at it, right? Hello. Look at the question, guys. Look at the question carefully. A sample of fluorocarbon was allowed to expand reversibly and adiabatically to twice its volume, right? Yeah? A sample of fluorocarbon was allowed to expand reversibly and adiabatically to twice its volume. So if the initial volume of the gas, for example, is V, so the final volume of the gas has to be 2 times V, correct? During the expansion, the temperature dropped from 400 Kelvin to 100 Kelvin. So as per the question, the initial temperature of the gas was 400 Kelvin and final temperature of the gas is something which is given to me as 100 Kelvin. Assuming ideal gas conditions, calculate CV for the gas. Now people, first thing which we already know, as per the question, the gas is undergoing reversible, adiabatic and expansion, right? Sorry. The gas is undergoing reversible adiabatic expansion. We know during the adiabatic expansion of the gas, temperature of the gas decreases, and it's mentioned in the question, the temperature is decreasing from 400 to 100. What do we have to calculate? We have to calculate CV. How do we get the CV value? You know, CV is nothing that's equal to R divided by gamma minus 1. Correct? So it is just that we have to calculate gamma value. How do I calculate gamma value? How do I calculate the gamma value? It's pretty much simple. First of all, the process is reversible and adiabatic. The process is reversible and adiabatic. If the process is reversible and adiabatic, how do we calculate gamma? For the reversible adiabatic processes, you know T1 V1 raised power gamma minus 1. It has to be equal to T2 V2 raised power gamma minus 1. So what is T1? T1 is 400. What is V1? That is V raised power gamma minus 1. Raised power gamma minus 1 is equal to T2. What is V2? V2 is 2 times V raised power gamma minus 1. So V gamma minus 1, V gamma minus 1 cancel. Achha, by the way, this T2 is also given to us. How much? T2 is given to us as 100. Perfect. So 0000 cancel. So V power gamma minus 1, V power gamma minus 1 cancel. So 4 has to be equal to 2 raised power gamma minus 1. Or you can say 4 instead of 4, you can write 2 square. So from here, you got to know gamma minus 1 is equal to 2. If gamma minus 1 is equal to 2, That means CV value is nothing but R divided by, instead of gamma minus 1, you're writing 2. So this has to be the final answer of the equation. So this is the value of CV, which I was supposed to calculate, right? This is the value of CV, which I was supposed to calculate. I believe this is clear. Okay. Is it clear, people? Is it clear to everyone? Is it clear to everyone? Is it clear to everyone? Yes? Look at one more question. Look at one more question. 1 mole of gas A whose CV is given plus 2 moles of gas B whose CV is given are mixed in a container and expanded adiabatically and reversibly from 1 liter to 4 liter starting at 320 Kelvin. What would be the work done in calories? This is a comparatively lengthy question. This is a comparatively lengthy question. And this question, it was long back asked in your JEE Advanced once. The same question. I don't remember the values, but similar question as far as I remember in 2013 or 14, right? But if you are able to solve this particular question, that means all your concepts related to adiabatic process are clear. That is my point of coming up with this particular question here. Okay. So see exactly what the question says. As per the question is concerned, imagine first of all, this is the container which we have. In this container, we have got two gases, gas 1 and gas 2. Instead of A and B, I'm writing 1 and 2. How many moles of gas 1 do we have in the container? 1 mole. How many moles of gas 2 are there in the container? 2 moles. Correct? So basically, we have got a gaseous mixture. We have got a gaseous mixture. CV value of these gases is given. So CV value for gas 1 is equal to how much? 3R. And CV value for gas 2 is going to be equal to 3 by 2R as per the question. Okay. Now, first of all, I have got a mixture of gas, and this mixture of gas is expanded adiabatically and reversibly from 1 liter to 4 liters. So volume of the mixture, initial volume of the mixture is given to me as 1 liter, and as per the question, the final volume of the mixture is given to me as 4 liters. So I had a mixture basically, right? This mixture, its initial volume was 1 liter, final volume is 4 liter. The mixture is being expanded, and the expansion is reversible and adiabatic in nature. Initial temperature of the mixture is also given to us as 320 Kelvin. Correct? 320 Kelvin. What do we have to calculate? We have to calculate work done in calories. So first of all, people, this mixture is undergoing reversible adiabatic expansion. When this mixture will be undergoing adiabatic expansion, first of all, we already know temperature of the mixture will decrease, right? So T2 value, it will be less than that of 320 Kelvin, number one. And you know, during the expansion, we say work is done by the system. We have to calculate how much work is exactly done by the system during this expansion. We have already identified the process to be reversible adiabatic. The first thing which I'm going to do over here, try to understand. Can I calculate CV for the mixture? We can do that. CV for the mixture is going to be N1 CV1 plus N2 CV2 divided by N1 plus N2. So this multiplied with this is 3R. This multiplied with this is also 3R. 3R plus 3R makes it 6R. 6R divided by 2 plus 1, 3. That comes out to be 6R divided by 3. Comes out to be 2R. So CV mixture is 2R. Correct? If CV mixture is 2R, you know, CP mixture minus CV mixture is equal to R. So can I calculate CP mixture from here? It's going to be R plus CV, which comes out to be 3R. So I got to know CV mixture, I got to know CP mixture. Can I calculate gamma for the mixture? Absolutely, we can do that. That's going to be equal to CP mixture divided by CV mixture. The value will be 1.5. Correct? You got the gamma mixture as well. Yeah? You got the gamma mixture as well. Now, why do I need this gamma mixture? Because I have to eventually calculate work done during reversible adiabatic process, and as per the result, it has to be NCV T2 minus T1. Right? I have to calculate this particular term. What does N represent here? Since the mixture is undergoing expansion, so N represents total moles present in the mixture. CV represents CV for the mixture. T1 is the initial temperature of the mixture and T2 is the final temperature of the mixture. So what all parameters do I already have? N I have, Cv for the mixture I have, T1 I have. I do not have T2. So the process is reversible adiabatic. So we can calculate its final temperature. We can calculate its final temperature with this particular formula. T1 V1 raised by this is equal to T2 V2 raised by gamma minus 1. So what is T1? T1 is 320. What is V1? V1 is 1. 1 raised by anything is 1 only, right? Is equal to T2. We have to calculate. What is V2? V2 is 4 raised by gamma minus 1. 1.5 minus 1 is 0.5. So this is 4 raised by 0.5. 4 raised by 0.5 is 2. So 320 divided by 2 comes out to be 160. So T2 comes out to be 160 Kelvin. Right? This is the final temperature of the gas. If you calculated the final temperature of the gas as well, so we can calculate work done during this reversible adiabatic process. So total moles present in the mixture is 2 plus 1, 3. Cv for the mixture we already got. That is 2R. T2 minus T1. T2 is 160 and T1 is 320. So the value comes out to be 160 minus 320. That will be minus 160. Perfect. So what would be the work done in calories? Work done in calories. So it has to be equal to 3 2s are 6. Take the value of R as 2. Multiplied by what? Multiplied by minus 160. Correct? Solve it and get the value in calories. This is the final answer of the question. Is it clear? Is it clear? Is it clear, people? Quickly. Is it clear? Let me know once in the chats. Yeah? Clear? All right. All right. Lot of people are watching. Yeah? Physics people are also watching. All right. People are saying the answer is minus 1920 calories. All right. You can keep the answer. Okay. So people, this was all about here. This was all about it. Well, you can take one question as the homework. Right? You can take one question as the homework. This is your homework question. Similar pattern this is. Right? You can give it a try. You can give it a try. Now I'm going to move into one more topic. That's going to be your cyclic process. Cyclic process and different types of questions which can be asked from the cyclic processes. Okay? As I already gave you the idea about cyclic processes long back, right? I gave you the definition of cyclic process, if you remember. I told you, in case of cyclic processes, what do we see? In case of cyclic processes, what do we see? System returns to its initial state. System returns to its initial state after going through a lot of steps. After going through a lot of steps, right? System returns to its initial state after going through a lot of steps. That means the initial state and the final state of the system is same. In case of cyclic processes, the initial state and final state of the system is same. You know it. And if the initial and final state of the system is same, that means change in the value of a state function in case of a cyclic process, it has to be 0. It has to be 0. What does that mean? That means delta U net as well as delta H net as well as delta S net as well as delta G net. All these are state functions, right? And change in the value of a state function for a cyclic process, for the overall cyclic process, that has to be 0. Already we have discussed these points from point A, right? From point A, you are moving towards point B, right? I'm showing the arrow towards right. For example, just to make you understand, from B till point C, let's say the arrow is towards down and from C towards A. So in the beginning, if you realize, I started from A, then I reached finally till A only. So initial state and final state of the system is same. If initial and final state of the system is same, I would say the ideal gas which is taken into consideration, that is undergoing a cyclic process. Number one, right? That's undergoing a cyclic process. Delta U net, delta H net, delta S net, delta G net, all these terms for this overall cyclic process is going to be 0, right? Now guys, few more things. If I ask you what is this delta U net, net internal energy change during the overall process has to be equal. It will be delta U during the process AB plus delta U for the process BC plus delta U for the process CA. Correct? Similarly, if I ask you one simple thing, delta U net for the overall cyclic process 0, you know it, right? Wait, just me erase this part. See, as I told you, delta U net for the overall cyclic process 0. If I use the first law says that delta U is nothing, it is Q net plus W net, right? So this has to be 0. So I would say Q net has to be equal to minus times W net in this particular case. This is one more important thing. Because delta U net for the overall cyclic process 0. If the delta U net for the overall cyclic process 0, I can say Q net has to be equal to minus times W net, right? Yeah? Correct, people? What is Q net? It is the net heat absorbed or released during the overall process, during the overall cyclic process. So, what is this Q net if you ask me? Q net is nothing. It is heat absorbed or released during the process AB plus heat absorbed or released during the process BC plus heat absorbed or released during the process CA. Similarly, W net, it will be equal to basically, it will be equal to work done during the process AB plus work done during the process BC plus work done during the process CA. Right? Perfect. These are some basic things which I'm telling you, and after 5 to 10 minutes, I'll be using all these things in the equations. Using all these things in the equations. I believe it's clear. I believe it's clear. Yeah? Right? Is it clear till here? Okay. One more thing which I would want you guys to remember directly, right? I'm not explaining all these things now in detail. Do remember, magnitude of work done, I'll say the net magnitude of work done during the cyclic process is equal to area enclosed by the loop. Do remember this particular point as well. So whatever is the area enclosed by this particular loop, right? That will always give you the magnitude of net work done during this particular cyclic process. Okay? And one thing which you can remember directly, if the cycle is clockwise, the value of W net will come out to be negative. If the cycle is anti-clockwise, right, you can remember it like this. There's a logic as well. I'm not going to the logics right now. Clockwise, what is the spelling of clock? C-L-O-C, yeah. Okay. For the anti-clockwise cycle, I would say W net will come out to be positive. Remember these two things directly. If the cycle is clockwise, W net sign will come out to be negative. If the cycle is anti-clockwise, W net sign will come out to be positive. Now let's do one thing. Let's utilize all these basic concepts in the questions, right? I'm going to start from the basic question. See, the question you should not take more than 10-15 seconds to solve this question. The question is calculate the net work done in the cycle. Cycle is this ABC. It is clockwise. We have to calculate net work done. So first of all, magnitude of net work done during the process has to be equal to area enclosed by this loop. This is the loop which we have, right? It is complete triangular, right angle triangle. Okay. So area is going to be half of here to here. It's going to be 2 times V1, right? Height is going to be, if this is P1, this is 6 P1, so it's going to be 5 P1, correct? So the value is going to be 5 times P1 V1. This is the magnitude of net work done. But we just don't have to calculate magnitude. We have to calculate net work done. So W net. So W net has to be equal to the cycle over is clockwise. If the cycle is clockwise, the sign has to be negative. So it's minus 5 P1 V1. This is going to be the final answer. Simple and basic question this is, right? Nothing to do here. Okay? Look at this particular question. 1 mole of an ideal monoatomic gas. We have got 1 mole of an ideal monoatomic gas is taken through the cycle below. Okay? Calculate AB calculate QAB and QCA. So, if you cannot see it properly, let me make it for you. Let me make it for you. Correct? This is the cycle which is given to us. This is the cycle that's given to us, right? So first of all, you need to identify exactly the different types of processes which we have. What do we have to calculate first of all? See, we have got 1 mole of ideal gas, right? It is monoatomic, so its CV has to be equal to 3 by 2R and its CP has to be equal to 5 by 2R. This is understood, right? Calculate QAB and QCA. QAB. QAB. If I look at this particular step, AB step is basically isochoric. AB step is isochoric in nature, and CA step, during C to A, pressure is remaining constant, so it's isobaric in nature. So this step is isobaric, right? So QAB, AB process is isochoric. Isochoric means volume has been kept constant. So QAB means heat absorbed or released during the process AB. AB process is isochoric, that means constant volume. So in short, I would say we will have to calculate the heat absorbed or released. Heat absorbed or released during the process AB. AB process isochoric, constant volume. And you know, heat absorbed or released at constant volume is equal to NCV T2 minus T1. Right? N value is 1. PV value as per the question is nothing, that's 3 by 2 R. Let's take R value in calories, right? Or let's take R as such only. Let's keep the answer in terms of R only. Perfect. So 3 by 2 R. T2 minus T1. From A to B, this was initial, this is final. So final temperature minus initial. 600 minus 300 comes out to be 300, right? So the value will be how much? It will be 450 R. This is the value of QAB which we were supposed to calculate. Yeah? This is the value of QAB. Correct? Now similarly, what do we have to calculate? We have to calculate QCA as well. What is CA process? CA process is isobaric in nature. That means from C to A, pressure of the system is remaining constant. So basically, QCA means heat absorbed or released at constant pressure. Heat absorbed or released at constant pressure, which is nothing, which is NCP T2 minus T1. Right? N value is 1. CP value is 5 by 2R and T2 minus T1. So we are moving from C to A. So this was initial, this is final. Final temperature minus initial temperature. The value will be 300 minus 450, which comes out to be minus 150, right? So this will be minus 750 divided by 2R. Or you can call it as minus 375R. I hope this particular point is also clear to you, right? Perfect, guys? Yeah? Perfect. Let's try to solve a few more questions. Let's see what all questions we have. Calculate Q net, W net, delta U and delta H for the overall cyclic process. Take 1 atm liter is equal to 100 joules. R is equal to this. Cyclic process is valid for 1 mole of monoatomic ideal gas. Okay. All right. So as per this question, we are starting from here. First, we are going from A to B. The arrow is towards right. Then from B to C, the arrow is downwards, right? From C to A. From C to A, the arrow is in this particular direction. Okay. So it's a basically PV curve which is given to us. We have to calculate Q net, W net, delta U and delta H. First of all, for the overall cyclic process, this delta U net and delta H net both will be equal to 0. So delta U net has to be equal to 0 and delta H net, they have to be equal to 0 because for the cyclic process, change in the value of a state function is always equal to 0. Okay. Now guys, we'll analyze the processes separately. Let's try to analyze the process AB first of all. Let's try to analyze the process AB. AB process is basically isobaric, right? Pressure is constant. Pressure is constant. pressure is constant. All right. If pressure is constant, one thing we can conclude from here, during the process AB, pressure is constant. As per ideal gas equation, PV is equal to nRT, right? PV is equal to nRT. If pressure is constant, moles are, they're already constant, so volume is directly proportional to temperature. AB process isobaric, right? So at point A, volume was 16 liters, right? Volume was 16 liters. At point B, volume is 32 liters, right? So volume is doubling over here. If the volume is doubling, that means temperature will double as well. So temperature at point A was 400. That means at point B, it's going to be 800 Kelvin. Agreed? Yeah? Simple. I'm not doing anything new. Now, if you talk about B to C is isochoric. You know PV is equal to nRT. If PV is equal to nRT, volume is constant, N constant, R constant. Can I say pressure is directly proportional to temperature? From B to C, what is happening to pressure? Pressure is reducing by half. That means temperature will be also reduced by half. If pressure is reducing by half, temperature will be also reducing by half, right? So temperature here will be 400 Kelvin. Temperature here will be 400 Kelvin. So basically, I calculated the temperatures first of all at point B and point C. Calculation of temperature is done at point B and point C. Now, what is next? What's next, people? Let's try to analyze the process AB. AB is happening at constant pressure. It's constant pressure, right? So QAB, calculate QAB first of all. QAB means heat absorbed or released during the process AB. So I can say it is basically heat absorbed or released at constant pressure, which is nothing, which will be NCP T2 minus T1. Right? NCP T2 minus T1. So this QAB has to be equal. What is the value of N? We have got 1 mole of ideal gas, right? CP value for monoatomic is going to be 5 by 2 R. R value we have to take as 8. T2 minus T1. T2 here is 800 minus 400 is 400. Perfect. So 2, 1, 2, 4, 5, 4, 20. 20 into 400 comes out to be 8,000. So 8,000 joules. So QAB we got to know is 8,000. If QAB we got to know is 8,000, calculate WAB. Work done during this isobaric process is simply going to be equal to minus P delta V, right? Minus P is 2 atm, delta V is V2 minus V1. V2 here is 32, 32 minus 16 is 16, right? So it's going to be minus 32 atm liter. WAB here is going to be minus 32 atm liter, but multiply it with 100 because it's mentioned that 1 atm liter is equal to 100. So the value comes out to be minus 3200 joules, right? So you analyzed, you calculated WAB as well as you calculated QAB, correct? Similarly, we will be analyzing different types of processes. Now, if you look at BC process, what is BC? BC is happening, right? This is isochoric, volume is constant, isochoric. So first of all, I'll be calculating QBC. Heat absorbed or released during this process, which is happening at constant volume, right? So it is QB in short, which is going to be NCV T2 minus T1, right? So I would say QBC has to be equal to N value is 1, CV value is going to be 3 by 2, R value is 8, T2 minus T1, final minus initial, that's minus 400, right? So QBC, I would say, this is 2, 1, 2, 4, 3, 12, 12, 4, 48, so minus 4800 joules. So this is QBC. If this is QBC, what about WBC? Isochoric, so WBC has to be 0, right? Need not to be discussed. WBC has to be 0, correct? Right, guys? I hope you got till now, right? Now, what about which process we have to analyze now? It is the process CA which we have to analyze now. So where do you analyze the CA process now? Okay, I'll get some space here. Just a second. Let's try to analyze the CA process. Now, guys, if you look carefully, At point C, what is the value of P1 V1? P multiplied by V value here is 32. At this point, P multiplied by V value here is also 32. P multiplied by V here is 32, here is 32. That means PV is constant. PV constant means isothermal. And which isothermal this is? This is reversible isothermal. This is reversible isothermal, right? This is reversible isothermal. Now, how do you calculate work done in reversible isothermal processes? How do you calculate work done in reversible isothermal processes? Minus nRT. It's going to be ln of V2 by V1. Correct? So minus N value is 1, R value is 8, temperature is how much? 400 Kelvin. Perfect. Ln of V2 by V1. This is ln of V2 by V1. So C to A. This was initial, final. Right? V2 divided by V1. Final wall, make this plus. You can make this 32 by 16 here. 32 by 16 is 2. Right? 32 by 16 is 2. So this is going to be 8 4s are 32. So 3200. Perfect. Ln 2 is going to be 0.7. Perfect. The answer is going to be in joules. So this is WCA. Now the point is, how do you get the QCA? Since CA process is isothermal, if CA process is isothermal, so delta UCA. Whenever the ideal gas undergoes isothermal process, delta U 0. If delta U 0, that means QCA plus WCA has to be 0. Correct? So WCA you have already calculated. That means QCA will be minus of this value. QCA will be minus of WCA. Perfect. So from here, you can calculate your QCA as well. What were you supposed to calculate? QNet, WNet. QNet is nothing. QNet will be equal to QAB plus QBC plus QCA. Right? Similarly, WNet will be WAB plus WBC plus WCA. Just take the sum of them and get the answer. That's it. Yeah? I believe it's clear. Right, people? Is it clear? So this sort of equation even you can solve, I believe. Now there is something called as efficiency of the cyclic process. From this particular concept also, a question can be asked. Right? From this particular concept also, question can be asked. And it's going to be a very simple and basic question. How do you get the efficiency of the cyclic process? Efficiency of the cyclic process is always equal to, let me tell you, it's going to be area enclosed by the loop divided by area under the loop multiplied by 100. Area enclosed divided by area under the loop multiplied by 100. Okay, see guys, for example, I have got a loop over here. This is pressure on one side, volume on one more side. Starting from point A. From point A, you are moving towards point B. From point B, you are moving towards point C. From C to A. Let the arrows be in clockwise direction. Okay. Now, guys, let's say this is E here. Let's say this is F here. Correct? If I need to calculate the efficiency of this particular cyclic process, how do I get it? I'll write efficiency of this cyclic process is equal to area enclosed. Area enclosed is this much. That means I'm talking about the area ABCA divided by area under the loop. This whole is basically the area under the loop. It's going to be ABEF. Area ABEF. Area ABEF. And at the end, you will have to multiply with 100. Whatever value you get from here, that's going to give you the efficiency of the cyclic process. Right? That's going to give you the efficiency of the cyclic process. Yeah? Right, people? Now, I'll be giving you one question and you will have to solve that. And the question is pretty much simple, I would say. Look at this. Look at this. This is a loop that is given to us. We have to calculate its efficiency. So first of all, efficiency of this particular cyclic process has to be equal. Efficiency has to be equal. I'll write area enclosed by the loop. That means this area. Calculate this area first. Half of base into height. Calculate this area first. Half of base into height. So it's going to be half of Base into height. Base is going to be 4 and height is going to be how much? 1, right? So this is area enclosed divided by area under the curve. What about the area under the curve? Area under the curve means this whole area. Area under the curve means this whole area. So it's a trapezium basically, right? It's a trapezium. So half of sum of parallel sides, which is 2 plus 1, that is 3, multiplied by this height, this distance. So 2 to 6, that's 4, right? So solve this and at the end multiply with 100, get the efficiency of this cyclic process. Again, this is very, very, very simple, guys. This is not something which is difficult. This is not something which is difficult, right? Yeah? Right, people? I hope these sort of questions related to cyclic processes you will be able to solve from now onwards. Okay? Now, there is something called as polytropic processes. How do you exactly define these polytropic processes? Let me write the definition. Those processes for which the equation PV raised by x is equal to constant, where x is not equal to 0, is not equal to 1, is not equal to gamma, is not equal to infinity. Those processes for which this particular equation is valid, you call those processes polytropic processes. What is meant by that? See, guys, if you look at this particular equation, if, for example, I take the value of x as 0, if the value of x is taken as 0, by the way, let me write the equation like this, or you can write it like this. P raised power 1 minus x, P raised power 1 by x multiplied by V is constant. This or this. Now let me write things over here. First thing, if by chance x value is 0, if x is 0, anything raised power 0 is 1, that means pressure is constant. Pressure constant means which process I'm talking about? The process isobaric right now. It is the isobaric process which I'm talking about. If by chance I put the value of x as 1, if x is 1, that means PV is constant. PV constant means which process? Isothermal process. It is isothermal in nature, right? If x value is gamma, then PV raised per gamma is equal to constant. The process is reversible adiabatic. It is adiabatic, right? If the value of x is taken as infinity, 1 by infinity is 0, anything raised per 0 is 1, so volume is constant. Volume constant means isochoric. These all processes we have discussed till now, right? Now, people, now guys, if the value of x, apart from these four values, 0, 1, gamma and infinity, if the value of x is anything apart from these, if the value of x is, for example, 2, then the equation will be PV raised power 2 is equal to constant. If the value of x is 1 by 2, it's going to be PV raised power 1 by 2 is equal to constant, right? Apart from these four values, whatever values you put here, right, you'll get an equation, right? And the gas which will be following that particular equation, that will be the we say that gas is undergoing polytropic process. As simple as that, right? Got it? Apart from these four values which we have here, whatever will be the value of x apart from these four values, at that point of time we say the gas is undergoing what? The gas is undergoing the polytropic processes. Now, people, just two things you have to remember here. First thing, how do you calculate work done? How do you calculate work done in case of polytropic process? I'm not going to derive this expression. Just remember it directly. It's P2V2 minus P1V1 divided by x minus 1. P2V2 minus P1V1 divided by x minus 1. P2V2 minus P1V1 divided by x minus 1. This is the expression by means of which you calculate work done in polytropic process. expression number 1. Expression number 2, that is calculation of molar heat capacity for any process. Cm is equal to Cv plus R divided by 1 minus X. I believe this particular equation you would have studied in physics as well. Molar heat capacity is always equal to molar heat capacity at constant volume plus R divided by 1 minus X. This is the equation which is used to calculate molar heat capacity for any process. Let's try to utilize these equations in the question so that you'll see what kind of questions are asked from it. See guys, the first question which is on the screen. Let's see what the question is. Calculate the molar heat capacity of a monoatomic gas. All right, we are given the monoatomic gas. If it's a monoatomic gas, its Cv has to be equal to 3 by 2R. This is something which I conclude first of all. As per the question, the ratio of pressure and volume is 1. The ratio of pressure and volume is 1, right? So from here, I can say PV raised power minus 1 is equal to 1. My dear students, don't you think this particular equation resembles with our equation? Don't you think these two equations resemble, right? So can't I say, by comparing these two, can't I say X value is equal to minus 1 here? X value is equal to minus 1 here, right? Can't I say the value of X here is minus 1? If you got the value of X, I gave you the result few minutes back. Cm is equal to Cv plus R divided by 1 minus X, right? Was it 1 minus X or X minus 1? Yeah. Cv plus R divided by 1 minus X. Now you are done, you're sorted. So molar heat capacity of the gas is equal to, this is 3 by 2R plus R divided by 1 minus, what is X? X is minus 1, so it's going to be minus minus plus. So it's going to be 3 by 2R plus R by 2. Perfect, the value at the end comes out to be 2R. So this is what you call as molar heat capacity of the gas, which I was supposed to calculate. The first and the basic question which we have. Okay, the first and the basic question which we have. Let's have a look on one more question. Let's have a look on one more question. Look at this particular question carefully. The molar heat capacity of the gas, molar heat capacity Cm, is given to us. 7 divided by 2R. Correct? For which P and V are equal. As per the question, P is equal to V. If P is equal to V, I can say P divided by V is equal to 1. Or I can say PV raised power minus 1 is equal to 1. This equation resembles with our equation, PV raised power X is constant. If you compare these two equations, you got the value of X as minus 1 here. First thing, which we have done over here, right? X value is minus 1. Now, after getting the value of X, I'll use the equation. Cm is equal to Cv plus R divided by 1 minus X. So this is 7 by 2R is equal to Cv plus R divided by 1 minus minus 1. So R by 2. So Cv is going to be 7 by 2R minus R divided by 2, which comes out to be 3R. For which particular gas Cv is 3R? Remember, for which particular gas Cv is 3R? Is it going to be monoatomic? For monoatomic gas, Cv is 3 by 2R. For diatomic gas, Cv is 5 by 2R. For polyatomic nonlinear, Cv is 3R, right? So the gas has to be polyatomic, nonlinear. Perfect, people? Okay. Let's have a look on one more question then. Okay. Look at this particular question. See what the question is saying. For 1 mole of monoatomic ideal gas, for 1 mole of monoatomic, ideal gas during any process, T square is equal to K V raised power cube, V raised power 3. Calculate Cm for the process. Okay. See guys, as per this particular equation is concerned, we are given with the equation T square is equal to K V raised power 3, right? Now, as far as your ideal gas equation is concerned, PV is equal to nRT, or I'll say PV is directly proportional to temperature, right? PV is directly proportional to temperature, correct? So if I take square on both the sides, so it's going to be P square V square is directly proportional to T square. So instead of T square, can't I write P square V square is equal to K V raised power 3. So V raised power 3 in the denominator, it's going to be P square V square divided by V raised power 3 is equal to K, or I can say P square V raised power minus 1 is equal to K. Take the root on both the sides. It's going to be P V raised power minus 1 by 2 is equal to K dash. Correct? Correct, people? Now, if you compare this particular equation with our equation, PV raised per x is constant. Compare these two. When you compare these two, you'll be getting the value of x. What will be the value of x here? X value will be minus 1 by 2. If you got the x value, you're done, right? Right? You're done. So Cm from here will be Cv plus R divided by 1 minus x. So Cv for monoatomic is going to be 3 by 2R plus R divided by 1 minus x is going to be minus 1 by 2. So 1 plus 1 by 2 is 3 by 2. 3 divided by 2. So 3 here, 2 here. The value is going to be 3 2s are 6. 6 plus, 3 is 9. 9 plus 4 is 13. So 13R divided by 6 is going to be the final answer of the question. Correct? Is it clear? Is it clear, people? Is it clear? Is it clear? Yeah? Guys, in today's session, we shall be completing dynamics part, and in the next session, we'll be completing thermochemistry part. Don't worry. See, we are left with basically, after this, we are left with 3 topics. One is entropy, one is free energy, one is heat of reactions. And all these 3 topics, I'll teach you in one more marathon, which is going to be the next marathon. That's going to be thermochemistry. Because if I teach entropy gives free energy and heats of reactions now, it will still, it will extend 5 to 6 hours more, which is not possible. Right? Which is not possible at all. Okay? Game of NEET. Nothing is going to happen to Game of NEET. I'm here. I've started this course. I'll finish this course, right? Don't worry. I'm going nowhere. I'm here only. GOC was done, yes. So history cannot be created. See, maximum stream duration can be 12 hours. After 12 hours, the stream automatically gets ended. Whatsoever it is. Stream automatically gets ended after 12 hours. Okay. So I think these sort of questions you can easily solve from now on. Now, guys, there is one more topic which you need to learn, which you need to know. What is that? Have you heard about something called as free expansion? Have you heard about something called as free expansion? How do you define the free expansion? Free expansion is nothing, it is defined as the expansion of the system. The expansion of the system against zero external pressure. Expansion of the system against zero external pressure. What does it mean? Try to understand. For example, this is the container which I have, and over here you have got a piston, and inside this, imagine you have got the ideal gas, right? Now, on this piston, there'll be 2 pressures. This will be pressure of the gas, and on this side, it's going to be P external. Now, first of all, tell me one thing. If by chance P gas will be equal to P external, if P gas will be equal to P external, will the piston move? Piston won't say any sort of moment. If P gas is equal to P external, right? Piston is at rest. Now, if P external suddenly becomes 0, if P external suddenly becomes 0, can I say the piston will suddenly go out? Right? The piston will suddenly go out. Is the process going to be reversible or irreversible? The process is going to be irreversible, right? The process is going to be irreversible. The piston is suddenly going outside. Expansion is happening rapidly, right? So, first of all, the process is going to be irreversible in nature. Right? If the P external is 0 and the process is irreversible, for irreversible process, how do we calculate work? For irreversible processes, this was the expression to calculate work, minus P external delta V. If P external is 0, the value of W is 0. So the first thing which you have to remember, which you have to conclude from here, what is that? That is simple going to be, whenever the ideal gas, whenever the system undergoes free expansion, W value will be 0. Work done is equal to 0, right? Work done is equal to 0. This is the only thing which you have to remember over here. Expansion of the gas against 0 external pressure is called as free expansion. During free expansion, P external is 0, right? W value is 0. Now, two cases arise over here. One is what you call as isothermal free expansion of an ideal gas. Isothermal free expansion of an ideal gas. One is what you call as adiabatic free expansion of an ideal gas. Adiabatic free expansion of an ideal gas. Now, what is isothermal free expansion of an ideal gas? And what is adiabatic free expansion of an ideal gas? Let's get to know about them. First of all, look at the terminology. Isothermal free expansion. If it is free expansion, W value is 0, right? Isothermal free expansion of an ideal gas. Whenever the ideal gas undergoes isothermal process, its delta U has to be 0. Delta U 0 means NCV delta T has to be 0. NCV delta T 0 means delta T has to be 0. Delta T 0 means temperature of the gas has to be constant. And if the temperature of the gas remains constant, you'll be calling the, wait, just a second. What am I writing here? Just a second. Say W is equal to 0. Delta U is equal to 0. Now, if you use the first law of thermodynamics, first law says that delta U is equal to Q plus W. Delta U is equal to Q plus W. Delta U is 0, right? W is 0. That means Q value will automatically turn out to be 0. And for which processes Q is 0, right? Q is 0 for adiabatic processes. So can I simply generalize one quick statement over here? Can I say an isothermal free expansion? An isothermal free expansion. Do remember, it's only valid for ideal gases. An isothermal free expansion for an ideal gas. An isothermal free expansion of an ideal gas is adiabatic as well. Right? Is this particular statement correct? An isothermal free expansion of an ideal gas is adiabatic as well. Okay, I'll teach organic chemistry as well. Wait, let me finish this off. Okay, tell me one more thing. This is the adiabatic free expansion. First of all, if it is a free expansion, so W value has to be 0. If it is adiabatic, so Q value has to be 0. Use the first law. Delta U is equal to Q plus W. If Q is 0, W is 0, that means delta U is 0, right? Since you have taken ideal gas. If you have taken ideal gas, that means delta U is equal to NCV T2 minus T1. So this value is 0, which is only valid if temperature is constant. If temperature of the gas is constant, right? And temperature is constant for what? It is constant for isothermal. So I can quickly generalize one statement over here. I can say an adiabatic free expansion. Free expansion of an ideal gas is isothermal as well. I believe these 2 points are absolutely clear to you. Right? Thank you, Kshitish sir. I believe these 2 points are absolutely clear to you, right? Yeah? I'll call you after the class, Kshitish sir. Okay, stay awake. Do not sleep. So guys, I feel all these things are clear, right? All these things are clear. So with this, our dynamics part is over. And now it's going to be the time for thermochemistry. but thermochemistry is further going to take some 6 hours, right? So this thermochemistry part we shall be doing in the next session. And before ending this particular session, let me tell you what all things we have to cover here. We have to cover heats of reactions. We have to cover heats of reactions here in this chapter. Apart from that, we shall be talking about entropy, and at the same time, there will be Gibbs free energy as well, which we shall be discussing. So these 3 topics, these are not basically only 3 topics. These are not just the 3 topics. These are basically heats of reactions are further classified into different types. You know it. Enthalpy of combustion, enthalpy of formation, neutralization, solution, bond energy, etc., etc. Right? Yeah. So enthalpy, heats of reactions, entropy, and Gibbs free energy, it will be covered in thermochemistry part. And thermochemistry part, most probably I'll be doing on 15th of this month. 15th of January. I'll be doing thermochemistry most probably. Right? Perfect. Perfect, guys. All clear till here? Can you let me know once if every single thing is clear? Can you let me know in the chats if every single thing is clear? Quickly tell me the answer of this question. Let me see how much you remember. Quickly, quickly, quickly. Quickly, quickly, quickly. What do you think? I'll be teaching the thermochemistry part on 15th. This is the asked question. That's why I'm asking you. What's the answer of this question? When 1 mole of ideal gas is heated at constant volume, right? Is heated at constant volume. Just a second. Yeah. Is heated at constant volume. Constant volume means if V is constant, that means W has to be 0. If W has to be 0, as per first law, delta U is equal to Q plus W. So delta U is equal to Q. Right? Heat supplied is 300. So Q is, 500. If Q is 500, so delta U has to be 500 as well. And W has to be 0. So this is the answer of the question. Look at the options. Check the options and solve. Right? Check the options and solve. And these are some people asked questions. Okay, what do you think about this one? This is again one asked question. See what kind of question this is. Basic. Delta U is equal. Delta U is equal. Isochoric work, isobaric work, adiabatic work, isothermal work. Delta U is equal. Quickly. Delta U is equal to Q plus W. Now, when delta U will be equal to work? When Q is 0? When Q is 0, delta U will be equal to W, right? So which W this is? This is adiabatic, right? So delta U has to be equal to adiabatic work. Correct? Again, this is one simple and basic question. Yeah? And all the other questions we have, guys, already discussed. Yes, we have discussed. Okay, what about this one? What about this one? Which of the following expression is true for ideal gas? Which of the following expression is true for ideal gas? You know, for ideal gas, internal energy is just the function of temperature. This is valid for ideal gas, right? I hope you remember. For the real gas, internal energy is the function of volume and temperature, both. This is for real gas. But right now, the question is asking about ideal gas. For the ideal gas, which of the following is true? Which one? Quickly. For the ideal gas, which is true? True. Change in internal energy due to change in volume at constant temperature is equal to 0. Is that? For ideal gas, internal energy only changes on changing the temperature, right? Perfect. If you change the temperature, keeping volume constant, if you change the temperature, there will be some change in internal energy. So this is non-zero. This has to be 0, right? So option 3 is the one which is correct. Option 3 is the one which is correct, right? So nothing to do with here. I mean, these sort of questions, guys, you should be easily able to solve. You should be easily able to solve. This was your question asked 2 years back in your NEET for 2 moles of ideal gas. For 2 moles of ideal gas. Do you remember this question? Cp minus Cv will be equal to 2R. Right? Cp minus Cv is equal to 2R. Look at this question. 1 mole of ideal gas. What do you think about this one? 1 mole of ideal gas expands from 1 liter to 4 liter at constant temperature. What work is done if the gas expands in vacuum? Quickly. This is free expansion, right? And free expansion in vacuum is what you call as free expansion. Expansion against 0 external pressure. That's free expansion. And whenever there is free expansion, work done will be equal to 0. So option 4 is the one which is correct. Okay, look at this one. 3 paths we have, 1, 2, 3. What do we have to calculate? We have to compare the work. You know, area under PV work is equal to work done. I mean, area under PV work, area under PV curve gives us the magnitude of work, right? Gives us the magnitude of work. So area under third curve is maximum. Area under third curve is maximum. Right? So area under third curve is maximum, followed by second, followed by 1. So magnitude of work in the third will be greater than that of magnitude of work in second, will be greater than that of magnitude of work in first. Already these things are discussed. I believe it should not take you more than 5 to 10 seconds to solve these sort of questions, right? So nothing to think here. Can you tell me the answer of this question in less than 5 seconds? 2 moles of ideal gas expanded spontaneously into vacuum. The work done will be how much? Expansion in vacuum is called as free expansion, right? And in free expansion, during free expansion, work done is 0. Right? Tell me the answer of this question. This again a PYQ. Which of the following are not state functions? Not he is saying. Not. Q plus W is your internal energy. Right? It is a state function. This is the path function. Heat. Work is a path function. H minus Ts gives free energy. It's a state function. So this is a path function. This is a path function. Which of the following are not state functions? It is 2 and 3. It is 2 and 3, right? Which are path functions basically. They are not state functions. I mean, guys, you can easily solve these sort of questions, right? You can easily solve these sort of questions. All the questions based on first law we have done. Okay, let me see if you remember things or not. Can you let me know at A or B, where is the Cp value more? It is enthalpy versus temperature. Where will be the Cp value more? Quickly. I just want to see how much you remember. Where is the Cp value more? At A or B? Enthalpy versus temperature. Remember, Cp is equal to dH upon dt, right? So you'll draw the tangent at A and B. Wherever the slope is more, Cp will be more. Already we have discussed this. So Cp at A will be more than that of B, right? Okay, good. Okay, rest all the questions are from your enthalpies of reactions, which we shall be doing in the next session. Okay. So I think your thermodynamics part is absolutely clear. Guys, let me tell you very honestly, if you watch this session from first minute itself, you'll be easily able to solve all the questions in thermodynamics. You can trust me on that. There won't be a single question asked apart from the patterns which I've showed you here. Okay. Nothing will be asked apart from the types of the questions which I've showed here. Trust me on that. And there are 3 topics left. One is your enthalpy of reactions, one is entropy, one is Gibbs free energy. That will be done in the upcoming session, which is going to be for thermochemistry. Okay? No, in the morning we won't have the problem practice session. No, not this morning. I'll let you know when. So first we'll complete the thermochemistry part, then we'll have the problem practice session, yeah? Okay? Done? All right, people. So I think with this, I'll be taking a leave then. Right? Do let me know in the comment section if you liked the session or not. Okay? Chalo. Yes, organic chemistry also I'll be doing. Chill. Chalo guys, take care. God bless you all. See you. Bye-bye.